fermions, with non-invertible symmetries, without non-invertible symmetries, and continuum and lattice. So there's a huge literature, and what basically our goal was is to sort of find some framework that could perhaps deal with all of these kind of questions. Anyway, let me sort of set the scene. What is actually the question we're trying to generalize? So in physics, there's sort of this famous Landau paradigm which says a continuous second-order phase transition is a symmetry-breaking transition. So usually, the symmetry is a group G, and I'll sort of focus in all of what I'm saying is the groups are usually finite groups, and the categories are semi-simple, so I always have finitely many generators of my symmetries. So G is a symmetry group, and it can be spontaneously broken to a subgroup H, and then there'll be G mod H many vacua, and the broken symmetry acts on these. So that's sort of the canonical picture. And when you take, for example, G equals to Z2, this is basically there are two phases. One is a trivial phase, where you have a single vacuum, and you act with a symmetry and acts trivially, and that's sort of the case when H is Z2. And then there's the spontaneously broken phase when I have two vacua, and the broken symmetry acts between these. It's, of course, very well known from sort of standard symmetry breaking considerations. And if I look at this in a two-dimensional system, essentially these two things would be gapped phases, so the topological phases, and the second one is essentially characterized by a non-trivial vacuum expectation value for an order parameter that's charged. So it's a charged operator that gets a non-trivial vacuum expectation value. And now I can ask, is there sort of a transition between these two phases? And indeed, if I look at sort of this phase diagram, there is a critical model, which is the Ising conformal field theory. So it's a gapless theory that sits between these. So you could think of this as the phase transition between this trivial and the spontaneously broken symmetry phase. So this seems sort of abstract. There's a very concrete way of thinking about this, which in all these considerations is helpful, also when we generalize the types of symmetries we're looking at, which is the Ising sort of spin chain. So it's a very simple Hamiltonian model in quantum mechanics. It's a spin model with a Hilbert space that's C2, and we have L sites, so just spin a half up and down spins, L sites, and there's a nearest neighbor Hamiltonian. Z and X are just Pauli matrices. There's a nearest neighbor Z interaction, and then there's a coupling strength G, and then X. So this is a transverse field Ising model, and that realizes precisely this transition I just talked about. So there's a Z2 symmetry, and that's the symmetry we're looking at. That's the one that sort of gets broken or is unbroken in the various phases, and that just flips the spins. So we have all spins up or down, and we can flip the spins. And so the first sort of ground state with the first phase with two ground states is we have all spins up or all spins down. That's the so-called ordered phase, and the spin flip just maps between these two phases. That's the case when G is actually just set to 0, and this is the dominant term here. If the second term dominates, then in fact the ground state preserves the Z2 symmetry, and then they get a disordered phase. And indeed, now at G equals to 1, we get this critical model, which is the Ising CFT, central charge equals to 1/2, and this is this sort of mini phase space of this spin model. So that just realizes this transition that we just talked about. This model is also useful, not just to illustrate sort of this simple symmetry breaking paradigm, but it also is useful actually for another angle, another sort of direction that this talk will be going, which is that this also has an interesting duality symmetry between the G less and G bigger than 1 regions. If I map X to ZZ and ZZ to X, this basically corresponds to G goes to 1 over G, and that actually maps this region to here. And of course, at G goes to 1, this becomes a symmetry. And this sort of symmetry basically is a symmetry of the Ising CFT. And if you square the symmetry, in fact, it squares to 1 plus the Z2 transformation. And this is this sort of Kramers-Vanier duality symmetry, and it's realized in the spin model very concretely. You should keep in mind that in essentially all of the models I'll discuss later that are more complicated with non-invertible symmetries, you will always have a simple spin model like this. And if you'd like to know more about those, I'm happy to discuss them afterwards. Anyway, so this segues, this sort of symmetry at this critical point segues nicely into the second part of the title, which is not just the Landau paradigm, but also the Landau paradigm in the context of non-invertible symmetries. So in the last 10 years, we've sort of generalized the concept of global symmetries in physics, essentially starting with this seminal paper here by Gayota, Kapustin, Seiberg, and Willett in 2014. And the idea is topological defects in physics should be identified with symmetries, and the most recent generalization is to the so-called non-invertible, or in this context here in this room, I think I can fairly certainly use the word categorical without half the room running away, so categorical symmetries. So these are, the simplest examples are really these fusion category symmetries. And most of my talk will be about fusion categories. So just to very roughly explain what the structure is you compose two symmetry generators, and what you get is not just another symmetry generator that is sort of like a group composition law, but you get a sum of generators, usually with non-negative integer multiplicities. There's a bit more structure, and I'll explain it in a moment, but there's a long history in two-dimensional quantum field theories about fusion category symmetries, but what's sort of in the last few years been really exciting is that, starting in 2021, is that such symmetries can also exist in higher dimensions. So you can construct quantum field theories with these sort of non-invertible composition laws, and in fact their symmetries form higher fusion categories, generalizing this notion of fusion categories. So just to be clear what a fusion category symmetry is, so you have a two-dimensional theory, and in a two-dimensional theory, all you essentially have, apart from strange -1 form symmetries, are zero-form symmetries. So these are just standard sort of zero-form symmetries as we know them, but they can now have these non-invertible compositions. So they're generated by lines. I always have these D1 subscripts to indicate the dimension of these topological defects, the topological lines, and they will have they have morphisms between them. So there's a morphism, which is now basically topological point operator, and the fusion is given in terms of this general fusion rule given here, and I can also depict this in terms of a picture like this. In addition, there can be sort of associativity conditions, which come from sort of how you've packaged, say, the composition of three lines, and these coefficients here will satisfy additional consistency conditions. So this is all the structure that forms a fusion category. The ones I will study are extremely simple. It'll be the Ising category and the representation category of a group. So let's just recap what this Ising fusion category symmetry is. That's the one that was realized at the critical point of this Ising chain. So it has a Z2 generator and this non-invertible generator n. So eta squares to 1, but n squares to 1 plus eta. And so this Kramos-Vanier duality symmetry. Another simple fusion category symmetry is coming, or a huge class is coming from the representation categories of non-abelian groups. So if you take a finite group G and you look at the representations of it, and you associate the representations to the lines, and now you look at the composition, and the fusion is given in terms of the tensor product decomposition, then that also gives a fusion category. So the simplest finite group that's non-abelian is S3, and so that the representations of S3 will form such an example of a fusion category. So here are the irreps, which are sort of the simple lines, the generators, or the trivial representation, the sign representation, and then also a two-dimensional representation I'll call E. And now this sign representation, of course, squares to 1. That's just the signature of a permutation. But E actually squares 2, and now this is just a tensor product decomposition of this two-dimensional representation into the irreps. And that's, again, a non-invertible fusion. So these two examples will be useful to keep in mind for the rest of the talk. I will not talk too much about the higher dimensional incarnations of non-invertible symmetries, but just to give you an overview, I think there were talks by Matt and by others about categorical symmetries, but just to give you a quick idea of what type of constructions they are. The first one is very much similar to the one that appeared in this Ising chain. You have a duality symmetry, you have a duality that acts on a quantum field theory in this case in 4 dimensions, and a particular point in the parameter space of this quantum field theory, this actually becomes a symmetry, and then this duality actually generates or represents a zero-form symmetry that's non-invertible. So this is a 4-dimensional Kramers-Wanier duality defect. The other defects, which are condensation defects, which come from gauging a higher form symmetry on not the full space-time, but a subspace. And then there are also gaugings of outer automorphisms, where you have an outer automorphism of your gauge algebra, for example, and then you get naturally non-invertible symmetries because only certain combinations of symmetry generators of the original theory are actually invariant. And if you square, say, this one-form symmetry generator, you get automatically a sum of other things. This just to highlight if that's the kind of constructions you can think about in higher dimensions, and that sort of has ignited this whole field. Then what the structure that governs these type of symmetries is this higher fusion category symmetry. So in addition to lines, you will generically have p-form symmetry generators, so topological defects that will act on p-dimensional extended operators, and in d dimensions, they are of dimension d minus p minus 1. And so in d dimensions, you would have a d minus 1 fusion category symmetry, which has topological defects of dimension d minus 1, d minus 2, all the way until 0. And all of them will have a composition, and they will also have certain associativity and compatibility conditions. So for a 3-dimensional quantum field theory, you would have surfaces, lines. Lines can also be junctions between these surfaces and points. And so in 2 dimensions in Ising is that, in fact, there's up to gauge equivalence, a classification of these types of 2 fusion categories. Okay, I will not talk too much about these things, but one really essential bit, which is true for both the 2-dimensional but also the higher dimensional non-invertible symmetries, is how they act on charges. So in a standard group-like symmetry, you would have say an operator and a zero-form symmetry, and you could measure the representation or the charge by surrounding the operator with a topological defect of codimension 1. For non-invertible symmetries, the structure is different, and I'll sort of illustrate this for you in this example of the Ising category, but this extends also to higher dimensions. And this is sort of a hallmark of how non-invertible symmetries are represented. So if I call a Q charge, so a Q-dimensional defect in the representation of non-invertible symmetry, you can study these in 2 dimensions using structures called tube algebras and the lasso action and so on. But effectively, this is this beautiful argument in Fröhlich, Fuchs, Funkel, and Schweiger, which goes back many, many years. Just look at the Ising category. You have these lines. This is the non-invertible line. Now we can act on a local operator. So you can insert, say, for example, the spin operator in the Ising CFT and pass this topological defect through sigma. Because it's topological, I can sort of bend this out, then use the fusion of n squared, and then actually at the end of this, I get another local operator, but now attached to this eta line. So in fact, this action of the non-invertible symmetry is always between a genuine operator, which is sort of not attached to a topological defect, and a non-genuine operator that's attached to a topological defect. So this also percolates throughout the whole representation theory of these generalized non-invertible symmetries. Okay, so that's the setting. So you should think of these as a new class of symmetries, in particular in higher dimensions. And now you can ask how we generalize the Landau paradigm that we spoke about in the Z2 example to such symmetries. When I have a fusion category symmetry, a higher fusion category symmetry, can we now, for example, explain transitions, phase transitions that cannot be explained by, say, a group-like symmetry? So in condensed matter, people are very much into understanding such beyond Landau transitions, and so one hope is these symmetries may actually help us to explain at least some of them. And we'll see many examples where the symmetry being non-invertible is essential. So to actually develop this framework, we'll have to actually see, well, first of all, what are the gapped phases? So this is like the SSB phase or the trivial phase, or maybe maybe some SPT phase. What are the order parameters? So these will be generalized charges. And then also how do we study these transitions between, say, a gapped phase, another gapped phase of a given symmetry. So there should be some gapless or some scale invariant theory sitting in the middle. That's what we'll try to sort of develop. I'll focus mostly on two-dimensional theories or two-dimensional phases, but this can also be extended to higher dimensions, and I'm happy to talk about this. So one essential piece in this study to make this a systematic sort of framework is the so-called Symmetry TFT. And the Symmetry TFT was sort of, it's known in the math literature in the context of Turai-Vero theories and two-dimensional theories. It's the three-dimensional topological field theory. Essentially, the way to think about it is you're given a quantum field theory with some finite symmetry S, and then the symmetry topological field theory corresponds to gauging that symmetry, but not in d dimensions, but in d plus 1 dimensions. So you have a TQFT in this sort of d plus 1 dimensional space, and the actual physical theory is d-dimensional. And the statement is if you put the symmetry TFT into a certain configuration on an interval with certain boundary conditions, you will get back, after the interval compactification, the original theory T. So there are many, so this terminology, that this is a sandwich, and in fact, it also is sort of related to the square of a quiche, comes from these gentlemen here. I think one of them is in the audience. This is a slightly peculiar terminology, but we will return to this because there are generalizations of this when we study gapless phases. So you should think of this as you have two boundaries of the SymTFT, and those determine what the theory and its symmetries are in d dimensions. Examples of the SymTFT is for a p-form symmetry, abelian, it's just a BF theory. And it's a Dijkhoff-Witten theory for, say, a Zien p-form symmetry. It has a background field BP plus 1, and it's dual, and there should be a D here. I'm really sorry, and the degrees don't check out. I'm really sorry about this. It's terrible typo. But then also in 2 dimensions, for example, the 3-dimensional TQFT are the Turai-Vero theories. The topological defects of the symmetry TFT will be the main players because they will actually correspond to the generalized charges. They will determine for us the order parameters, the types of boundary conditions. And so in fact, given a symmetry S, a categorical symmetry, they are forming what's called the Drinfeld center of this category. So the two boundaries are what the SymTFT really is sort of really importantly depending on. One thing is that on the left-hand side, we have the symmetry boundary, and that's essentially where all the symmetry aspects of the theory live. So for example, the topological defects that will generate the symmetry will live on this boundary of this interval. And in terms of boundary conditions, these are topological boundary conditions for this d plus 1 dimensional theory, and they're classified in general terms by Lagrangians inside this Drinfeld center. On the right-hand side, you have the physical boundary. That doesn't need to be a topological boundary condition. It sort of captures all of the non-topological aspects of the theory, the dynamics, and usually the charges will be things that stretch between these two boundaries, and we'll talk to the physical and the symmetry boundary. And indeed, after the interval compactification, you get the theory together with the action of the symmetry. So the point of this is that you can separate symmetry aspects from non-symmetry aspects of the theory. And we'll see that this framework also allows us to classify all the gapped phases. How do I recover the symmetry? As I already said this comes from topological defects that have a projection to the symmetry boundary. So these are the Neumann boundary conditions. And the ones that are mutually non-local with them, they're essentially part of this Lagrangian algebra that defines the boundary condition. So this is basically how you recover the symmetry. And the charges come from this linking action. So if you have a topological defect that ends on both of these boundaries, and there's a dual sort of D that links with these in the bulk. So in the SymTFT, these topological defects have a non-trivial linking, and in 2 dimensions, they would be it's a 3-dimensional topological order in the bulk, and this would be just the linking between 2 topological lines. Then this type of configuration, this will become, if this projects and becomes a symmetry generator, then this calculates precisely the symmetry action on a charge, which comes from the compactification of this line that has Neumann directly boundary conditions on both ends, computed in this sort of Sim TFT picture. So a charge is coming from a linking in the Sim TFT. And finally, there are also these non-genuine operators that are attached to some topological defect, and they come from these lines that sort of have these L-shaped configurations. You can also get these types of things, and in this way, we will see the action of the non-invertible symmetries in this context. Okay, so the Sim TFT for finite groups is already interesting, particularly if G is non-abelian. I'd like to actually go through what the structure of this Drinfeld center of this fusion categories. So the group-like symmetries in 2 dimensions, they're just forming this fusion category vec G. They're just graded G-graded vector spaces, and the lines in the center are labeled by conjugacy classes and representations of the stabilizers of an element G in this conjugacy class. So that actually is all the topological defects in the Sim TFT. And of course, the question is now, how do I, from this structure, extract out, for example, the boundary condition that gives me back the group-like symmetry? Or how do I extract, say, the symmetry where, for example, I have gauged that symmetry? So the Sim TFT is, in fact, completely blind to start with as to which type of global, gauged form of the symmetry you've taken. And that's actually given in terms of these Lagrangian algebras. So these are with the gap boundary conditions. So these are algebras in this center where I take linear combinations of these lines with coefficients, and they have to satisfy certain consistency conditions. And the fact that they're Lagrangian means that they're of sort of maximal dimension. So you're picking a maximal set of mutually local lines, essentially, and they form this Lagrangian algebra, and they can then end on the symmetry boundary, and the ones that are mutually non-local with them, they will become the symmetry generators. In the case of S3, which is the simple example we talked about before, the group is just the same indirect product Z3, Z2. The irreps are the trivial, the sign, and the E representation, and then we can write out the conjugacy classes, the representations of the conjugacy classes, and then this is the Drinfeld center of S3, or vec S3. It has these lines here, and now one can ask, what are actually these gap boundary conditions? And indeed, there are these 4 gap boundary conditions, and 2 of them are the ones that we've encountered before. This one here will give rise to the vec S3 symmetry, so it's just a group-like symmetry, and this one will give rise to the rep S3 symmetry, which is the non-invertible symmetry. And then there are 2 others, which are sort of, I will discuss them later. They come from particular gaugings of these. For example, this one is rep S3 mod Z2. But there's a full list of gap boundaries. And now you'll ask, why am I telling you all this? Well, okay, so there's another piece that sort of is essential, is how actually the symmetries then act. So we can get these non-trivial actions of symmetries on charges by looking at this Drinfeld center and the linking inside there. So for example, for S3, basically these ones are just the representations of S3. So these are the untwisted charges when they end on both boundaries, and these are the twisted sector operators. And in the rep S3, it's a bit more complicated, but the crucial thing is what I explained at the beginning. You get these combinations of genuine and non-genuine operators sitting in the same multiplets of the symmetry, and that also comes out from this Drinfeld center computation. So for example, there's a local operator, an operator O plus, and this non-genuine operator O minus, and in fact we can calculate the action of the symmetry, and it maps this operator to this plus some phase and the non-genuine one, and vice versa. Okay, so just to summarize maybe the Sim TFT, basically has the topological defects are the generalized charges. The gauging actually corresponds to changing the boundary conditions, and if 2 symmetries are related by gauging, then in fact they have the same sim TFT. At least this is true in the two-dimensional setting. This construction exists for any higher fusion category also, and concretely, for example, for two fusion category, where you have a group-like symmetry, maybe with an anomaly, this has a concrete decomposition in terms of some simpler objects, in terms of these two wrap categories of destabilizers. And of course, there's recently been work also here at CISA about extending this whole structure of the sim TFT to continuous symmetries, where then you can also include, for example, higher groups with continuous factors, etc. Okay, so why am I telling you all about these gap boundary conditions? And in fact, this comes from the fact that this will lead us now to how we will classify these symmetric gapped phases. So in the sim TFT, I said, well, the physical boundary condition usually is chosen not to be a topological one, because usually you're looking at a quantum field theory, and it's not necessarily a topological theory. But if you're interested in symmetric gapped phases, then in fact, you would like to pick also the right boundary here to be topological. So in fact, we said that those topological boundary conditions are given in terms of the Lagrangians in the Drinfeld center. So in fact, once I fix the symmetry on the left, I can now cycle through all the Lagrangians, and then the collapse of this will give us TQFTs with symmetries S. And the types of things that can happen are essentially exactly similar to the group case. There'll be sort of spontaneous symmetry breaking phases, so this is this case here. And they can be characterized in terms of the Lagrangian that characterizes the symmetry, and the symmetry Lagrangian actually having more than one element inside. If there's only one element, it means there's a single vacuum, then in fact this is what's called a symmetry protected topological phase. So in fact the Lagrangians, its properties, is sort of encoding the types of gapped phases we get, and also the order parameters, etc., and the number of vacua, which is precisely the number of sort of lines that stretch between both of these boundaries. So just to be concrete, we will repeat this now for a case we know extremely well, which is again the group case, but there's some surprises as you go to the gapless setting. So I just want to repeat this very briefly. The case of the Z4 group-like symmetry, which is totally a Landau kind of symmetry breaking setup, but it's useful to see it in this sim TFT picture. So we expect there are subgroups and then potentially some phases. In this case, there's no real phase. So essentially, we're expecting there to be the Z4, the dual Z4 symmetry, and then something that's a gauging of a Z2. So those are the phases we expect. The sim TFT is the Z4 Dijkgraaf-Witten theory, now written correctly. This is the form of the Dijkgraaf-Witten theory here. And the topological defects, these are the Drinfeld center sort of generators. These are these holonomies of B and C. And they have these lines in the center, have these relations here, so that actually E to the 4 and M to the 4 is 1, but we can have these combinations of lines. And E and M, of course, braid non-trivially because of this BF coupling. The Lagrangians are these three Lagrangians, so these can just be computed from these general conditions. And the one that gives this sort of Z4 symmetry is the first one here. So I fixed that to be the symmetry. And now I ask, what are the gap phases? So the gap phases are slot in one of these three on the right-hand side and calculate what the properties of that sim TFT setup is. So we fix the symmetry boundary to be the one for Z4. And then we can, for example, look at the same boundary condition to be the physical one. So now every line in this Lagrangian, so E1, E squared, and E cubed, they can all end. We get 4 non-trivial order parameters. And in fact, this means there are 4 vacua here. And this is precisely Z4 spontaneous broken symmetry phase. There's the dual sort boundary condition, which is the Neumann boundary condition, where I just have 1 m squared, m cubed. In this case, I just have the identity line, so I get the single vacuum, so that's a trivial phase. And finally, there's one which is sort of a mixed boundary condition, and that actually has 2 vacua. So that's precisely what we expected from the Landau sort of general analysis, and this is sort of the sim TFT picture of it. But the nice thing is this we can apply also for, say, non-invertible symmetries. So for example, for Ising, the sim TFT is the double of Ising, so Ising box, Ising bar. There's some topological lines. I will not bore you with the details, but there's a single Lagrangian algebra. So I will get only one choice, and I get 3 vacua. And in fact, we can also, because we know the linking of these topological lines with these lines that are the order parameters, we can see how the symmetry acts. So the Z2 will act trivially on one vacuum, and then exchanges these. So there's basically a trivial Z2 and a SSB Z2 phase, but a non-invertible symmetry will act between these non-trivially. So this is sort of how the Ising gap phase, this Ising SSB phase, so to speak, is realized in this context of this sim TFT, and we can extract the action of the symmetry and the order parameters. So for S3, we already wrote down all these Lagrangians. There are 4 Lagrangians, and there are these symmetric phases. There's a trivial phase, a Z2 SSB phase, a rep S3 mod Z2 SSB, and the full spontaneously broken symmetry phase. You will see that this actually is very reminiscent of the action of what we saw in the Ising case here. But in fact, there's a crucial difference that in this case, actually, there are relative Euler terms. So in fact, this phase can be distinguished from the phase from this Ising. Okay, so for gap phases, the sim TFT gives you a complete classification of the phases by just classifying Lagrangians and then looking at these configurations. But what's also interesting is to ask what happens to these gapless phases, and so how do we consider transitions? So we have a gap phase and another one, and now can we actually have a sort of critical point between these, and can we study its properties, what type of CFTs these are? So one observation is if I have 2 gap phases in 1 + 1D, we said these are Lagrangians of the Drinfeld center, then there's a sort of a natural guess that this object here will be determined in terms of an algebra that's, again, a set of lines that will end on some defect, and that's the intersection of these 2 Lagrangians. But this will generally, of course, be non-maximal. So the question is, in fact, what's the physics of this? How does this actually help us characterize? Isn't this actually the moment when you need to extend the sim TFT picture? So from a sandwich, we now need to extend it to a club sandwich. So we have 3 slices of bread with fillings on both sides. And when you open it up, which is the structure that was, I think, dubbed the quiche, now becomes a club quiche because you have sort of a sandwich plus a quiche on top of it. Anyway, why is this relevant? So the key is these algebras that are non-maximal, in fact, will give rise to interfaces between topological orders. So for example, I will start with a symmetry S. That's the symmetry I'm interested in. And then such an algebra that's non-maximal will define interface to another topological order, usually a reduced topological order. And so this configuration here will in fact determine for us these gapless phase transitions. If you just look at this picture, I can also collapse this side here. And then it's saying to this topological order, this actually characterizes boundary conditions that are S-symmetric. And they may not be sort of irreducible boundary conditions, but usually there are some sum of boundary conditions. So this is not an irreducible boundary conditions. We'll see many examples of that. But it'll be an S-symmetric boundary condition to a topological order that's not necessarily the center of S. So in fact, if A is a Lagrangian, right, if this interface here is given in terms of Lagrangian, then in fact, then you're giving just that the Z prime is just trivial, and so you just get the gap phases. But if this interface is determined by a non-maximal algebra, then in fact this Z prime is a reduced order, and in fact, it'll be the center of a smaller symmetry S prime, a reduced symmetry S prime. Okay, so this is sort of the picture. The club sandwich is then the closure of that, where I start with this is the sim TFT of the symmetry. I have a non-maximal algebra, so I end a subset of lines, and then essentially there's a reduced topological order, and then I can slot in the B physical, and this object will have a symmetry that is S. But in fact, this physical theory here may not be sort of initially, this theory actually may only have a symmetry S prime, and in this way we'll get actually a theory that has a symmetry S. So it's a way of bootstrapping from starting with a symmetry, a smaller symmetry, a gapless phase that has this larger symmetry S. So in condensed matter, this goes under the name of Kennedy-Tasaki transformations from an S prime symmetric to an S symmetric theory. So just to, yes? The interface is, well, it's given in terms of just a non-maximal thing, so there'll be some operators on it. We'll see what the interface will look like in a second.
Okay.
But it's all topological, I think. I think so, yes. Right, so for example, I start with a theory that has S prime symmetry, and I can construct just the sim TFT. So think of this as the smaller symmetry. There's a sim TFT for this. Then I can slot in this club quiche that connected to the sim TFT of S. And then this sort of compactification on this side here will give us now an S-symmetric theory out of this construction. So I essentially feed in a transition for smaller symmetry and get a KT transformed, larger symmetric phase transition. Okay, so let's see this, and this is interesting already for the Z4 case. So we will see that if we look at these non-maximal algebras, already in the Z4 case we get some interesting structures. So for example, in this case, the condensable algebra, so all these sets of lines that are consistently can be ended, and it's sort of consistent diffusion, is the identity line, this one here, 1 plus E squared, 1 plus M squared, and 1 plus E squared, M squared. So you can see these are not maximal, these are not the Lagrangian lines. This club quiche says there's a sim TFT for Z4, but then certain lines will end. So in this case, E squared ends, but the other lines will just propagate through, and then there'll be some reduced topological order. In this case, it's Z2. In this other case, it's also Z2, but in this case, it's Z2 omega. So this is Z2 with an anomaly, the double semion theory. So this is just a way of bookkeeping how the condensing of lines, or the ending of certain lines that are not maximal, lead to interfaces between topological orders. And now we can, of course, take one of these configurations, so for example, this club quiche here, and then slot in and then ask what is actually the interpretation when we compactify this Z4 interval. We get a reduced boundary condition for the Z2 topological order. And in fact, the Z4 still is acting on this. That was the whole point of that. So you get essentially sort of a configuration of a Z2 symmetric theory with a Z4 acting between them in this way. You get a Z4 symmetric gapless theory as soon as you've slotted in on the right-hand side now a Z2 symmetric gapless theory. So for example, the Z2 one, of course, naturally is the Ising CFT. So for an example of the Z4 symmetric gapless phase is Ising plus Ising, with the Z4 acting as an exchange between these two, and a Z2 subgroup acting inside the Ising as the standard Ising symmetry. So that's the transition between the Z4 and Z2 SSB phases. And then there's also the transition between the Z4 trivial and Z2 SSB, which is this Ising model with the action of Z4 on it. Okay, so that's for invertible, and now the nice thing is we can do the same for these non-invertible symmetries, because the whole formalism is completely blind to whether you've started with an invertible or non-invertible one. You can repeat the whole thing, and now, for example, in this case, you get reduced topological orders that are Z3. So the initial transition will be something like a three-state Potts model. So that's giving you sort of this initial transition, and then one can use that, for example, to construct the associated gapless phase for rep S3. There's also one from this one here, from this example here, which is similar to this Ising plus Ising, but again with some relative Euler terms. You get an Ising plus Ising transition with the non-invertible symmetry acting. Okay. All of this can be put together into sort of a phase diagram, sort of a cartoon phase diagram. So we have the gapped phases for rep S3 with the 4 gapped phases, There's all these vacua and the action of the symmetry. The red is the non-invertible symmetry. The blue is the Z2. And now between these, here there's a Z3 Potts model, Ising model, and then here you have the Ising plus Ising. And this it can be sort of understood both in terms of the continuum analysis using the Sym TFT, but also in these papers by our group and also by Chatterjee, Aksoy, and Wen, there's a lattice model with RAP-S3 symmetry, where this phase diagram can be realized by just starting with a lattice model and tuning parameters, which realizes this RAP-S3 symmetry. So that really has underpinning in some, lattice computation, and so that's an extremely nice sort of story. There's also some multi-critical point, which I think Wen and collaborators try to pin down, and that remains a little bit of a question, which corresponds to basically the algebra 1 in this case. Okay, so the roadmap to get phases, all phases basically, for a symmetry S is you construct a Sym TFT, you construct the center, classify all the condensable algebras. The maximal ones give you the gapped phases, and the non-maximal ones will give you the gapless phases, and then there'll be some transitions between these, which are essentially characterized by intersections of Lagrangians. And all these condensable algebras, in fact, have a structure which is a partial order. So in fact, you can also put them into what's called a Hasse diagram. So for example, Z4, these were our Lagrangians, and then these non-maximal ones, so our sub-algebras in these two Lagrangians and so on, and then we can pick. So this is simply an analysis in the Sym TFT. We haven't committed to any symmetry yet. If you pick a symmetry, it means you pick out one of these Lagrangians to be the symmetry one, and then each one of these boxes come to life as a particular phase. It's a spontaneous symmetry breaking phase, or an SPT phase, or SSB phase. So in this diagram, I want to sort of explain a little bit the types of phases that there are. So we already talked about these SPT phases, which are these symmetry protected phases, a single vacuum, and you can't deform to the trivial theory without breaking the symmetry. There are also analogs of that in the gapless world. So these are these gapless SPT phases, and they have the same property that the Lagrangian and this algebra intersect in one. But then there are also interesting ones, which essentially are these sort of IGSPT, so they're intrinsically gapless, and they have sort of, the criticality is protected here by the symmetry. You can't actually deform this without breaking the symmetry to an SPT phase. So these actually never connect to SPT phases in the gapped world, only potential to SSB phases. And there's sort of an analog in the world of SSB phases, so the gapless SSB phases. So in this sense, you can now map out for any symmetry category, you pick the symmetry category in the center, and then classify these algebras, and you get these type of diagrams. And I was saying, so for example, for the center of RAP-S3, this is the Hasse diagram. You can pick, for example, the symmetry S3, and then determine what all these different algebras correspond to. But you can also pick a different boundary condition and look at the RAP-S3 phases, and then get sort of this diagram, and the phases have a different interpretation. So for example, in this case here, right, this will be an SSB, this will be an SSB phase, but in this case, this is an SPT phase, etc. So it's a sort of gauge invariant way of characterizing all the, the possible phases, and then you put properties onto them once you picked the symmetry Lagrangian. And if you have very powerful students, they will also give it to you for RAP D8. This is sort of Allison and Dan's work. And there's actually, this is not just sort of entertainment, but there's a really interesting thing from the point of view of studying gapless phases. There's an intrinsically gapless SPT phase for this RAP D8 symmetry, which is sort of the first non-invertible such phase. Okay, so I'm running out of time. 4 minutes. Okay, so maybe, so just a few general words about how to characterize these phases. Essentially, there's sort of the gapped versus gapless. So there's an energy gap in the spectrum. It's bigger than 0, 0. But there's also sort of a SPTness. so how much of this is there a symmetry gap? And what I mean by symmetry gap is basically the symmetry gap is bigger than all the charges of S can be realized in this phase. And so there are some charges that are actually confined. And so all phases should be labeled by both what the symmetry gap and the actual energy gap is, and then you get this classification of gapless, gapped, SPT, SB, and so on. Okay, so this is the table. So the roadmap is very clear, and basically you carry out this program for your favorite symmetry category, and this should give you a characterization of all the phases that are possible. Now, you might ask, are there actual physical systems that realize these types of symmetries? And the nice thing is that for fusion category symmetries, there's something called the anion chain. So it's a spin chain that actually has the fusion category symmetry built in. So it's symmetric under that given fusion category symmetry. And this type of analysis can be carried out in parallel for any fusion category symmetry for the anion chain. So you can also construct anion chain as Ising, Fendley, Mong, and others. And so the anion chain has some drawbacks in terms of the properties that's maybe not realized on a single tensor product Hilbert space, but in this case of the RAP-D8 that I gave you this phase diagram, you can realize it on a tensor product Hilbert space, and one can feed in sort of the general continuum analysis property. So I can feed in the algebra, the symmetry that provides a chain that realizes that specific phase. Okay, so conclusions, open questions. So I focused in this talk mostly on two-dimensional phases with fusion category symmetry. There's many sort of interesting open questions to extend this to higher fusion categories, particular to 3D and to 4D. In 3D, of course, there's this interesting thing how one could connect to the classification of 3D topological order in this context. Also, what is the meaning, the physical meaning of higher dimensional GSPT, IGSPT, etc. phases? So there are some examples of GSPTs in 4 dimensions that Dimitrescu and Sin studied, and Thomas gave a really nice talk at Strings last week. So certainly these things will have some interesting insights in higher dimensions. And finally, also, it would be interesting to extend all of this to the study of not necessarily finitely many symmetry generators, to so non-semi-simple categories, also continuous symmetries, so that we can build these into also these symmetry considerations. So I should also mention, if you are interested in this field, there are 2 meetings. One is in Oxford in August, where there'll be sort of condensed matter theorists and high energy theorists and mathematicians will come together. And then there's a long program at KITP, again, math, physics, and or high energy physics and condensed matter physics. So you're welcome to please come to these meetings if you're interested. Thanks very much.
Yeah, thank you very much for this nice talk. Are there questions?
There's a question there.
Yeah, I'm trying to understand the general picture. So in this club sandwich picture you have, right? So you have, I guess you have a Lagrangian subalgebra on the leftmost boundary.
That fixes the symmetry.
Yes. Okay. Great. So if I choose a Lagrangian algebra, if I choose a Lagrangian algebra on the interface, which
then you have this reduced order is just trivial, so you get a gapped phase. Right, so the interface will be 1 to the trivial topological order. Because you end all the lines, right? It's a maximal set of lines that will end, so there's basically, this is all the maximum set you could condense.
But I can choose exactly the same Lagrangian algebra as the leftmost one, or choose some other Lagrangian algebra.
You get an SSB phase.
Oh, I see, okay.
Right, so this was this analysis. You have a gap phase. This is, for example, this one is the same as this one, then you get an SSB phase. But both of these are gap phases, gap boundaries.
And if I choose a different Lagrangian algebra, that will
Then
be
you will get a different gap phase. This was this one, this is this one, this is this one. So as you go through all the Lagrangians, you go through all the possible gap phases with that symmetry. Z4 SSB, Z2 SSB, and then this is a trivial phase.
okay. Thanks.
And then if you have a non-maximal one, you get an interface. That's sort of the description of the gapless phases.
Are there more questions?
Sorry. There are some general framework for capture this phase transition from the holographic point of view. You can realize the 3 and the 4 dimensional theories in holographic.
Yeah, so that would be interesting. I think we don't quite know yet enough about the transitions, at least from this sort of, for non-invertible symmetries, right, you're asking. So I think we first need to understand the general formalism. But certainly holography is, the Sim TFT has many similarities to holography, right? It's just a sort of topological sector of the holographic, reduced action. So that seems like a way you could maybe approach it once you've understood sort of the general framework, for sure.
Yes, I see another question.
So this type of discussion can be done both on the lattice and
Yes.
in field series. And on the lattice, there are some subtleties. For example, there is a translations needs to be involved, and then the fusion categories.
No, I mean, this is, if you want to realize a symmetry on a tensor product Hilbert space, then you need to also involve lattice translation. So Nati, Shuhang, and Sahand have this Ising chain, symmetric thing.
That's
Then
what I mean.
if you want to have tensor product Hilbert space, then there's translation that comes into this. However, this anion chain is a setup where you can just realize the symmetry without any of these additional, the cost that you might have to pay is, it's not a tensor product Hilbert space.
I see.
But then it still gives a way to characterize these phases in this context.
I see. Okay. Okay. So if you don't care about the factorization of
That's
the Hilbert
right.
space, then the story is
That's
parallel.
right.
I see. Great. Thank you.
Are there more questions? I don't currently see any, so let us thank Sakura again. And we shall resume at 10 for the next talk.
But this is not, Ising is a Z2 symmetric transition. Is the CFT, not the Ising categorical symmetric. If you metric set of phases, in your parameter to G equals to 1, Z2, but it has a larger symmetry. This is the Z2. No, no. Vanilla Ising is a Z2. You actually take a larger symmetry, so it's 4 transitions. Then I have these transitions between. What happens is that the Ising model. That's the critical Gapless. Ising, and then there's a symmetry after. One that is just an Ising. Ising TFT. Gaussians, yes.
One gaugeable.
That's actually just the identity. Actually, this universal Z2 symmetry. This layer structure, and these algebras give you, say, an larger one. And you can use the Z2. As if you just have a Z2. Identity is always the universal.
I mean,
I can open it myself. Turn
Now
it on.
it's working. It's unmuted.
Okay.
I mean, especially in the higher dimension.
Okay. So you have forward, backward. If you keep pressed, you have that one. You can point wherever you want, even down. Doesn't matter.
If I
Always
point
works.
here.
It doesn't matter where you point.
Oh. I see. Okay. Good.
You can point wherever you want.
Interesting.
Good. And is this yours?
Yes.
Ah, okay.
Just put it here.
So if it's strict, you only have one representative. So, I know recent physics has to get ready for the next talk. So.
Okay, so yeah, it's time to continue with the next talk. As our next speaker, I'm very happy to announce Song Sun from the Institute for Advanced Studies in Mathematics in Zhejiang University and University of Berkeley. And he will tell us about small structure degeneration of Calabi-Yau metrics. Please.
Thank you very much for the introduction. I would like to thank the organizers for inviting me. It's a great pleasure to be back to the ICTP after 12 years. Last time was in 2012. So I'm going to talk about a small complex structure degeneration of Calabi-Yau metrics. This is based on work 5 years ago, which was joined with Robin Zhang, who was an assistant professor in Princeton. And 1 year before, actually, we wrote another paper joined with Hein and Vyakovsky, which is related. It's in dimension 2. It's a baby case. So this talk is concerned with Calabi-Yau about metrics. So I'm a differential geometer. So I will talk about metrics So what is a small complex structure degeneration? So this is a simple family of, this is just a given example. It's a family of hypersurfaces in the projective space. So it's parameterized by T. So you choose a generic polynomial Q of degree n plus 2, and then two polynomials of lower degree, f1, f2. So when t is not 0, this is, when t is close to 0 but not 0, this is smooth. When t equals 0, this splits into two parts. So this is a pretty simple. This is an algebraic family. So this is a picture. So I've looks complicated, but I mean, color-wise, it's very colorful. So this is not. We will make use of this later. So remember this. So this D is a intersection of the two components on the degenerated fiber, on the central fiber. I can use this red color, or does not look like red. It looks like, I don't know, orange. So there's also this thing H, which is the intersection of all these three polynomials. So this is certainly on the central fiber, but it also lies on all the general fibers. So it's why this blue thing is always there on all the fibers. And implicitly, you can see that this if you put all of them together as a total space, this is actually not smooth. It's singular exactly along this this point, the special blue point on the central fiber. This is pretty simple. So, and then when t is small but not 0, on this xt, on this general fiber, we can use Yale's proof of Calabi conjecture. It gives us a unique Calabi-Yau metric in the cohomology class, which is proportional to the Fubini-Studi metric. These are hypersurfaces. And we normalize it so that the diameter is 1. So this Calabi-Yau metric, they are richly flat, so you can dilate it. And so one has to if you want to really understand the geometry of a family of them, one has to choose a scale. So the scale now is this is a minimal possible scale with diameter equals 1. So this is a theorem. So this is a picture. So it's even more complicated than the previous one. But then the thing that I want to, my goal is very modest in this lecture. I just try to explain what this picture means. The more precise statement will come later. But right now, just see that this thing, you should think of this as a picture for the metric when t is very small, and so the whole thing is actually very, very close. If you look in the microscopic scale, it looks really like just an interval. It's a one-dimensional object. But then, if you dynamically think of this as t goes to 0, all this thing, I mean, they collapse down. All these the fibers, you think of this as a fibration over the interval, as a map to the interval. These fibers, they are actually all have very small diameter. So there's also colors here. So this color actually is related to the color in the algebraic picture. So before we explain this picture, we need to do some preparations and introduce some languages. What do we mean by convergence? So a Calabi-Yau matrix, a Riemannian matrix with a holonomy group contained in a special unitary group. So this is an example of a matrix with special holonomy. So these are very special Riemannian matrices, and in particular, they have vanishing Ricci curvature. If you want to understand it in terms of complex geometry, one can fix a complex manifold, say X, and then so we have a family of a pair of two objects. One is the little omega, which is a Kähler form. Capital omega is a holomorphic N form. So it's a holomorphic volume form. And the equation can be written simply as you just cook up top forms from the Kähler form and from the holomorphic form. They are proportional by constant. So normally So omega, capital omega is a holomorphic thing. It actually encodes the complex algebraic data. So often, if we're given examples such as this hypersurface gamma, we can write down them explicitly in terms of equations. And the main thing is this little omega, this Kähler form. So this should be viewed as the equation for little omega. So locally, little omega is determined by a real value function, it's a potential function, phi. And then the form of the equation looks like this. You take this Hessian, complex Hessian of phi, takes a determinant. It's equal to some given function, e to the psi. Because this is pretty difficult. Partial differential equation is fully nonlinear. But you can view this as a nonlinear version of the Laplace equation. If you replace the determinant by trace, then this will be the Laplace equation. So when this manifold X is compact, then Yau theorem gives a unique little omega solving this equation, which is cohomologous to a given Kähler form. So this is a PDE result. It's an existent result. So very rarely one can write down explicit equation for little omega. So in Albrecht's talk, so he mentioned that when X has dimension 1, this elliptic curve, you can write down this little omega, but in higher dimensions, it's not known whether we can find an explicit formula for this metric. So the standard example is a hypersurface in the complex project space. You were given omega, then given f, you will get omega f. And then when you can vary f, then you can vary this omega f. So when you vary f, you are really changing the complex structure, changing the holomorphic form. So little omega also changed. So when f degenerates become singular, then little omega f can also become singular. So the example of degenerations is you can more generally you can do splits into k components. So when k equals n plus 2, which is maximum, this is called large complex structure degeneration. So when k equals 2, so that's why this name, small complex structure degeneration. So I gave a talk in 2019 in front of an audience. I just cook up this his name small, and I asked for a better name, but it seems there's no better name, so we just call it small complex structure generation. So we require this n's at least 2, because when n equals 1, that's different. We'll see later. The main question that we're interested in is to relate the differential geometric singularity formation of little omega f to the algebraic generation of f. Recall this algebraic generation is pretty explicit. So what we mean by the singularity formation of this matrix, so this is a terminology, Gromov-Hausdorff convergence. So this is the definition. The sequence of compact metric spaces converge to a limit if this holds. But roughly speaking, it just says that if you look at when J is very large, this Mj and M infinity looks similar in the sense that if you ignore this small epsilon j error, if you allow this epsilon j error, then they're basically the same. So this is a very rough topology. So these maps, we only require they are maps. They're not necessarily continuous. So there's no topology, no algebraic geometry. It's just the, oh, sorry. I show pictures a bit later. So this is just metric spaces. Give you measure the distance and length. The example. So this is a family of two-dimensional objects. So here, this part is getting smaller and smaller. In the end, it forms a conical singularity. So this is an example. So in the previous example, the dimension, I mean, the limit is singular, has a singular point, but this is smooth elsewhere, and the dimension does not change. But in general, dimension can also change. So here, this is this family. In the end, they converge to a two-dimensional family converging to a one-dimensional object. There's also this kind of thing is not always guaranteed. If you give a random family of metric space, you don't get a limit. So here you introduce these spikes and you introduce more and more. In the end, you don't get any limit. Yeah. So in our case, these metrics, they are Ricci flat. So and then we have this Gromov pre-compactness in this topology. And the key point is that this Ricci flat, in particular, Ricci is non-negative. So this is important in Riemannian geometry. It implies that if you take any point, you take a radius r ball around the point, geodesic ball, you take the volume. This volume, if you compare with a Euclidean ball, then this ratio is actually decreasing when r increases. Bishop-Gromov inequality. And this, using this, just by some elementary argument, one can uniform approximate this manifold, this Riemannian manifold, by discrete metric spaces and in all scales. And then for discrete space, this metric is just a bunch of numbers and then boundary numbers, and then you can easily take limits. So this is the idea of Gromov-Hausdorff convergence. So in our setting, we can fit into this topology. We can always talk about limits. But then the question is, what structure do we have about this limit? What are these limits? This is a pretty abstract thing. We don't just take the limit. We also want to understand the finer structure, as the previous picture, like this one shows. There are things that disappears in the limit. If you just take the limit, you don't see this process. So we have to generalize this to rescale the limits. The Calabi-Yau matrix admits natural rescalings. If you change the scale, the limits may be different. So the definition has to be extended to the case when the diameter is not necessarily bounded. So this is a standard. It's just you pick a base point in each metric space, and you say this has a limit to something. If all balls are fixed radius around this fixed point converge to the corresponding ball in the limit. Picture. So this one, if you now increase this this length, but your fixed point, base point is on the left, then in the end, you just see this non-compact limit. But if you choose a different base point, if you choose a base point in the middle, then you will see this two ends. So this will give you a variety of limits. By looking at all the scales and all its choice of base point, you in principle should be able to see all the information of this singularity formation. One last piece of data is there's also beside metric, there's also measure, natural measure defined on this manifolds. So, it's essentially just the volume measure of the metric, but because of the equation, the volume form can be described in terms of the holomorphic form. So this measure actually can be defined without using the metric. It's just the omega t, which conjugate of omega t, and normalize so that it becomes a probability measure. And actually, under this Gromov-Hausdorff convergence, you can also encode this measure, and then we get this so-called renormalized limit measure on the limit. So if your space, there is also a notion of dimension on the limit. If the space, the dimension does not drop, this renormalized limit measure is basically just a Hausdorff measure in the limit. But if the space is collapsing to a lower dimension, then the total volume is going to 0. So one has to do this renormalization. So that's why this is called a renormalized limit measure. And the limit metric measure space, this is not just a metric space, also with a measure. So one can intrinsically make sense of this have a non-negative Ricci curvature. It's called a RCD space. I think there are many people in Italy studying this, this theory of RCD spaces in mathematics. There's a study of the limit spaces with Ricci curvature has a lower bound. This was initiated by Chigger, Coding, and many others. So in general theory, there is this fit into this general theory, but this is only inequality, so you cannot make sense of this limit space as Ricci flat space. This is something not known in general. So why? I mean, yeah. So the measure and the metric actually independent of each other. So if you look at this kind of limit before, the limit is metric, just the standard metric on the interval, and the measure is also the there's a standard bigger measure on the interval. But if you consider a slightly different family, so of metrics, the measure in the limit is different. So this I mean, you can do this. For example, you can just take a R2, a flat R2. You just quotient by finite group, okay? By finite group of order k. That has singularity, but you can smooth out that singularity. But if you let k go to infinity, then what's left is if you, in terms of the polar coordinate, the theta direction will disappear. They only have r direction, but the measure is rdr. It's not just dr. So the difference is that this collapsing is like a uniformly distributed. The collapsing fibers have almost the same length everywhere, but here it's not the case. But back to our degenerate family of Calabi-Yau metrics. So we can talk about the Gromov house of limits and also with this measure. So in our setting, it's known that the volume has to collapse. So remember, we normalize the diameter to be 1. So the volume has to be going to 0. It's by, sorry, I misspelled Van Titton's name. It's Tossati. And then we can also rescale this metric to pick base point and pick in the scale lambda t and take limits. And then we see more refined structure in smaller scales. So a TOEIC example is a case when n equals 1. So this is, this is not this is different from the case when n is bigger than 1. So so where's the picture? It's algebraic. Oh, back. So here it's this D is the intersection of the two components, but in n equals 1, this two components has two intersections. Not this D itself is not connected. So this is n equals 1. So omega t is a metric, is a flat metric on an elliptic curve. As t goes to 0, this flat metric, we know that the only possible degeneration is to collapse to a circle, as this picture shows. It's just abstractly, we know it has to be a circle. The diameter equals 1. And the collapsing is along smooth circle fibrating. You collapse the other circle. So topologically, just observe that this is the same as the so-called dual intersection complex of this x0. So that's some space formed by looking at this x0, and for each component you associate a point. So you have 2 points, and when two components intersect, you connect the 2 points by a line. So here you have 2 points, but you have 2 intersections, so you connect by 2 lines. So that gives you a circle topologically. So this is different from the case when n is bigger than 1, where you only have 1 component of intersection. So instead of a circle, you should get an interval. So this is a very naive picture, but it's actually the motivation for the more difficult high-dimensional study. here, of course, the renormalized limit measure is just standard measure. It's the flat circles. And the rescaled limit. So if you don't want this red circle to collapse, you have to scale this red circle to have radius 1, diameter 1. Then you get infinite long cylinder. And this cylinder you can also be connected to the algebraic degeneration in the sense that if you look at this x0, so each component is actually a CP1. You remove 2 points, it's the cylinder. And the xt itself, for t is small, it can be recovered from gluing of these flat cylinders. So this is very simple to observe. So now I can explain the case when n is at least 2, and this picture is actually for the case when n equals 2. So this says that this space xt, as t goes to 0, its Gromov-Hausdorff limit is the unit interval on the bottom. And topologically, it agrees with the dual intersection complex of the central fiber x0. And also, so here we have 3 colors. So there's this green on the right. On the left, this is purple on the middle. It's the light blue. So the space is consists of 3 building blocks. So the 2 ends are different. They were this complete Calabi-Yau matrix constructed by Tian Yao in 1990. And in the middle, there's a neck region N. So I will explain what these are later. But for now, just to see, there are 3 pieces. Where's the algebraic picture? I should have the algebraic picture. Oh, it's all gone. The algebraic picture is here. Algebraically, we see 2 components. Okay. There are 3 pieces. So how this is this collapsing happens? So this collapsing is multi-scale collapsing. So there are 3 spectral points on the unit interval. There's 0, 1, the end points, and the spectral point in the middle called U star. So away from these 3 points, the collapsing is along a smooth fiber bundle. So this, for example, you can consider this thing. So this is a smooth manifold itself. It's also a circle bundle over D. D is this red thing. Okay, this is a circle bundle. So this whole thing, this whole fiber has to collapse to a point, but it's a different scale. So you can see that this D is much bigger than the circle. The circle collapses in a faster rate than the D, the base of the circle fibration. On the left, it's also similar. So, what about these endpoints? These endpoints, this whole thing. So y1 minus, this is part of y1 minus d. This whole thing goes to this point. It's not really I mean, there's a lot of topology here. And there's also a lot of topology here. They also go to just one point. So you see that this is kind of a dichotomy. So most topology are actually concentrated in these ends, but they do not contribute to metric or measure. They all converge to point. And this N is more interesting. This is a neck region. So, and there's all these blue dots, blue crosses. So, if you remember in the beginning when I said that there's an H, maybe I should review this. I should have put the picture also here. So, this is triple intersection Q and F1, F2. So this H blue. So when n equals 2, this H is just a bunch of points. Okay, so these are blue points. So what happens here? So this thing you should think of that there's a singular fiber above this point U star, and it's explicitly determined by the degree of the two polynomials. So this fiber itself is a circle fibration. It's also over D, but this fibration is pinched along this locus H. So it's a singular circle fibration. If you now, I mean, this whole fiber also goes to just this special point. But now, if you choose your base point to be this blue cross, if you rescale suitably, you will see something which is called it's a product of n minus 2 dimensional flat space times top knot. So this is topologically, or even complex geometry, is just C2. So the whole thing as a complex space is just a Cn. There's no algebraic geometry, no interest in algebraic geometry on it. But the metrically, it's quite non-trivial. It's not the flat metric. It's a top knot metric. So I will explain this later. That's the goal for the rest of the talk, is to explain what are these Tianyao metrics, how do we construct this neck region, and what are these top knot metrics. Okay, so let's see. Once again, the picture. So it took us 100 pages to prove this picture. Oh, so there's also this normalized renormalized limit measure. Just forget about this formula, just to scare you. But then the main thing is you can already see from this picture that this measure is something interesting. It's not uniformly distributed. The volume is kind of it's curved, and it has kind of non-smoothness at this point, U star. Yeah. So what are these Tianyao metrics? So these are complete, non-compact Calabi-Yau metrics. So this is I mean, naively you may think that the Yau theorem just extends, but unfortunately, well, fortunately, that's not the case. It's much more interesting in the non-compact case. So this is one setting. You take a Y to be a Farlow manifold, and D to be a smooth anti-canonical divisor with a normal bundle we denote by L. So this is a positive line bundle. And then by adjunction, we know that D is Calabi-Yau. Again, you can write down omega D, capital omega D explicitly, but normally little omega D, you have to rely to Yau theorem, but that's one dimensional lower. So D is one dimension lower than Y. And then when you look at the neighborhood of D, so it's not exactly, but it can approximate by a neighborhood of the zero section in the normal bundle. But this omega D is essentially in the cohomology class, first chain class of L, so it determines a Hermitian metric on the normal bundle. But now on this normal bundle L, if you remove the zero section, so there's a natural holomorphic form. Again, explicitly, just pull back the holomorphic form from D, and then you wedge a fiber, natural fiber wise holomorphic form, meromorphic form on the fibers. It is invariant, and the natural circle action which rotates the fiber. And then there's Calabi ansatz. So this is a formula which is give you a Calabi-Yau metric. This is not a miracle. So what Calabi did is you just look for functions of the form metrics, which is a form dd bar of a function of the norm squared of this S. S is a point on L, and then you solve the equation becomes an ordinary differential equation, and just solve it. You get this. So it's complete as you move towards the zero section. So using this Calabi model at infinity, and then Tian Yau extends Yau's proof to this non-compact setting. So can we solve the equation with where on this non-compact manifold? But you know this is you have something to start with. That something itself is almost Calabi-Yau at infinity. So it's still a lot of technical work, but they constructed a complete Calabi-Yau metric on Y minus D, which is asymptotic to little omega. So a metric is not the metric, because this is something you construct by using this ansatz. It's not natural. It's not clear that this metric is unique on this non-compact. This is always difficult. Thank you. No, sorry. I thank the chair for giving me 10 minutes notice. I still have 10 minutes, so I can still explain. So the metric looks like this. It's just looks like the part on the end of the picture before. So now the construction of the next region, that's really the heart of the work. But the idea is not complicated. So you recall that this D sits inside X0. So on each component, you can apply Tian Yau construction. You get this Tian Yau metric. But now if you look at the nearby XT near D, you can also approximate. This time not by a subset of a line bond, but by a subset of the direct sum of this two line bundles, the y1 component and y2 component. And it's cut out by this equation. So you basically just approximate everything by the restriction on to D. So this looks similar to the equation for xt, except that this is now on this total space of this line bundle over D, and this now admits if you project to D, it's a conic fibration. The projection to this NT, from NT to D is a C star fibration, and it's a singular exactly over this H. There's a natural C star invariant holomorphic form on this NT. Write down explicitly again, and then you can also ask a question whether you can find S1 invariant Calabi-Yau metric on this bundle. This metric, if it exists, it has to be incomplete. So now I first explain the baby case when n equals 2. So here the Calabi-Yau metrics are hyperkiller, so that means SU2 equals SP1. And S1 invariant Calabi-Yau metrics are given by Gibbons-Hawking ansatz. And the interesting thing is that the equation, I said the Calabi-Yau equation is the nonlinear Laplace equation. And now if you look at this case, then it becomes exactly the linear equation. And you can write down explicit solutions. Of course, these are not compact. So away from the fixed point, the metric is given by this part V. So it's you take a domain in the flat R3, and you view this R3 as a complex C, direct sum a real line, x, y, z coordinates are these natural coordinates. So this you take this flat metric, and then you choose a positive harmonic function on this domain. You just you can conform or change the flat metric by V, and then this V is harmonic, so star dV is closed, and with the right comodular condition, it defines a circle bond, and then you choose it determines the connection on the circle bundle. So you get it, and you put the V inverse here. This is this is a Riemannian metric, and the complex structure, the projection to this X to this first C, you can make this holomorphic, and then this becomes a Calabi-Yau metric. So this is away from the fixed point. Near the fixed point, then we need to have singularities for V. And so V is, so if you want, if the space smooth, then this V has to be of this form 1 over 2R plus a smooth function. So the examples is when you choose omega to be the whole R3, and V equals exactly this 1 over 2R, then you get a flat metric on C2. And the projection map is just this product coordinates. And you can deform V by a constant, and that will not change the topology or the complex structure, but it will change the metric. So that's this top knot metric. It's a deformation of the flat metric, and you can add two of these together. You choose different poles. Add together, you form a space where it contains this S2. So you take so these are the 2 pole points. You take this interval, pre-image is a circle generically, and pinch 2 points. You get this non-trivial. So this was discovered much earlier by Calabi and Gucci-Hansen. So now this Calabi model space, this end of the Tianyao space, they are also circle invariant, so they correspond to this function. This case, so you take a flat T2 times a array, and you take V to be the linear function on the ray, then you will get this Calabi model. And then you look at the pictures on the two sides. They are these models. They're both growing towards the interior. So we have to interpolate these two linear functions. And the naive way is to interpolate like this. So that means you will need something which behaves like a linear function on both ends. And then this is just a standard electricity. So you take a electric potential of k points on this product, this is Green's function, and if you average it over the T2 fiber, you will get a Green's function on one-dimensional space, and it's just a piecewise linear function, and you can see that this V will behave like this at infinity, and then you can add the linear functions, and then this will. But you want V to be positive, so this has only positive in a bounded domain, and that's exactly this neck region. And you want this to have two ends to match the two Tianyao metrics. So this is this cousin of the so-called Auguri-Vafa metric, where you take omega to be S1 times R2. So that's important in the work of Gross-Wilson when they study collapsing of Calabi-Yau metrics on elliptic fiber K3 surface. These are local models around a singular I1 fiber. So here, instead of S1 times R2, you take T2 times R. This is once again the picture. So there are difficulties when n is bigger than 2. One is that if you can still do this reduction, but it's done by Matesi and Zarkov, but the equation is still not linear. And the idea is to use adiabatic limits. So when fibers are small, you can use a linear equation as an approximation, but then you have to deal with the nonlinear equation in the end. And instead of Green's function, you study is called Green currents. So this is you take the d times r, and you take h times 0 inside d times r. That's a codimension 3 submanifold. Study this Green currents. It's much more complicated. But also, in order to fit into the algebraic geometric picture, one has to have 3 components. So n it was not seen from the original picture. One has to extract a new component using the algebraic geometry, and this result gives a possible inductive description of the geometry of Calabi-Yau matrix for special class of degenerations. So I have 2 more slides. So this is a conjecture. This is a rough conjecture. It generalizes the conjecture of Gross-Wilson and the Kontsevich-Soiberman in the case of large complex structural limits. So in general, the Gromov-Hausdorff limits of the Calabi-Yau matrix, the differential geometric objects should be related to certain non-Archimedean objects. So there are important progress made by Yang Li and others, which gives us some information about geometry in the generic region and in a more general setting. But again, for certain classes of degenerations. And also, this rescaled Gromov-Hausdorff limits should also be related to the algebra geometric limits itself. It's classical algebra geometric objects. There are progress by Yuji Odaka in the algebra geometric aspect. Okay, I finished here. Thank you.
Yeah, thank you very much. Are there questions?
How really did you use the algebraicity of the Calabi-Yau? I mean, in the sense, you certainly needed the structure of the central fiber of the degeneration, but if everything was actually not algebraic, you could actually give a similar description of the degeneration of the Calabi-Yau matrix?
Yes. So if you don't need to fit into the algebraic geometry, it's actually easier. Just that's in the case when it's baby case when n equals 2. So you just do a gluing construction at the level of matrix. That's actually easier. So you forget about the algebraic geometry. Just say that there are Ricci flat matrix that degenerate this way. Then it's actually easier. So here is a technical part. One of the technical parts is to fit into this into the algebraic geometric family.
So your discussion of when towards the end, when n is greater than 2, you obtain the nonlinear equation generates a Gibbons-Hawking. And what was the statement about that? So can you prove the existence or?
Yeah, we prove the existence of for solutions to that equation, but when the fiber is very small. So you see the right. So that's.
I see. So for example, I wonder if there is even practically, there is a way to do the expansion with respect to the volume, and then keep improving it, and then try to approximate the solutions, and that you can do, I would imagine, practically by solving it.
Yes, so that's an interesting question. So we actually use, the singular perturbation method. Originally, we want to do this expansion, as you said, but actually, that's not the way we did it. But one should believe there should be an expansion. But this expansion will not be uniform. It will be uniform. There are this region, near away from H, it should be uniform, but around H is actually different. Yeah, so it's definitely interesting to understand this this perturbation more explicitly.
I see.
Yeah.
Thank you.
Are there further questions? Yeah, Vivek.
So within algebraic geometry or something like that, if you have some deformation, you wind up at some singular object, you could ask to reverse the process. You could say, okay, for my singular object, what deformations does it have? It is a very well-studied problem. So is there any analog in this world? If I go to this Gromov-Hausdorff limit, maybe I keep along this rescaled one, does the deformation question make sense? Can you ask where could it have come from and so on?
Yeah, that's what they call gluing construction. So you pick objects, you glue them together, you graph them together, and then you perturb to exact solution. So that's exactly how, in differential geometry, how you produce this. But of course, as similar to the previous question, it's much more complicated than you do algebraic geometric deformation theory, where everything is finite dimensional. Here you are working in infinite dimensional objects. So this gluing construction is the main art of many constructions in geometry, in differential geometry. Make sense? But the point is that you have to guess what do you want to do before you start, right? It's not like you just pick the thing is that in algebraic geometry you have this notion of singular objects, where it's very singular, right? They still fit together as one object. But in differential geometry, because of this different scales, they are very different objects. You have to imagine what can you do to put them together. They are not a priori one object. Even before you start.
Okay, are there any further questions? Doesn't seem to be the case, so let us break for coffee and resume at 20 past. Okay, yeah, let me correct the announcement, 30 past, so we have a bit more of time for coffee. It's in the program.
No, I know.
It's okay.
No, it's better. We made a mistake, I think, because it's too short otherwise.
meisten erwartet man ja schlagende Konjunktionen oder mittel flachen Metriken zu arbeiten, die sozusagen String. Ja, gerade sozusagen das zum Beispiel Duality.
Macht das ja sozusagen locker.
I asked for this both, but I think it's only this.
Sì, sì. Tu sai, non... Oh.
Francesco.
Immaginavo. Sapienza. Sapienza. Yeah, yeah. Yes. Yeah, sorry, I didn't even put my name. No, my affiliation.
Okay, so let us continue. I'm very happy to announce our next speaker, Lorenzo Foscolo from Sapienza, and he will talk about hypertoric varieties, W Hilbert schemes, and Coulomb branches.
All right, thank you very much to the organizers for inviting me here. It's my first time at ICTP and first time at one of these math strings events, so I'm very happy to be here and meet you all. So this is what I'm going to talk today is a joint project with Roger Bielaski, and our first interest was sort of try to generalize some constructions and study of non-compact hyperkähler manifolds in dimension 4, which are these decay ALF spaces to higher dimensions. So the sort of full hyperkähler part of the story, unfortunately, is not as satisfying as we were hoping at the beginning. Sort of along the way, we realized that the spaces that we were aiming to study actually have a big overlap with the sort of hyperkähler spaces that arise as Coulomb branches of three-dimensional n=4 Superunion-Mills theories. And therefore, as I mean, the main result that I'll actually going to discuss today is a more sort of explicit geometric realizations of these spaces, which have been defined by Braverman, Finkelberg, and Nakajima, sort of given sort of more geometric realization of the sort of as a holomorphic symplectic sort of spaces. And toward the ends, I'll say what we can say about the hyperkähler metric. So, so recently there's been a sort of a lot of sort of progress by Song and Robin Zhang and collaborators about sort of classifications of four-dimensional non-compact hyperkähler, four real-dimensional non-compact hyperkähler spaces. And sort of because hyperkähler geometry is so special, then I mean, there's sort of some features of these classes of spaces that immediately sort of want to be somehow generalized to higher dimensions. And so this is the start of the story. So starting real four-dimensional hyperkähler spaces of type ALF. So in let's start, there's two infinite classes. The first class is the case of ALF spaces of type AK, or AK minus 1. So of course, it's hyperkähler geometry, so there's lots of structures. And for example, one can start from simply the complex structure. And so in a generic complex structure, an affine AK minus 1 surface is just a hypersurface inside C3 with this coordinate. So X, Y, Z are coordinates in C3, and the lambda I are some fixed complex parameters. So this is a affine hypersurface as sort of the structure of sort of projecting down to Z, gives some sort of C-star holomorphic vibrations. So all the fibers are C-star except over these special points lambda 1 through lambda k, where the fibers develop a node. And sort of there's a sort of one is interested in the hyperkähler metric, then there's sort of this can be constructed also in a fairly explicit way by the Gibbons-Hawking ansatz. So the complex parameters lambda I become sort of points in R3, and the sort of four-manifold, real four-manifold becomes underlying this complex surface, becomes a circle vibration over R3 minus these distinguished points. And then if we want to write the metric, actually there's an additional parameter. There's sort of some scale parameter L, sort of consistent with what Song has also told us, since we're working in non-compact spaces, then just the underlying sort of complex geometric data don't quite say everything. We need some fixing asymptotic geometry, and so this parameter is a real parameter that can be sort of infinity, and then, as you know, if sort of this is sort of measuring the size of this circle at infinity, and if L equals infinity, then we have some ALE metric asymptotic to C2 mod ZK, and if instead L is strictly positive and not infinity, then we have a ALF metric, so a metric that at infinity looks like a Riemannian submersion. The base metric is flat R3, and the fibers are circles of fixed length L, this parameter L. All right, so then there's this other infinite class of four-dimensional ALF hyperkähler manifolds. These are type decay. Again, sort of if we forget everything except complex structure, then sort of generically these are going to be, again, affine and given by sort of the generic sort of equation for an affine decay surface. There's actually, later on it will be relevant, there's a particular subfamily when one of these parameters, lambda I, is set to 0 that sort of is where the equation simplifies. And so again, this is the complex structure side of the story, and if you want to put a hyperkähler matrix now is more complicated because there's no circle action, there's no symmetry, so no Gibbons-Hawking ansatz. And there's been lots of different ways in which these metrics have been constructed, and sort of one that is find particularly inspiring is sort of the following one that goes back to San in the late 90s, and then has been sort of made rigorous in a more mathematical sense recently by Schreers and Singer, and then basically the same idea also what went into an older paper of mine where I was studying sort of metrics on K3 surfaces that collapse to a three-dimensional limit. So it is the following. So first of all, there's some base case that is somehow is very symmetric, and one can prove the existence of this hyperkähler metric just by different methods. So this is the Atiyah-Hitchin metric, so found by Atiyah and Hitchin in the 80s. So so this is this hyperkähler metric on this D0 surface, and sort of at infinity this has a ALF asymptotic geometry that looks like this. So again, we have our circle vibration over R3 with fibers of some fixed length L. This is a circle vibration over an S2 at infinity, so it has a Euler class, a degree, which is -4, and then everything is actually quotiented by an involution that is acting as plus or minus the identity on R3 and as a sort of complex conjugation on the circle fibers. So, and this is this decay sort of type of asymptotic geometry. And sort of this adhesion metric actually is not simply connected, so there's a double cover, which is D1 surface, or actually the special D1 surface where one of these lambda I parameters is set to 0. So these are very symmetric errors, have a rotational symmetry, so one writes down ODEs and solves them essentially explicitly. So we're lucky there. And then to construct a matrix for higher k, at least in a limit where this parameter L is very small, we can do the following. So, or Sen actually suggested us to do the following. So we start with a Gibbons Z2 invariant Gibbons-Hawking metric. So now we have 2k points in R3, put in a Z2 invariant configuration, a parameter L, very, very small. And actually we sort of do a Gibbons-Hawking ansatz not only with these 2k points, but also putting some negative charge, -4 or -2, around the origin, which corresponds to sort of the asymptotics of the Atiyah-Hitchin metric or its double cover. So there's this Gibbons-Hawking metric, so that's determined by a single harmonic function, that is this one. Quotient by Z2 gives us a nice Haber-Kelly metric that is sort of becomes incomplete as we go very near the origin. And as this parameter lambda is very, very small, then the ball that we need to remove to have a well-defined metric becomes smaller and smaller. So what one can do is just glue in sort of everything was chosen so that basically we can cut out a ball and stick in a rescaled copy of this Atiyah-Hitchin metric or its double cover. And one gets a very good approximation to a Haber-Kelly metric and then sort of use analysis to perturb. All right, so this is one way of producing this DK-ALF matrix in a special degenerate, close to a certain special degenerate limit. There are other ways. And in particular, what was sort of inspiration for the latter part of this work comes from sort of realization of this matrix via twistor theory and Nahm's equations due to Dancer, Cherkis and Kapustin, and Cherkis and Hitchin. Okay, so the basic question is that all of this story seems to have very natural generalizations to higher dimensions. And the main reason is that there is a sort of higher dimensional version of the Gibbons-Hawking ansatz, which is this special class of Haber-Kelly metrics that are sometimes called hypertoric metrics or toric Haber-Kelly manifolds. So these are 4n-dimensional Haber-Kelly metrics that have a trilomorphic action of an n-dimensional torus. So again, one can start more of from a sort of complex geometric point of view. So we have a complex n torus, quotient of a complex vector space by some lattice. And then sort of instead of having points in R3, then one needs to fix sort of data that determines certain hyperplanes inside this complex vector space H. So these are special hyperplanes. They can come with some multiplicity. The normals, they must be integer vectors inside this lattice. And then there's a sort of constant parameter or masses lambda I. And then this data on one side lets you define some affine symplectic variety just by taking some holomorphic symplectic quotient of some flat symplectic vector space and this cotangent bundle of this complex torus. So, and again, everything can be done at the level of hyperkähler metrics when where complex masses becomes sort of parameters valued in R3. And then again, before we needed the extra constant parameter L that was determining the asymptotics. Now in higher dimensions, what one needs to fix is essentially a flat metric on this torus. And then the sort of picture is kind of similar to the kind of the cartoon picture of this matrix is similar to what we have in the Gibbons-Hawking ansatz. We have a sort of holomorphic moment map from X down to H star. We have these hyperplanes with normals, these integer vectors alpha I, possibly some multiplicity, and then sort of the picture is that kind of we have some sort of generic C star fibration. So if you are away from these hyperplanes, then the fibers are copies of the torus T. And then if we are at generic points on exactly one of these hyperplanes, then we see something that kind of in transverse direction looks like the real four-dimensional picture that we had before. So one of these AK surfaces. Okay, and right. So then, so this is and the metric again, because it's sort of that's this generalization of the Gibbons-Hawking ansatz. The hyperkähler metric is completely explicit and determined by essentially a single sort of function, or rather matrix-valued function that solves a linear equation. So everything is explicit and completely determined by this combinatorial data that I've given. Okay, so then sort of to generalize kind of the Z2 action that appears in sense picture, then the natural thing is to look at a finite group acting on this complex vector space so that it preserves the lattice, and it's generated by reflections, so that we are going to see the four-dimensional pictures as a generic sort of codimension for pictures. And so this puts you immediately in a situation where you basically have a Weyl group acting on this Lie algebra of this torus and the torus in the standard way. And so you have this configuration of hyperplanes that must be invariant under this action of the Weyl group. Right, and then you assume that this action of the Weyl group actually lifts to an action on the hypertoric variety determined by these hyperplanes. And then you sort of can imagine a cartoon picture like this, where basically you have your sort of hyperplanes determining the hypertoric variety where everything is as before. And then, as in real four dimension, we were adding the origin with some negative multiplicity. Here we can imagine adding this sort of these hyperplanes that are fixed by involutions inside the Weyl group with negative multiplicity -2, -4, sort of meaning that the transverse geometry there is going to be modeled by Atiyah Hitchin or its double cover. And then you quotient everything by this Weyl group, and you get at least some incomplete hyperkähler metric on some large region that corresponds to this sort of cartoon. And a question would be, when and how you fill in this sort of asymptotic hyperkähler geometry with something that is hyperkähler inside. So there's lots of actually known examples of spaces that are going to have this sort of corresponds to these cartoons. So there's many gauge theoretic, sort of classical gauge theoretic moduli spaces. For example, moduli spaces of monopoles on R3. I think this cartoon, for example, should be the modular space of charge two centered charge two monopoles on R3 in the presence of one SO3 monopoles in R3 with one singularity. And so this is one source of examples, and then sort of at some point we realized that actually there's this other big source of examples coming from sort of quantum gauge theories. So these Coulomb branches of three-dimensional quantum gauge theories with n=4 supersymmetries are precisely supposed to be spaces of this sort of type. And sort of why is that? Because sort of if I we have a complex reductive Lie group. Of course, we have its maximal torus and Weil group. And actually, conversely, if we have a torus with this action of the Weil group, then essentially there's a unique complex reductive Lie group determined by this data, except for an ambiguity of SO odd and SP, which causes some complications and which ultimately is related to whether one is allowed to take this multiplicity -2 or -4 here. So, so that's the sort of Lie group, and then of course if we have now a complex representation of the Langland dual to this, then we get immediately a doubly invariant collection of this combinatorial data that we need to produce the doubly invariant hypertoric variety, and where, I mean, all the masses, I guess, I mean, one can choose what they are, but in general, we put them 0. So this gives doubly invariant hypertoric variety, actually a restrictive class of them that we call strongly doubly invariant ones, where basically all these normals alpha I to these hyperplanes are actually doubly invariant. Okay, and then from this data, as you know better than me, then there's a Coulomb branch that one can associate to this data, and this is supposed to be some hyperkähler space, and I guess well, I guess if we think about the metric, then also that there was this extra datum of this basically asymptotic flat metric on the torus that comes in, and that corresponds in the sort of quantum gauge theories to the gauge coupling constants that come in there. Okay, and then of course, not so long ago, Braverman, Finkelberg, and Nakajima have defined these Coulomb branches as holomorphic symplectic, affine holomorphic symplectic variety. I guess the fact that they're symplectic is a very recent result of Bellamy. And right, so then I guess when we realized this, then our questions became sort of, well, can we sort of give a more explicit geometric realization of these spaces, thinking about these sort of more cartoon geometric pictures of what the Haber-Kellin metric should look like, which I think has also appeared in the physics literature, so nothing new there. And then also sort of, I guess, a doubly invariant hypertoric variety is a bit more general than sort of the type of data that one gets from a representation. Okay, so then basically on the holomorphic symplectic side, we were successful, and the constructions that we sort of came up with is inspired by, I think it's chapter 6 of the book by Tia Hitchens on monopoles, where they describe sort of the generic complex structure on the moduli space of monopoles in terms of transverse Hilbert scheme, and then sort of an extension of that to the DK ALF spaces given by Cherkis and Hitchin. So in high dimensions, what we can do is the following. So we start with a doubly invariant affine hypertoric variety X. there's this holomorphic symplectic moment map, which is W equivariant. And then you basically want to get some open subset of a particular Hilbert scheme on X. And that's our candidate. So we start with the Hilbert scheme of exactly cardinality of W point in X. So this is basically some open then subset of where we have exactly cardinality of W distinct points on X, and then points are allowed to coalesce, and we remember directions, so they come together. So because we've, so inside here, there's the sort of fixed, there's a fixed locus of the W action on here. That is going to be lots of irreducible components. There's a union of irreducible components that is the sort of, usually denoted with this W Hilbert scheme. So these are sort of zero-dimensional subschemes where this quotient space is sort of the regular, is a representation of W that is the regular representation. As I said, this is in general made up of various irreducible components. There's a distinguished one, which is the closure of the locus of regular orbit. Okay, so that's one thing that we can do. And then because we have this W equivariant map, we can actually have a well-defined open subset inside here, which is this transverse Hilbert scheme. So here we're basically looking at zero-dimensional, double-invariant zero-dimensional subschemes in here, such that their image under mu is a scheme theoretic isomorphism. So kind of in a cartoonish way, this means that if the image of points are coming together in the base, then they also must come together in the fiber, and they're not allowed to come together in a fiber in directions that are tangent to the fiber. So this is this transverse Hilbert scheme, and it has a well-defined induced morphism down to this quotient of the sort of Cartan, the algebra mod, or dual of the Cartan, if one is careful, modulo this Weil group. Okay. So one can do this, and this has this is a natural holomorphic symplectic structure on its regular part, and is an affine variety if we start with an affine variety, as we are here, and it's actually regular if the original X is also regular. Okay, so why does this look like to be the right space to look at? Because of sort of concrete examples. So first of all, we can get all of our decay surfaces can be realized in this way. So for example, so if I start with C times C star and sort of the kind of this projection mu is just a projection to the first factor, Z2 action is plus or minus the identity here and passing to the inverse on the C star factor. So I mean, calculating actually, if one has equations for an affine variety, then it's not so complicated actually calculating the equations for these for the transverse Hilbert scheme. So actually one can do is a very explicit computation and realize that this spaces is exactly basically the double cover, I mean as a complex, so of course we're just looking at the complex structure, so it's the double cover of the Atiyah-Hitchin manifold, and more in generally if we start with a Z2 invariant, a 2k-1 surface, then we get this special subfamily of dk plus 1 surface. So this is good, but we're missing something, and to recover basically the Atiyah-Hitchin itself and the whole family of decay surface, then there's a trick. We first need to go to something higher dimensional. So now we take C times C star twice, and the Z2 action is just the swapping of the two factors and projection down to C2. And so we take this Z2 invariant transverse Hilbert scheme. So this gives us this, I mean, this is smooth. This is a smooth holomorphic symplectic variety. And it has a Hamiltonian C-star action, so we can take the quotient, and that's exactly this D0 ALF space. Okay, and then you can do the same if you now sort of want to produce any decay surface. You can also do, starting with some hypertoric variety of some higher dimensions, sort of depicted by something like this. Okay, so this is the 4-dimensional examples, and then in higher dimensions, the sort of kind of higher rank analog of Atiyah-Hitchin matrix in a way. So if you start with the cotangent bundle of a torus and take this transverse invariant Hilbert scheme, then sort of you get a space that can be identified with the universal centralizer of this Lie group that one gets associated to T and W. So these are pairs of an element S in the so-called regular Zlotowicz slice to the Lie algebra. So, so this is basically a slice to the adjoint action on the set of regular element in the Lie algebra. And then G is an element in the group that is sort of fixing, centralizing this element S. Okay, so this is basically going to be this C-star fibration, and then that degenerates along these hyperplanes in the H-star that corresponds to fixed points of the involution generated by the coroots. Okay, and again, if one sort of was this problem that not everything was there, and but again, you can sort of go to higher dimensions and then take a C-star quotient and to get everything. Okay, and then sort of another simple example is where you just take C to the 2n, that's your hypertoric variety with the symmetric group acting here, and so this can be explicitly realized by this sort of matricial kind of explicit affine variety inside inside this space. Okay, so and basically if your hypertoric variety is smooth, then basically all the local picture of your hypertoric variety is basically is products of these two cases. Okay, that's why these are some key sort of examples. Okay, so then sort of what we managed to prove with Roger is that, so we start with one of these strongly double invariant affine hypertoric variety, where the strongly means that these normals to the, it's not only these hyperplanes that are the collection of hyperplanes that are invariant under the Weil group, but also the normals that can be chosen in a double invariant way. And then sort of basically then, well, we can prove that this transverse Hilbert scheme is a normal affine symplectic variety with a flat morphism down to this H star mod W. Again, the fact that this is symplectic is the same result of Bellamy that I was saying before. And then basically we can compare this transverse Hilbert scheme with the definition of the Coulomb branch given by Braverman, Finkelberg, and Nakajima, and prove that they are the same. So when the hypertoric variety is obtained from the combinatorial data of a representation of the Langlands-Joule group, then actually the Coulomb branch, as defined by Braverman, Finkelberg, and Nakajima, is indeed one of these transverse Hilbert scheme or some torus quotient of them, which is only necessary when we work with this sort of special, the odd SO groups. Right, so actually this comparison is sort of well, sort of the Braverman, Finkelberg, and Nakajima in their work, they have a recognition sort of theorem for their Coulomb branches, meaning that they have a theorem that says if you find a normal, basically if you find a space that has this property in part 1, which is a normal affine variety with some flat morphism down to H star mod W, then this is going to check that the two spaces agree. It's enough to check what happens along sort of points corresponding to these generic points of one of these hyperplanes. So the idea is sort of that everything else is high codimension, and because of normality, sort of the isomorphism over this locus is going to extend everywhere. So then basically all of the work went here, and since neither me nor Roger are algebraic geometry, this took quite a bit of time and effort. So I think I'll maybe skip some of sketch of what goes in there, and instead make some remark and then say what we can say about the hyperkähn metrics actually. Okay, so the first remark is that, okay, what I hinted at before, so there's slightly more transverse invariant Hilbert scheme than polarized representations. It's more like the double invariant hypertoric variety corresponds to an element of the representation ring of this, I mean, the combinatorial data corresponds to a representation ring, an element of the representation ring of the Langland dual group, but perhaps this, in physics, is already clear that sort of the Coulomb branches actually exist also for virtual representations. And another thing is that, so if you think just of the underlying geometric space, there's, of course, lots of different ways in which it can be realized as a Coulomb branch already in real dimension for sort of rank 1, real dimension 4. So, so for example, I guess that makes a bit more complicated understanding. For example, if one is interested in understanding all the possible deformations or resolutions of these spaces, then sort of the fact that some are transparent in one description as a Coulomb branch, but not others, might complicate things. So there's okay, so that's one remark. The other remark is that it looks like sort of this transverse Hilbert scheme construction really is some uniform sort of description of spaces that sort of fit in this type of cartoon picture that I explained at the beginning. For example, so here is probably another interesting example, some Hilbert scheme of points on a AK-1 surface, and similar story for the decay ones. So, okay, so if you start with the, so I did here the case of 2 points. So if we start, so if you start with kind of, okay, so first of all, you start with the symmetric product of the AK surface. That can indeed be realized as a one of these transverse Hilbert scheme for a hypertoric variety that is essentially obtained this way. So one takes the product of all the AK-1 surface. So in this case, there's 2. So we have this sort of Gibbons-Hawking pictures along the 2 axes, and then you throw in diagonals with multiplicity 2 and symmetry. So if you take the transverse Hilbert scheme of this, you get precisely this symmetric product. And then sort of what you can do, you can simply just introduce non-zero masses and separate this multiplicity 2 diagonal into 2 ones, and sort of this gives you a deformation of this space, and sort of I guess the feeling is that sort of the transverse Hilbert scheme of this is going to be a deformation, complex structure deformation of the Hilbert schemes of the AK-1 surface, where somehow, so the Hilbert scheme in general, one takes this, so this multiplicity to plane hyperplane corresponds to C2 mod Z2 singularities, and so to go to the Hilbert scheme, one does a sort of resolutions of that C2 mod Z2, transverse resolution of that C2 mod Z2 singularity, and here instead we're doing a complex structure smoothing. Okay, and then final remark is that actually also Coulomb branches for arbitrary quaternionic representation also fit into this framework, because if one starts with a quaternionic representation, then one gets, basically considering half of the weights of the representation, one gets a hypertoric variety, a collection of combinatorial data that determine hyperplanes. The hyperplanes are sort of invariants as a set. The normals are not necessarily doubly invariant. So there is a hypertoric variety, and then there's a further obstruction to say whether the W action on the base actually lifts to the hypertoric variety. So in this context, it comes naturally in terms of some extension class of a short of exact sequence of groups, and through sort of work of Braverman, Finkelberg, and collaborators, and Telemans, who have given definitions of these Coulomb branches in the general case, actually one can check that this vanishing condition is exactly the same as the anomaly conditions that appears in physics. What's a bit less satisfying in this case is that the case of groups SO and SP is a bit sort of the solutions that we find of going to something higher dimensioning and then quotienting in Barra-Torres sort of works most of the time, but not quite always. So it's a bit more unsatisfying. Okay, so right, that's right. So let me just just make some comments about the hyperkähler metrics. So if one is interested just in producing sort of complete, smooth hyperkähler metrics, then probably the thing that one should do, and I'm hoping to be doing soon, is, well, once you have an underlying holomorphic symplectic manifold, well, because of these sort of cartoon pictures, you can write down some approximate Kähler-Ricci flat metric at infinity for these metrics. So then what you would like to do, maybe sort of solve a complex Monge-Ampère equation with these asymptotics, find a Kähler-Ricci flat metric on this holomorphic symplectic manifold, and then use the existence of the holomorphic symplectic manifold and basically maximum principle and curvature identities to to show that this Kähler-Ricci flat metric is actually hyperkähler. So here there's recently, or very, very recently, there's been sort of technical work that allows to do this. So there's Hein as sort of giving a very general framework to solve these complex Monge-Ampère equations on non-compact manifolds. Song explained how this is non-trivial, and it's important to understand asymptotics at infinity. I guess there's been a whole revolution in understanding sort of Kähler-Ricci flat metrics in higher dimensions that are on manifold as simple as C3. So for example, here there's work of Yang Li that has produced Calabi-Yau metrics on C3 that are sort of kind of at infinity as an asymptotic geometry that's very much adapted to the historic picture of C3 that appears also in the talk of appeared in the talk of Vivek. So this trivalent graph, and then basically away from the graph we have flat T2 tori that of fixed sort of with a fixed flux metric at infinity, and then this vibration degenerate along this trivalent graph. And then sort of to deal, I mean, if you want to do this in every dimension, then there's some complicated sort of combinatorial analytic things that you need to keep track of because of these multiple intersections of these hyperplanes as you go off to infinity, but there's been some recent work of Kottke and Rochon from the sort of more kind of analytic type thing to understand sort of how one can do analysis on this sort of asymptotics. So it seems there's everything that's needed. So, but so this would just work on sort of smooth or mildly singular cases, I guess. If you want to do everything, or if you hope that you can maybe bypass some hard analysis, then we entertain the idea, again inspired by what happens in real dimension 4, that maybe there's some uniform description of this hyperkähler metric using twistor theory and Numb's equations, and we got somewhere, but not quite to where we wanted. So, so in twistor theory, the idea is that basically the hyperkähler metric is encoded into two types of things. So first of all, a twistor space, which is a fibration over CP1. The fibers are basically copies of your manifold with the holomorphic symplectic structure that corresponds to, we're looking for a hyperkähler space, so there's a hypercomplex structure, so every point on CP1 corresponds to a choice of complex structure with a holomorphic symplectic form on the fiber. And there's some real structure as well, and sort of, so that's one piece, and that's easy to construct, or at least it's easy to construct a singular model for the twistor space of our conjectural hyperkähler metric on this transverse Hilbert scheme, because one can take the sort of Hilbert scheme of the hypertoric variety. This is some explicit space. This parameter L actually enters inside the Hilbert scheme. It has basically this, now this holomorphic symplectic moment map becomes a projection down to the total space of this, what's sometimes called the mini-twistor space, tensored with this Cartan, the algebra. And then basically you can do this transverse Hilbert scheme construction on all the fibers of this twistor space, and you get something. But what's complicated to get the hyperkähler metrics, one needs to produce sort of twistor lines, so sections of the twistor projection with prescribed normal bundle, and sort of the twistor theorem tells you that on each connected component of this modular space of twistor lines, there's going to be a hyperkähler metric. There's a further complication, is that what the theorem tells you is this hyperkähler metric is a pseudo hyperkähler metric, so one really should think about producing sort of component of the space of twistor line that gives a hyperkähler, sort of Euclidean hyperkähler metric. And then also, basically, from this picture is essentially impossible to understand questions like completeness of the metric and asymptotics. But so then sort of we started trying to describe how we can understand twistor lines in this new twistor space. And this is what gets us to Numb's equation by a series of sort of connections that are sort of more or less well known. So first of all, you can think twistor. So twistor lines, first of all, can be understood in this new twistor space. Can be understood as W invariant curves inside the twistor space of the hypertoric variety itself. And these twistor lines must be sort of have a projection down to this twistor space that is W invariant flat degree cardinality W over P1. And conversely, if you have a curve like this in here, then lifting it up corresponds to trivializing a certain principal torus bundle over the curve, being W equivalently trivial. So this, right, so then basically the data of a W invariant curve in here, together with this W equivariantly trivial torus bundle, you think of it as cameral data for co-Higgs bundles on P1 with, so this is a principal horomorphic bundle for the non-abelian group, and phi is just a O2 twisted section of the endomorphism, of the adjoint bundle. Okay, and then once you have this, actually you have a whole one-parameter family of this cameral data just by basically tensoring your torus bundle with this particular one that determines by this choice L. And it is understood that sort of if you have a one-parameter family like this, this corresponds to basically trivializing all of these principal G bundles. That gives you a solutions to NUM's equations. And and then when sort of this bundle for a specific value of t becomes trivial, that means that the solutions to NUM's equation is developing a regular NUM pole. So the simplest type of point singularities for NUM's equations determined by some SL2 triple in the Lie algebra, and here we take the principal. So this is enough, for example, to identify the kind of the vacuum Coulomb branch, if you want, with a modular space of NUM's equations. I guess it was known, but this is saying that really the Hyperkähler metric is this natural one. And in high dimensions, basically the picture that we got to is a picture where you have NUM's equations on an interval with two regular poles at the end and then some jump in the middle. And this jump in the middle is determined by some sort of additional Hyperkähler space constructed from the data of the hypertoric variety, a sort of, Hyperkähler space, conjectural Hyperkähler space. So there's a twistor space and sort of, but one needs to find again twistor lines and everything for this one. So it seems like it's a circle. The only sort of advantage is that this new space that you put in the middle is basically this product of cotangent bundle of Lie groups, which by work of Cronheimer, we know how to put Hyperkähler structures on them, and then spaces that have a sort of more of an algebraic twistor space. And therefore one can hope that maybe there's a realization of Hyperkähler's quotient or some manifold of a Hyperkähler quotient. Okay, sorry, I'll stop.
Yeah, thank you very much. Are there questions?
I have a couple. Could you go back to the page where your theorem was?
Yeah.
Yeah, so I was a bit confused about something. Maybe you can clarify. I was surprised you have to do anything at all to prove 2, because your description seems very similar to the usual description of abelianization for Coulomb branches. So what is the difference, and why doesn't that give you an immediate proof of 2?
Well, but sure, that's I'm not sure whether abelianization, what does this give you? It gives you this cartoon picture of these, basically the what would corresponds to a hypertoric variety where you put these negative hyperplanes. So I'm not sure, it might be just a lack of my own understanding, but I'm not sure if that, the procedure that then starts with that to give you the actual Coulomb branch, I'm not sure if it's a rigorous procedure.
Maybe I'll show you some references. You could tell me what to say.
Okay.
But my other question was, how much more general is your construction than Coulomb branches?
Well, as I said, it's just replacing. Instead of having, because when you take these weights of a representation, right? You have the rules that then sort of, if you take the W orbit of the highest weight, then you need to fill in certain ways what's inside, right? So.
But is it important for you that W is a reflection group associated to a Lie group?
Oh, yeah. That comes just by thinking of, I take this asymptotic picture given by this incomplete sort of hypertoric metric, and I want some, I mean, if you start saying, okay, I want a group generated by reflection because the local model is going to be one of these decay surfaces, and then you want to act on a torus, so basically then you're immediately to a Weil group. There's no other, yeah, that's.
Okay, thanks.
Yes, okay, are there more questions?
Thanks for the nice talk, Lorenzo. Could you comment on the possibility of using, sort of, these results and previous results for non-compact hyperkähler manifolds? Complete metrics on non-compact hyperkähler manifolds as ingredients in gluing, potential gluing constructions in the compact case?
Oh, well, I mean, sort of, kind of it's clear that, sort of, for example, if you start with, so I was saying, so there's this picture that is basically Sang's picture of families of hyperkähler metrics on K3 that are sort of collapsed to a 3 torus mod Z2 with these configurations of points that is Z2 invariant. So then, for example, if you start taking the Hilbert schemes of points on those K3s and you think about what is happening to the hyperkähler metrics on those Hilbert schemes as the K3 degenerates, then you will have a picture where basically these non-compact spaces come in as, that I was talking about, come in as rescale limits of these high-dimensional hyperkähler manifolds, right? So conversely, then one could imagine sort of if we start with some sort of basically periodize the base and then sort of understand what is the combinatorics of these sort of periodized hyperplanes that would allow you to sort of imagine some metric build-up of sort of pieces that looks like these non-compact building blocks that but I don't have except for situations where I know that, kind of the Hilbert scheme or the Kummer type constructions where you see very clearly what's this picture of these degenerations in high dimensions then.
Okay, there's, yes.
Thanks. So perhaps you said it and I missed it, but so let's say I give you a gauge a 3D unequal for gauge theory. So in your main theorem, you said that there exists a hypertoric variety that is the starting point of your construction.
Yeah.
But how explicit is that?
Oh, this is the way that that you know very well. You just
okay. That's the one.
Yeah, yeah, yeah. Except for this little slight complication if you start with the Langland group, if there are SP factors, then then if you want to reproduce this by the Strasser-Hilbert scheme, then you need to go to something high dimensional first. So basically lifting the representation to SPC and then taking a sister quotient. But it's essentially the same as, that you know how to produce, yeah.
Okay, are there any further questions? do not see any. Okay, before we thank Lorenzo again, let me ask you to stay a little bit after we thanked him again for the conference photo, which is, or you make a...
Yeah, sorry.
Okay. So let's then just thank Lorenzo again, and then there will be an announcement about...
Just outside the building, in front of the flower bed. So I think we can slowly move in that direction. Yeah. No, Exactly.
Funziona e poi
because there is the conclusion after.
Maybe yes, I will sit there. I'll sit there. Tomasz in the middle and we'll just ask questions.
Vedi, luce verde e accesa. Ok? Non ok?
No, no, ma non c'è problema. No, volevo dirti, allora, vabbè, 50 minuti, domande, quelle che ci sono le facciamo andare, tanto è, poi magari prendiamo 5-10 minuti di pausa tra il talk e la gente si deve andare in bagno, erano lamentati l'altra volta che era subito dopo. Una conferenza, vedrai. Domenica. Non c'è il talk lunedì. Rama ha detto che viene, non so se viene qualcuno. Ah, ok, non lo sapevo. La settimana, magari riesco a vedere un po' la città, stavolta volevo fare un po' di... Torno sabato. Cioè, un attimo meglio, però non... No, vabbè, un pochino meglio. Ho provato in effetti. Penso di sì. No, non ho guardato. No, parlo del lavoro con Godet che dovrebbe uscire questo mese, il prossimo mese. Che vabbè, è un po' tangenziale con la conferenza. No, perché siccome c'era anche Brennan, non sapevo se lui voleva parlare dell'1. Allora, fare due articoli su due lavori sull'1 era un po' ridicolo. Poi in realtà neanche lui parla di sto 1 in realtà. Cioè, vabbè, parla di qualcos'altro. Ho anche fatto un lavoro io. No, no, non sempre elegante, è una persona normale, diciamo.
Please take a seat.
So welcome everybody to this afternoon session. We will have a talk and then a number of gong show. So the talk is by Edward Witten from the Institute of Advanced Study in Princeton, as you all know, and is going to talk about instantons and the large n=4 algebra. Please, Ed.
Well, thank you to the organizers and to the ICTP for hosting this meeting and for the invitation to give the talk. So, two of the most familiar and most studied examples of ADS-CFT duality involve type 2b superstrings on ADS 3 times S3 times either T4 or K3, which appear because they're the two compact hyperkähler manifolds that are possible. And the duals are two-dimensional sigma models in which the target space is the moduli space of instantons on either K3 or T4, as the case may be. These models have large supersymmetry algebras, n=4 supersymmetry, and those have been important in understanding them. But there's a superficially similar example that's been much less understood, even though it has an even larger supersymmetry algebra. This is type 2b superstring theory, where you replace T4 or K3 by S3 times S1. So it's also a classical solution of supergravity, and there's a fairly extensive literature on it. I think I'm pressing the wrong button. Okay. There's a fairly extensive literature, of which these are some of the more relevant papers. So the first two papers on that list showed by analyzing string theory and supergravity that the superconformal symmetry of type 2b in this space-time is not the usual so-called small n=4 algebra. When people talk about n=4 supersymmetry, normally they're referring to what is sometimes called the small n=4 algebra. The large one is sufficiently rare that people normally take for granted that they're talking about the small one. But as I'll explain, as well as the usual n=4 supersymmetry algebra, which here I'll call the small one, there's a slightly more unusual large one. It doesn't come up too often, but these authors showed that type 2b superstring theory on this spacetime has a symmetry under the large n=4 algebra, compared to the small one that you get in more familiar models, such as a sigma model with a hyperkähler target, or type 2b on either one of these spacetimes. Now, though the dual of type 2b in the spacetime I'm interested in today has been unclear, a proposal in the literature has been that the dual is a sigma model with target the instanton moduli space on S3 times S1, which I'll call a curly M in this lecture. Curly M will always be the instanton moduli space on this space. The original motivation was largely that the same statement is true in the other examples, that the dual of this or this is instanton moduli space on T4 or K3, so why shouldn't the dual of this one be instanton moduli space here? The goal of today's lecture is to test this conjecture by showing that this sigma model does have the large n=4 superconformal symmetry. There are previous partial results of which these are the most notable papers. So, but before I get into that, I want to explain why you might think that the dual might be a sigma model with this target space. So you can give a kind of heuristic explanation by a brain construction, which I want to explain. First of all, the supergravity solution on ADS 3 times S3 times S3 times a circle has a non-zero 3-form flux on each of the first three factors, ADS3, S3, and S3. By S-duality, the 3-form can be of Riemann or Neveu-Schwarz type or a mixture, but it's the same in all three factors. I'll call the 3-form G. It's conventional to call these fluxes Q1, Q5, and Q5 prime, as they're believed to reflect, in some sense, the numbers of branes of indicated kinds. So Q5 and Q5 prime, which are fluxes on compact manifolds, are integers in supergravity. Q1 is really a field strength rather than a flux, and it's not really an integer from the point of view of supergravity. In the derivation, we'll start with type 2b on R2 times a circle times the deformed conifold T star S3 times R. So T star S3 is a non-compact Calabi-Yau manifold, the deformed conifold, and we put Q5 prime units of G-flux on the 3 sphere that's the center of the deformed conifold. So an important point, detail, is that T star S3 with flux is a supersymmetric configuration that actually has been studied a lot. Then we're going to wrap Q5 D5 branes on R2 times a circle times S3. The S3 is again at the center of T star S3, and all this is localized at a point in R. R was the last factor of the spacetime, this one. Now, when you wrap Q5 D5 branes, you get a UQ5 gauge theory. So there's a UQ5 gauge theory in 6 dimensions on this manifold, R2 times a circle times S3. But this UQ5 gauge theory has a coupling that depends on the G-flux, and that coupling can be written this way. It's a 3-dimensional Chern-Simons coupling wedged with the field strength, the 3-form field strength. That term is a standard part of the D-brane effective action, but it's often written by integration by parts. So if G is D of C2, by integration by parts, what I've written is the same as the trace of F wedge F, wedge C2. So some of you will be more familiar with it in that version. Finally, we introduce Q1 D1 branes, which are wrapped on, well, the R2 that's going to be the non-compact spacetime, and then times some points in S1 times S3. But as usual for the D1, D5 system, the D1 branes will dissolve into instantons in the UQ5 gauge theory. So at low energies, we're going to get a sigma model on R2, whose target space will be the moduli space M of instantons on S3 times S1. But it won't be the perhaps most obvious sigma model. Okay, sorry. Everything said on this page up to here would be the same if we were on T4 or K3 instead of S3 times S1. The difference is that because of this Chern-Simons interaction, the sigma model will have a topologically non-trivial B field at a level Q5 prime. By the level, I just mean the integer coefficient of a topologically non-trivial B field. So this interaction in 6 dimensions, First of all, the Chern-Simons interaction is well-defined mod 2 pi. And it's parity odd, and it only involves first derivatives of the field. So when we reduce to a sigma model, it's going to be a B field, but it's going to be a topologically non-trivial B field because of the topologically interesting nature of the Chern-Simons coupling. So Chern-Simons is not, under big gauge transformations, it's not well-defined as a 3-form, but its periods jump by integer multiples of 2 pi. So with Q5 prime an integer, this interaction is going to give a properly quantized but topologically non-trivial B field on the sigma model target space, which will be the instanton moduli space. So what we get then will be a sigma model in which the target space is the moduli space of UQ5 instantons with instanton number Q1, and with this B field at level Q5 prime. What does this have to do with ADS3 times S3 times S3 times S1? To answer this, we just follow Maldasena's original derivation in the T4 and K3 cases. So we replace the Q5 D5 we replace the Q5 D5 branes by the near horizon geometry they create. That was the basic idea of Maldasena's derivation. So what is the near horizon geometry they create? Well, first of all, they're wrapped on a 6 manifold. And the normal bundle to the 6 manifold is a 4-dimensional, of course. Locally, it's just R4. And the near horizon geometry of the D5 branes, you throw away the origin in the R4. Well, 3 things happen, roughly. The normal bundle is rank 4, which locally means it's just a copy of R4. In the near horizon geometry, you throw away the 0 section of the normal bundle. The radial direction of the normal bundle combines with R2 to make a copy of ADS3. That happens exactly the same way it happens for T4 and K3. So if you're not familiar with it, you'd find exactly the same story in Montesano's original paper. And the angular directions in the normal bundle remain as another copy of S3. So after doing all this, the near horizon geometry is ADS3 times S3 times S3 times a circle. So roughly, just imitating Montesano's derivation, we learned that the D5 branes can be described by the gauge theory I described, which leads to a sigma model whose target space is the moduli space with that non-trivial B field. But on the other hand, the geometry produced by the same branes, or the near horizon geometry they produce, is the one that we're trying to find the dual of. So that gives at least a heuristic explanation that the dual of type 2B on ADS3 times S3 times S3 times a circle should be that particular sigma model. So hopefully that motivates the idea that the string theory on this given space-time is dual to the sigma model with target curly M, and we've determined also the dictionary. Q5 maps to the rank of the UQ5 gauge group. Q1 maps to the instanton number, and Q5 prime is the level of a topologically non-trivial B field. Now, I'd next like to motivate the idea that strings in this space-time and also the sigma model with target M both have this slightly unusual large n=4 superconformal algebra. But since it's a bit exotic, I don't want to assume you all know what it is. So I'm going to first explain what is the large n=4 algebra. And by way of explaining that, I'll start by reminding us what's the small one. And then we'll discuss how the large one is different. So I'll describe the small one with the example of a free hypermultiplet. You can think of a free hypermultiplet as parameterizing the hyperkähler manifold R4 with its flat metric. So the free hypermultiplet has 4 free scalar fields, phi, and they transform under an SO4 rotation symmetry. But SO4 is SU2 times SU2 divided by Z2. So to keep track of the two SU2s, I've given phi 2 SU2 indices, an index A for one SU2, A dot for the other. Phi obeys a reality condition that I won't stress. And then we have also 4 fermions. For brevity, I only will consider the positive chirality fermions, let's say. And they also transform onto 2 different SU2s. So I've given them an A dot index and an X. So there are several SU2 symmetries, one acting on each type of index. The chiral algebra is generated by 4 supercurrents. And to make the supercurrents, you contract one index of phi, of d phi, with one index of psi. So that contraction is only invariant under a diagonal copy of 2 of the SU2s. But you're left over with 4 supercurrents that transform under an SU2 that acts only on phi and an SU2 that acts only on x. So shouldn't be a big surprise. If there are 4 supercurrents with n=4, it can potentially have SO4 symmetry or SU2 times SU2. The only point I've made is that one SU2 acts only on the bosons, one acts only on the fermions. Now, for the one that acts only on the fermions, we could write chiral currents. A bilinear of the fermions is a current that generates that SU2. And what I've written here are actually the generators of the small n=4 algebra. Or more precisely, these and the stress tensor generate the small n=4 algebra. So the algebra with these generators, first of all, is the small n=4 algebra. But second, it has an SU2 group of outer automorphisms that acts on the index A of GAX. It doesn't act on the currents. And you see, that comes from a symmetry that acts only on the bosons. Now, the free hypermultiplet does not have holomorphic or chiral currents that generate this SU2 symmetry, because currents that would rotate the scalar field phi are not holomorphic. That might sound like a fussy detail, but it's crucial. So the small n=4 algebra is the chiral algebra of the free hypermultiplet. it has these generators, and it has an outer automorphism group, SU2, of symmetries. Now, in most theories you meet in real life with the small n equals 4 algebra, the outer automorphism group is not a symmetry. So for the free hypermultiplet, it is a symmetry. But if you take a sigma model with target T4 or K3 as examples, these are typical examples in which the outer automorphism group is not realized as a symmetry. It's an outer automorphism of the algebra, but the outer automorphism does not act on the theory, on these particular theories, which have the small n equals 4 algebra. It's a little tricky to find a theory that does have the large n equals 4 algebra, meaning that the algebra is generated by the 4 supercurrents G, 2 different SU2 current algebras, and some additional chiral fields that, roughly speaking, are forced on us by the Jacobi identity. Now, I don't want to try to justify in detail the claim that string theory or supergravity in this spacetime has large n equals 4 symmetry. Well, I'll just note that it has, well, I'll partly motivate it. You see, it has 4 SU2 symmetries. S3 is the same as SU2. And SU2 has 2 SU2 symmetries, one acting on the left and one acting on the right. And so therefore, S3 times S3 has 4 SU2 symmetries. That's the right number for 2 copies of the large n equals 4 algebra. Because the large n equals 4 algebra has 2 SU2s, but you're going to get 2 copies of the large n equals 4 algebra, one for left movers, one for right movers in the sigma model, so you really need 4 SU2 symmetries, which is how many we have. Notice that on ADS3 times S3 times T4 or K3, we only would have had 2 SU2 symmetries, which would have only been enough for the small n equals 4 algebra. Actually, I said I wasn't going to say more about justifying the large one, but just for fun, let's note that potentially we have symmetries exchanging the 2 S3s, and also we have a reflection symmetry between left and right. So we have symmetries that pretty much guarantee that you couldn't possibly get the small one without getting the big one. Because if it were true that some of the SU2s were in the chiral algebras of holomorphic or anti-holomorphic degrees of freedom, the others would have to be also in view of the symmetries. Now, how do you get a sigma model with large n equals 4 symmetry? The simplest example is a model with target space S3 times S1. And that's convenient because we're going to be talking about S3 times S1, and it's not a coincidence. So in this context, when we say S3 is the target, we really mean SU2 at level K. In other words, an SU2 WCW model at level K. In our application, K will be Q5 prime. So you see, if you took a sigma model of a target S3 times S1 without the B field, it wouldn't be conformally invariant at all. A sigma model with target S3 is asymptotically free. It would become massive in the infrared rather than conformally invariant. The Western-Mean interaction at level K stabilizes it at a radius squared, I guess that's proportional to K, and you get a nice superconformal field theory, but the a nice conformal field theory, but the superconformal version of it, if you also add a circle, has this large n equals 4 algebra. So I'm going to explain the special geometry of M equals, I'll often refer to S3 times S1 as M, straight M, not curly M. I'll explain the special geometry of M that leads to large n equals 4 symmetry. Then I'll explain how the corresponding instant non-moduli space curly M has the same kind of geometry and leads to a sigma model with the same large n equals 4 symmetry. So M itself is the target space that has large n equals 4 symmetry, and its instant non-moduli space has the same geometry and the same kind of symmetry. That's an example of many results showing that if a 4-manifold M has some kind of geometry associated with some supersymmetry algebra, then the corresponding instant non-moduli space curly M has the same kind of geometry, leading to the same supersymmetry algebra. So here are the most famous cases. If M is scalar or hypercalar, then curly M is also scalar or hypercalar. These are associated to 2-2 or 4-4 supersymmetry without a B field. It's also true, although not exactly exploited in supersymmetry, that if M is merely complex, not necessarily scalar, then curly M is complex. Cases relevant for today I've listed here. So first of all, and I've also, I've indicated references. So one is that if M is a Hermitian manifold, which means a complex manifold with a Hermitian metric, then curly M has a naturally induced Hermitian structure. That is, curly M will also get a complex structure with a Hermitian metric. If M is generalized scalar, which means the geometry leading to 2-2 supersymmetry with a B field, then so is curly M. If M has the geometry that leads to 0-4 supersymmetry with a B field, with the small n equals 4 algebra, then so is curly M. A result that I think is apparently not in the literature, but is an easy consequence of comparing what these two authors did, is that if M is generalized hyperkähler, which leads to 4-4 supersymmetry with a B field and the small n equals 4 algebra, then so is curly M. And finally, if M also has the extra symmetries that lead to large n equals 4 algebra, then so does curly M. So in all these cases, whatever geometry M has, curly M has the same geometry. So I'm going to try to first explain.
So if M is almost complex, then curly M is not in general almost complex. Is it, from this point of view, can we see what goes wrong with that?
Oh, Greg, I'm only discussing conditions related to supersymmetry, because the physical idea, I think, is that
so that's the point. Almost complex is not a condition that
for
leads to supersymmetry.
Right. Yes.
Discuss the large n equals 4, you are not saying that this would be corresponding or associated to the two copies of D21 alpha, right?
Well, D21 alpha is a finite dimensional group, right?
Right, but that would be the corresponding ADS3, S3 cross S3 cross S1.
Yeah, okay. Well, this would take us a little bit farther afield to explain that properly. But the question is about, I've emphasized the chiral algebra. Then you can look for a finite dimensional group in the chiral algebra. And the group is the super isometry group of ADS 3 times S3 times S1, S3 times S1. So I think I'm presenting it logically without getting to that point. We can discuss it in more detail at the end, perhaps. Okay. Anyway, I've listed here various conditions for all kinds of supersymmetries. And they all have the property that if M has that type of geometry that leads to that kind of supersymmetry, if M has the target space of a sigma model would have a certain kind of supersymmetry, then curly M does the same thing. But so now the rest of my talk will be in two parts. First, I'll explain the relevant geometry of S3 times S1. And then I'll explain how to prove that curly M has the same geometry. So S3 times S1 is sometimes called a Hopf surface, and it's often given as the simplest example of a compact complex manifold that's not scalar. To explain its special properties, start with R4 with the scale invariant metric. So I take the standard metric, dx squared, in the numerator, but I've divided by x squared to make it scale invariant under rescaling of x. Since it is scale invariant, we can divide by x going to e to the tx for any positive t. If I divide by that operation, the quotient is compact. And you can see the quotient will just be S3 times S1. Because, well, okay. I should say you throw away the origin, and then you divide R4 minus the origin by this. So the distance from the origin is a positive real number, but when you divide by rescaling the distance by e to the t, that means you can, up to rescaling, it's between 1 and e to the t, so it lives in a compact space, a circle. 1 is equivalent to e to the t, so you've compactified it to a circle. and the angles are a copy of S3. So the quotient is S3 times S1. And it's S3 times S1 with a metric which I can write this way. The unit metric on a three-sphere of radius, round metric on a three-sphere of radius 1, and a flat metric on a circle of circumference t. Well, how do we see that S3 times S1 is a complex manifold? Right. We just combine the x's in pairs into complex variables. So if z1 is x1 plus ix2 and z2 is x3 plus ix4, then we can parameterize S3 times S1 by complex variables z1 and z2, and the equivalence relation rescales them by e to the t, and that's a holomorphic operation. So the quotient is a complex manifold with a complex structure that I'll call I. In this complex structure, it's easy to see that the metric of S3 times S1 is Hermitian, which means simply that it's of type 1,1, but it isn't Kähler. It can't be Kähler because the second Betti number of S3 times S1 is 0. So S3 times S1 can't have a Kähler metric, since the Kähler form on a compact Kähler manifold is always non-trivial in the second homology. So, okay, I described one complex structure, but there really are a lot of them. And the reason is that I broke the symmetry in picking this complex structure. So the first factor of S3 times S1 is SU2. S3 is SU2, so it has SU2 symmetry on left and right. I'll call them SU2 left and SU2 right. The complex structure that I called I is invariant under one of them, say SU2 left, but SU2 right rotates I into two other complex structures, which we could call J and K. They satisfy a quaternion algebra. I squared equals J squared equals K squared equals -1, and IJ is equal to K, equal to minus JI. So I said we rotate I into the other two, but really you could more symmetrically say that there's a two-sphere worth of complex structures. I rotates into a whole two-sphere of complex structures which are linear combinations of I, J, and K. So this structure makes S3 times S1 what's called a hypercomplex manifold. The metric of S3 times S1, since it was Hermitian for I, and is invariant under SU2 left times SU2 right, is actually Hermitian for all of I, J, and K. So S3 times S1 is hyper-Hermitian. Yes. The answer question is, did I take the standard metric? And yes. Let's remember just where we got it. So I took this metric on R4 minus the origin. Then I divided by this operation. And we got the standard metric, except S1 had circumference T, capital T. So since it was a standard metric, it was invariant under rotations of either S3 or S1. And in particular, because it's invariant under rotations of S3, the complex structure I called I isn't unique. It's rotated into a whole IJK family. Now, we can get a second family by exchanging SU2 left with SU2 right. We could do that by just doing a reflection on S3. But a reflection on S3 isn't quite what we want to do because it's not a symmetry of the instanton equation that we eventually will be studying. What we want to do is a joint reflection of both factors of S3 times S1. That preserves the orientation, so it is a symmetry of the instanton equation. It reverses the orientation of S3, so it exchanges SU2 left with SU2 right. And it maps IJK to another hypercomplex structure, I prime J prime K prime. One is invariant under SU2 left, the other is invariant under SU2 right. So, as I just said, essentially, since this joint reflection row exchanges SU2 left and SU2 right, so IJK was invariant under SU2 left and rotated by SU2 right, and it's the other way around for I prime J prime K prime. The metric of S3 times S1 was invariant under the joint reflection, so it's Hermitian also for this new family of complex structures. Now, since M equals S3 times S1, which is the same as SU2 times U1, it's a group manifold. So it has two natural flat connections, which I'll call nabla and nabla prime. Nabla is defined by saying that left invariant 1 forms on M are covariantly constant, and nabla prime is defined by saying that right invariant 1 forms are covariantly constant. So I, j, and k are covariantly constant for nabla, and I prime, j prime, k prime are covariantly constant for nabla prime. Both connections are metric compatible, and they have completely antisymmetric torsion, which is given up to sign by a closed 3-form H, which in the sigma model is interpreted as the field strength H equals dB of the sigma model B field. So if D is the Riemannian connection, the definition of, well, I just want to make clear the statement that the connection is metric compatible but with completely antisymmetric torsion. So H is the field strength. If we were studying a sigma model whose target is S3 times S1. Actually, let me see what I've said next on the slide. Okay. So H is the H which is relevant here is the Riemannian volume form of S3 as I've written here. So if D3 omega is the Riemannian volume form of S3, S3 had this round metric of radius 1, so it has a Riemannian volume form once you pick its orientation. And the H, which is relevant here, is the Riemannian volume form of the 3-sphere. And then, well, nabla is defined by the formula I've written, and nabla prime is the same thing, but with H replaced by minus H. So here the torsion is completely antisymmetric because H is a 3-form. But just antisymmetry in the first two indices would be the definition of a connection being metric compatible. So here we have two connections that are both metric compatible with completely antisymmetric and closed torsion. And it's also true that the two connections have equal and opposite torsion. One has torsion H, one has torsion minus H. That's clear because the two connections are exchanged by rho, the joint reflection, and the volume form of the 3-sphere is odd under that joint reflection. Now, in general, on a complex manifold M with metric G and complex structure I, you can define a Hermitian form that I've called omega I. So you take the metric times the complex structure, and you get a Hermitian form. But here, because there's so many complex structures, I'm calling it omega I rather than just omega. By definition, M is scalar if d omega is 0 and not otherwise. In our case, the condition that the complex structure is covariantly constant for this connection that I've defined here, this one, and that the torsion of the connection is a 3-form, implies a formula for H in terms of omega I. H is minus I times d of omega I. And with a little computation on the 3-sphere, you can check that that's true in this example. Thus, if and only if M is not scalar, which happens for S3 times S1, the B field curvature H is non-zero. So this funny formula I've written here is probably not very familiar, but it appears in the literature on n equals 2 supersymmetry. If you want a sigma model to have n equals 2 supersymmetry with a B field, to get n equals 2 supersymmetry, you need a complex structure and a Hermitian metric. If it's going to have a non-flat B field, it will not be Kähler, and its failure to be Kähler is going to be related to the curvature of the B field by this formula. So this is this expression here that I expect most of you might not be familiar with is the condition that you get for n equals 2 supersymmetry of a sigma model with a B field. However, if we want n equals 4 supersymmetry, what happens to us? Well, then we're worried about not one complex structure I, but 3 complex structures I, J, and K. If there had been no B field, we would have asked that the corresponding Kähler forms were all closed, and we would get a hyperkähler structure. With the B field, each of them is going to satisfy this equation. But there's only one B field of the sigma model, so they have to all satisfy the same equation with the same H. So the same formula must hold for J and K with the same H if we're going to get a sigma model with n equals 4 supersymmetry. So we need this to hold. And then the same sort of identity must hold for I prime, J prime, and K prime, as they all have torsion minus H. So what I've explained up to this point is the geometry that leads to small n equals 4 supersymmetry with a B field. You need the 2 hypercomplex structures I, J, K, and I prime, J prime, K prime. The metric is Hermitian for all of them. None of the Hermitian forms are closed, and their failure to be closed is related to the curvature of the B field, but in such a way that this identity has to hold, and its counterpart for I prime, J prime, K prime also has to hold. So that's this. Okay. That's the story for n equals 4 supersymmetry with the B field, as described by Gates, Hall, and Rocek in the 80s, and is eventually reinterpreted by Hitchin and Gualtieri in terms of generalized hyperkähler geometry. But what if we want large n equals 4 supersymmetry? Well, if we want large n equals 4 supersymmetry, we need to take into account the rotation symmetry of the circle. So the second factor, S1 of S3 times S1, has itself a rotation group generated by this vector field that I'll call V, which is d by d tau. And the properties of V that lead to large n equals 4 supersymmetry beyond what we already said for the small one are the following. First, V is covariantly constant for both nabla and nabla prime. And second, the vector fields IV, JV, and KV generate SU2 right, while I prime V, J prime V, and K prime V generate SU2 left. By IV, I, as a complex structure, is a map from the tangent space to itself. V is a vector field, so IV is another vector field, which is an SU2 generator. Similarly for JV, KV, and so on in my statements. So the properties of S3 times S1 that I've just described lead to large n equals 4 supersymmetry for the sigma model with target S3 times S1, or for any target, really. What I've described are the properties that you need in order to get large n equals 4 supersymmetry in a sigma model. So to show that the sigma model with target the instant non-moduli space M likewise has 2 copies of the large n equals 4 algebra, we have to show that it has the same properties. And that's what the rest of the talk will consist of, but I'll stop for a moment for questions on this, if there are any.
If you could go back to the metric, the distance form of the regular metric, ds squared.
The metric was this, right?
Yes. Yes, indeed. Yeah. There was an omega, d omega squared. I couldn't see from where it appeared.
Well, dx squared in polar coordinates is d r squared plus r squared d omega squared. D omega squared was what appears in this formula. And then what I did was I defined tau by r equals e to the tau. And then dx squared over x squared is this over r squared. So then I have d omega squared plus d tau squared.
Thank you, sir.
Where r is e to the tau. I hope this wasn't in your way when I was writing on the blackboard. Any other questions? Okay. Okay, so for the remaining time, I'm going to explain why the instanton moduli space has the same kind of geometry. Well, we get a little bit for free. For free, we have an orientation-preserving symmetry group because isometries of S3 times S1 will obviously act on the instanton moduli space. So for free, we get the symmetry group SU2 times SU2 times U1, which is indeed part of the large n equals 4 algebra. But we only get for free the global part. We don't get for free holomorphic currents generating a current algebra. And it's also obvious that the joint reflection of the two factors will act. And that will mean that whatever we prove for I, j, and k, we'll have a counterpart for I prime, j prime, and k prime. But the rest is up to us. We're on our own. So first, let's construct a Hermitian structure on the moduli space. On the space curly A of all connections on some smooth G bundle over S3 times S1, there's a natural Hermitian metric. Now, if we think of our four manifold M, which could be S3 times S1, but will be a little more general, as a complex manifold with complex structure I, then on the space of all connections, we have a corresponding complex structure curly I by saying that if we make a Hodge decomposition of A relative to I, then curly I acts as I on A01 and minus I on A10. That makes the space of all connections a Hermitian manifold. So that's the 0th step. We want to turn the metric and complex structure on A into one on the instanton moduli space. Now, the first problem we face is that the metric is not invariant under a gauge transformation, where sigma is the generator of a gauge transformation. In other words, delta A is a variation of A, but we want to think of delta A as being equivalent to delta A minus something induced by a gauge transformation. But this formula for delta A squared is certainly not invariant under that. So to get so our metric does not descend automatically from A to a metric on the space of connections mod gauge transformations, where G is the group of gauge transformations. To get a metric on A mod G, we need to pick a gauge condition on variations of the gauge connection. Any gauge condition will give a metric, but different gauge conditions lead to different metrics. Whatever metric we get on A mod G can be restricted to M, the subspace of A mod G corresponding to solutions of the instanton equation, to get a metric on M. So the main step in getting a metric on M is to get a metric on A mod G. For example, an obvious gauge condition is Lorentz gauge. In the case of T4 or K3, it works well. But Lubke and Telemann showed that we should use a different gauge condition in the case of a non-Kähler manifold M. The reason is we will also want to define a complex structure on M, and we want the metric on M to be Hermitian for the complex structure. That means that what I called curly I should act on the tangent space to M at a generic point in M. Well, the tangent space is defined by the linearized instanton equation together with whatever gauge condition we pick. The linearized instanton equation is that, you see, the linearized curvature is the exterior derivative of the variation of the connection. So dA of delta A is a succinct way to write the variation of the f mu nu is d mu delta A nu minus d nu delta A mu. But an abbreviated version of that is d sub A of delta A. But then the instanton equation only sets the self-dual part of that to 0, which I've indicated by the superscript plus. If we make a Hodge decomposition relative to I, the linearized instanton equation says that the 2, 0 and 0, 2 part vanish, and also the 1, 1 part vanishes. The 1, 1 part can be written as omega I wedged with dA of delta A. The equations in the first line are invariant under the action of the almost complex structure on the space of connections. But the one in the second line is not. So the only hope is to choose the gauge condition to be whatever the last equation transforms into under delta A going to I delta A. If we do that, then we'll have a set of equations that is invariant under the action of I. So the gauge condition has to be this one. With this gauge condition, we get an action of the almost complex structure on the tangent space to M at any point. It manifestly satisfies I squared equals -1 because the underlying complex structure, which was I with a different font, squared to -1 on M. So it defines an almost complex structure on curly M. And the metric defined using the gauge condition is Hermitian because the metric is invariant under the action of curly I, which is equivalent to saying that it's of type 1, 1. We also want to know that curly I is integrable. That has a short proof by comparing the gauge condition and the 1, 1 part of the equation to the action of complexified gauge transformations. But I'm going to skip explaining that proof. So at this stage, we know that if M is a Hermitian manifold with metric G and complex structure I, then curly M is Hermitian. Curly M, if we define it with this gauge condition, is Hermitian with complex structure curly I. So we've shown that if M has the condition for 0,2 supersymmetry, then so does curly M. Well, what if M has a hypercomplex structure IJK with G being Hermitian for each? Well, then for each of I, J, and K, we define corresponding complex structures, curly I, curly J, and curly K, on the space of connections. But it looks like we're going to be in trouble because I explained that there was a unique gauge condition we had to use in order for the metric to end up being Hermitian. And for each of I, J, and K, we're going to need to use different gauge conditions, leading generically to different metrics on M. However, something happens that's highly not obvious, as shown by Hitchin. Despite appearances, the gauge condition depends only on H, the B-field curvature of the sigma model with target M, which I, J, and K have in common, as I explained before, not on I. So rather miraculously, this gauge condition can be written this way. It's a highly non-obvious identity, I would say. But anyway, it's true. So given that it's true, you learn that the moduli space, this was kind of the main observation in the paper of Moraro and Verbitsky. Given that it's true, the Lebke-Tellman construction can be carried out for each of I, J, and K using the same metric on the moduli space. And it's manifest that I, J, and K obey the quaternion relations since they were obeyed on the space of all connections. And in the construction, we just restrict from the tangent space to the space of all connections to the tangent space to M. So at this point, we know that M is hypercomplex, hyperhermitian. Okay. We need one more thing to finish this proof that M has the structure of 0,4 supersymmetry. We need to know that I, J, and K are compatible with the same torsion, which should be a closed three-form H hat on M. So Lebke and Tellman had actually computed the exterior derivative of the Hermitian form on moduli space. And Moraro and Verbitsky showed that their formula implies the identity we want. To say that curly I, curly J, and curly K are all compatible with the same three form. So denoting the common value of all three is H hat. This is the identity we need to ensure that I, J, and K all have the same torsion H hat. And H hat should therefore be the curvature of the B field on the instanton moduli space. So this would give us 0,4 supersymmetry with the small n equals 4 algebra. What if, as in the case of S3 times S1, M has a second hypercomplex structure with torsion minus H. The computations of Lebesgue and Telemann show that H hat is homogeneous and linear in H, so it's odd under H going to minus H. So if I prime, J prime, K prime have torsion minus H, then their cousins on the moduli space have torsion minus H hat. So this may seem to show that curly M is generalized hyperkähler leading to small 4-4 supersymmetry, but there's a snag. There's a snag because for I, J, and K, we had to use this gauge condition, which miraculously was the same for all of I, J, and K. But for I prime, J prime, and K prime, we have to use a gauge condition that's actually different. And it seems, therefore, that we're going to get 0-4 supersymmetry. So generically, a different gauge condition will lead to a different metric on M. So if that's the state of affairs, one metric on M will lead to small 0-4 supersymmetry, and the other will lead to small 4-0 supersymmetry, left and right-handed in the targets in the world, well, on the boundary of ADS3, actually. But another small miracle intervenes, as shown by Hitchin, even though generically different gauge conditions lead to different metrics. In this particular case, the two different gauge conditions lead to the same metric on curly M. So at this point, that's the last ingredient we need to get small 4-4 supersymmetry. To extend to large 4-4 supersymmetry, the main thing we need to do is to show that if we lift the vector field V on M that generates the rotation of a circle to a killing vector field V hat on M, we need to know that V hat is covariantly constant for the two flat connections associated to the two hypercomplex structures. Now, the flat connections are defined this way. I'll just put hats on everything to tell us that we're on the moduli space rather than on the original manifold. And, well, we basically have the Lebesgue-Telemann formula for H hat. Well, originally it was a formula for D omega, but reinterpreted as a formula for H hat. And a computation using essentially their Lebesgue-Telemann formulas, you can prove that this is true, although I won't try to explain the details of that computation today. So that's as much as I'll tell you about why the instanton moduli space has the same geometry as the underlying 4 manifold. Thank you.
Thank you. Questions? Yes, one there.
I have, two questions. First, what's the geometric interpretation of this modified gauge condition? The Lorentz condition is the usual metric definition. If I want to define a distance between two gauge orbits, I just find two closest points.
Yes. Let me explain to everybody what you've just said. We have two gauge orbits, and you want to know how far apart they are. And one way to decide how far apart are two orbits is take the closest possible distance between 2 points on the two orbits. And that's what the Landau gauge condition does. So the Landau gauge condition is intuitively natural. And also it gives the best answer for hyperkähler manifolds and in lots of other applications of instantons. The Lebesgue-Telemann gauge condition isn't so intuitively natural. I can't justify it except that it's the gauge condition that makes everything work in this problem.
I had a second question.
Yes, go ahead.
So in your original notation, it seemed like you had a symmetry, Q5 going to Q5, exchanging Q5 and Q5 prime. So there is a system of intersecting D5 branes, and there is a modular space of crossed instantons, which seem to be related to it.
Yes. So Nikita is asking the following question. We had the system that was parameterized by integers Q1, Q5, and Q5 prime. And the underlying problem in ADS3 times S3 times S3 times a circle has an obvious symmetry between Q5 and Q5 prime, which has been completely lost in this presentation. I can only tell you one special case. In my lecture, Q1 is positive. But in the underlying problem, it makes sense for Q1 to be 0. And Modesena, unfortunately, I've forgotten which Modesena paper it is. Modesena, and I apologize to his co-author for forgetting right now, showed that if Q1 is 0, there is a symmetry between Q5 and, Then, in my lecture, it was R2 times a circle, but it could have been any 3 manifold times S3. they considered this setup, but with Q1 equals 0, and showed that the exchange of Q5 and so Q5 became the rank of the gauge group. Q5 prime was the level of a Chern-Simons coupling, and then they showed that the symmetry between the two was level rank duality of the Chern-Simons theory at low energies. Okay, I should explain the following. All this only holds in the low energy limit. So in the brane derivation, we didn't have the large n equals 4 algebra except when we take the near horizon limit. And in the sigma model, it's like the WZW model. There's a special metric which is super conformally invariant and all that, but a generic one isn't. So, when I was motivating the brane construction, we started with a large S3 compared to the flux in order to justify the discussion. So we were actually far away from the conformally invariant metric. We have to flow in the infrared. I've answered the question as much as I can, so let's move on to other questions.
So if you lift these instantons from S3 times S1 back to C2, will there be sort of dilatation in periodic instantons?
Yes, dilatation invariant.
Okay. And could one sort of make a variant of the ADHM construction which would build them? Something with infinity many?
That's an excellent question. The question was, is there a version of the ADHM construction for instantons on S3 times S1? That would be nice. I don't know a version of the ADHM construction with a B field, but I can't say there isn't one. It would be great if there is. Maybe there is. The actual ADHM starting point involved twistor space. There's certainly a twistor space here because it's hypercomplex. I have no idea. Good question. Greg?
So the second Hitchin miracle was pretty shocking. So the two gauge conditions with H and minus H lead to the same metric.
Yes.
Is there some intuitive way to see why that's true?
No, but it's a rather short
shock.
calculation. I agree with you that it's shocking, and I'm glad you say so because I consider it shocking, but when I prepared the lecture, I had trouble seeing in the available time how I'd be able to make people shocked, but at least one person was shocked. But although it's shocking, it's a surprisingly short calculation if you look at Hitchin's proof. The other one, that the gauge condition, that the gauge condition, well, that this gauge condition is actually independent of I is also pretty strange. If you look at Hitchin's proof, it's again short, but to a physicist, rather bizarre looking. Yes?
Very nice talk. I'm not very familiar with the instantons on S3 times S1, but is there a relation with symmetric products, the moduli space?
No, the moduli space is not a symmetric product.
Only for very special ones it is.
Oh, sorry.
Like rank 1 and
one of the papers I mentioned by Eberhard et al. Gives evidence that for Q5 equals 1,
right.
the dual is a sigma model of a symmetric product. And that's the case, the gauge group is U1, and it's credible that the moduli space should be regarded as a symmetric
So in that case, probably there's a simple proof also for showing that it has a large n equals 4 algebra just by usual orbifold construction.
Yes. Well, it's manifest. That was part of the motivation for the symmetric product. Since S3 times S1 has the large n equals 4 algebra, so does the symmetric product.
Right. So if you go to the Coulomb branch, I mean, isn't there a way to put them together? In other words, just piecing together UN as U1 to the n and putting each one U1 would be n equals to 4 large algebra. So bringing them together, would there not be a way to do it that way, to show it's large n equals 4?
Maybe.
Is there any other understanding of the instant moduli space similar to symmetric product for general case?
Well, there's very little literature on it that I know about. And no. The only simplification I know about, Brahm and Hurtubise showed that it's elliptically fibered. Not elliptically fibered, sorry. S3 times S1 itself is elliptically fibered. That's a classical fact. And using that, you can show that the instanton moduli space, it's algebraically completely integrable. It's fibered by complex tori. That's the only... Any simplified property, well, first of all, there's very little literature on it, but secondly, any simplifying property that's known follows from that.
Just want to comment on that exchange with Kumran. So one of the main points of the paper I wrote with Gukov, Martinick, and, oh God, Strominger, was that we argued that the dual cannot be a symmetric product. So we constructed indices and we looked at singleton theories, and we argued that it was probably not a symmetric product. So I would be doubly shocked. I've already been shocked a few times, but I would be doubly shocked if the moduli space of UQ was a symmetric product.
Well, in any case, it's not, so you don't have to worry about that one.
Can you, I think you said it's at some moment in this discussion, this large n equals 4 forced you to be not Kähler.
Yes.
Is that true in general?
Well, it's true in general for a compact manifold. Because to get large n equals 4, you need a hypercomplex manifold with an SU2 symmetry that rotates the three complex structures. But a compact hyperkähler manifold can't have such a symmetry. More generally, a compact Einstein manifold can't. And hyperkähler manifolds are Einstein.
Hi. So presumably the S dual here, S dual of this from the supergravity point of view will work as in the same way if you have NS fibrons.
Yes.
So is it in the same moduli space as the sigma model? Is it somewhere in the same modular space of this sigma model?
Is what somewhere?
The S dual version of this.
Well, Greg and others in their paper claim that there aren't really any non-trivial dualities of this moduli space, apart from obvious ones. You can realize the moduli space with D5 branes or NS5 branes in the string theory, but you can't interpolate it in the moduli space between them, I don't think. There aren't different weakly, the moduli space is actually sorry, I didn't explain it in the talk, but a small bit of evidence for the duality between ADS 3 times S3 times S3 times S1 and this instanton moduli space is that they both have precisely two moduli. One is the radius of the circle, and the other is a theta angle. There only are those two moduli. And there are some obvious reflections. There's a parity symmetry, I guess, but I think that's the only, I hope I'm not forgetting something. I think that's the only duality symmetry.
So is there any gauge holonomy along the circle?
Is there any what?
Gauge holonomy along the circle.
Gauge anomaly?
Holonomy. Wilson loop along the circle.
Well, you could consider Wilson operators around the circle. You probably can consider supersymmetric Wilson operators around the circle. I don't have any useful comments at the moment, though. I see a question by Lawrence.
I just want to comment on Greg's comment, if that's okay. Because there has been a lot of confusion in the literature about the BPS spectrum on this background. And part of the argument that Greg and others gave in their paper, that there cannot possibly be a symmetric product dual to this background, was by comparing the BPS spectrum that was computed on the bulk side in supergravity and in the symmetric product. In the symmetric product, the BPS spectrum that you get doesn't seem to match with the supergravity, but that was based on an earlier computation where the BPS spectrum was based on a guess. And that was later repeated, that computation, and it was actually shown that the BPS spectrum in supergravity is different than what was originally thought. So I think that at least if you compute the BPS spectrum in the symmetric product of S3 times S1, it does match with the supergravity BPS spectrum. And yeah, we can also discuss indices if you want.
Well, since the question has more or less come up, I'm going to tell you how to prove that the moduli space isn't a symmetric product for no added cost. So here's the 3-sphere, and here's a vector field in the 3-sphere. You look at its fixed points on the moduli space and on the symmetric product. On the moduli space, Graham and Hurtubise describe the fixed point set of this vector field, and it has many components as they analyzed. You can work out the fixed point set on the symmetric product, and you'll quickly see that it's connected. So the two spaces are different, for what it's worth.
Okay, if there are no more... Okay, the very last question.
Sorry. There are a very rich classes of BPS operators in the string theory sites in ADS3, S3, S3, S1,
yes.
like Wilson lines, BPS. Yes. You expect there are some operators in corresponds with this class of operators in a string theory site, or not?
So I hope so. That's an excellent question. So the question was the following. In ADS 3 times S3 times S3 times S1, you could, with various branes and so on, and the boundary perhaps, define all kinds of supersymmetric probes. The question, I think, is what do they mean in terms of the instanton moduli space? I'm sure some are easier to understand than others, because one of the S3s is hidden in this description, and the other is manifest. But I think it's a good question.
Okay, I think we can stop here and thank Ed again. So I was instructed to give a 5-minute break, and then we meet again for the gong show.
Usano il microfono questo.
Ah, ok. Devo accendere questo.
Bagno anch'io.
Allungare dopo il coffee break. Sono problemi. No, ti sto dicendo puoi fare, tu sei il chairman, quindi puoi fare solo e te pare. Sì. Io sono un nazista. Sì, diciamo se fanno 10 minuti c'è una domanda e basta. Sì, lo dirò all'inizio. Only one question is admitted. Dipende, se finiscono 8 minuti possono farne 2. Cioè, possono fare 10, ognuno ci ha allocato 10 minuti. Poi però quando si finisce poi c'è un altro workshop. Ho fatto anche io fotografie, tutte fotografie oggi. Ecco, insomma, solo, e le presentazioni tanto sono una dopo l'altra. È un unico file.
Allora qualcuno mette quello solo o mette...
Quindi, ok.
No, no,
ok,
bisogna
non devo... Ok. No, si sente solo così, ok.
Okay, I think we should start.
Okay, give me a minute.
Yes, I will explain a few things.
Non deve rientrare un po' di gente? O... No, vabbè, non aspettiamo.
Allora, quindi appunto i microfoni sono questi due, quindi non stare troppo lontana.
Ah, ok.
Con questo vai avanti e indietro, e se lo tieni premuto...
Ah, posso contare.
8 minuti.
Comincio adesso? Sì, ma dico, non deve entrare più... Oh, vabbè, ok, uguale.
Okay, we can start the gong show session. So let me remind you, each speaker has 10 minutes, including questions. So whether there can be question or not depends on the speaker. And yeah, 10 all included. So, and okay, that's it. So we start with Marina Moletti, please.
Okay. Hello, everyone. First of all, I thank the organizers for giving me the opportunity of presenting my work, which is done in collaboration with Roberto Valandro and Andres Colinucci. So today I will talk about Calabi-Yau threefold plots obtained as quiver varieties from monopole deformations. So the starting point is type 2A string theory on trivially fibered AD surfaces. That is type 2A string theory on a background geometry that is given by flat space-time times an AD orbifold singularity of type G, where G is one of the AD families. Okay. So, so the complex deformations of the X2 surface, so of the AD singularities, are encoded in the background profile of a complex scalar field that transforms in the adjoint of the Lie algebra G, which belongs to the six-dimensional effective field theory that develops at the singularity. And what we want to do is to consider background profiles for this phi field that depend on a coordinate W that parameterizes a complex plane transverse to the AD singularity. So to generate a threefold geometry that is basically a fibration over C, of a family of deformed AD singularities. And notably, the resolution pattern of X3 is completely specified by the profile that we assign to phi. So what we ask is, our aim is basically to recover the structure of the geometry X3 from the moduli space of a D-brane probe, which in our case will be a D2 brane. And since the world volume EFT of D2 that probes an AD singularity is known to be an n=4 supersymmetric 3D theory with a quiver that is nothing but the dinking, a fine dinking quiver of the a fine dinking diagram, of the Lie algebra. We show that it's possible to obtain an effective description of a D2, of the theory on a D2 that probes the geometry, the threefold geometry X3, by adding to the theory on the trivial fibration an n=2 preserving deformation that affects the superpotential of the originally n=4 supersymmetric theory. So the structure of this deformation is schematically represented by a trace of a product of two matrices. The first one, phi, is nothing but the profile of the phi field that we have introduced in the beginning, now expressed in terms of the chirals of the vector multiplets in the theory, times a G moment map that repackages the Coulomb branch data of the theory, so both local data like the Coulomb branch chirals and non-local excitation like monopole operators. So once we integrate out the massive degrees of freedom, we obtain an effective theory and an effective superpotential whose F-terms reproduce the defining equation in C4 of the geometry that we wanted to probe. So it must be mentioned that analogous results have been obtained in the past, but though with completely different approaches by Witten and Klebanov for the conical case, and by Kachazov, Vafa, and Katz, or Gubser, Nekrasov, and Shatashvili. So an example is an example of simple flop geometry, which is basically our focus. So that is a geometry where you can only blow up a single P1, is a non-trivial vibration, basically a monodromic vibration of an A3 singularity over C, which from the point of view of the D2 brane is obtained by deforming the theory of an A3, and the deformation, as you can see, involves only the degrees of freedom of the leftmost and rightmost nodes. And in particular, the deformation involves the monopole operators associated to the two nodes, which are can be treated according to a technique that has been discussed in the literature. So to obtain an effective theory in the IR that is characterized by a conical shaped quiver with fields that corresponds to the invariant invariants under the two nodes that have been integrated out. And the effective potential that we obtain gives access to an equation that precisely reproduces the defining equation of the geometry in terms of the Coulomb branch invariant of the gauge invariance of the theory. So another relevant example in this case of flop of length 2 is a Brown-Wilms Drinfeld, which is a non-trivial vibration of deformed D4 surfaces over C, described by this equation. And this is analogously obtained by turning on some monopole deformations for the 3 non-exceptional nodes. And this, after integrating out all the massive excitations, gives rise to an effective theory described by this quiver, where the only degrees of freedom appearing are, again, invariants under the gauge groups associated to these nodes, to the red nodes. And the effective superpotential that we have not fully written here reproduces the singularity that we wanted to describe. So to conclude, basically what we do is to provide a simple recipe to extract the n equal 2 superpotential over a large class of non-toric Calabi-Yau threefolds. We propose a physical explanation for a non-commutative geometry algorithm that derives the quiver and the from the non-affine and the affine linking diagram of the starting ADE algebra. And our final aim is to apply our technique to simple flops of any length, that is also E6, E7, and E8 families. Thanks for your attention.
Thanks, Marina. Any question or comments? Yes.
The black hole that you worked on, which mechanism such a black hole comes from? We know, is it same as the gravitational collapse black hole?
Sorry, I cannot hear.
Black hole that you mentioned.
The black hole?
That comes from the potential that you have shown.
I'm not talking about black hole, sorry.
Okay, thank you, sorry.
Sorry.
Any other questions? Okay, if not, let's thank Marina again. Next speaker, which, yes, thanks.
Stay a bit close
Oh,
so
okay.
they can hear you
Thank
better.
Okay, the next speaker is Kuan Yu Hao. Please go ahead.
Thank you so much for the opportunity to speak here, and I also want to thank the organizers. So I'm going to describe a joint work in progress with Andy Nitsky on the abelianization of Versaro conformal blocks at c equals 1. So as we are familiar with, the Versaro blocks are the building blocks of the 2D CFTs. They are solutions to the word identities. In this talk, I will only focus on the chiral part, and for simplicities, I will mainly focus on the Riemann surfaces without punctures. Let me first give a quick review of the definition. So a Versaro block is a system of correlation functions where the insertions are the stress energy tensor. So the insertion number can be arbitrary non-negative integer. We require that the correlators should be holomorphic away from the diagonal, which I mean pi equals pj. And at the diagonal, the singularity structure should be controlled by the TTOPE. And as usual, under the change of coordinates, T should transform in this particular way. So Versaro blocks are very important and interesting, but they are also hard to compute. And the main goal of my talk today is to describe a new way to construct the Versaro conformal blocks at the particular central charge c equals 1. So to be more specific, what we do is to construct a non-abelianization map, this FW, and here this conf means the space of conformal blocks. So FW is a map from the space of Heisenberg conformal blocks over C tilde to the space of Versaro blocks over C. So this subscription W means a spectral network, which is originally defined in the work by JMN. And actually, the main new idea in our paper is to use the spectral network in this non-abelianization construction. And we should understand that the non-abelianization map is to simplify the computation of the more complicated Versaro blocks to the calculations of the abelian objects, the Heisenberg blocks. And we call it abelian because, first of all, naively, the Heisenberg algebra has another name, which is this F and U1 vertex algebra. And also, we know that the Heisenberg algebra is the vertex algebra behind the free boson theory. So in that sense, it's much simpler. And to construct this non-abelianization map, we will need to require that this Riemann surface, the tilde for the Heisenberg side, to be a branched double cover of the Riemann surface C. And here is how it's going to be presented. So on the base, we have a curve representing the Riemann surface C. And on the top, the two curves are the two sheets of C tilde. Because it is branched, so we will have a branch point, which is denoted by the orange cross, and it corresponds to where the two sheets of C tilde collide. So now let me start constructing this non-abelianization map. So in the definition, we said that those correlators should have insertions, which are the generator of the vertex algebra. So I should first tell you a dictionary for the generators. And here's what we do. So if we want to insert a TP on the base, we will need to use both of the insertions of J, which is the generator of the Heisenberg algebra, at the two pre-images. And we need to take this particular combination of the terms. We can check that by this dictionary, we can indeed get the correct OPE if we are away from the branch point. But now you might have a question, which is, it seems that using this dictionary, we could have already written down some non-abelianization map. Why do we even need to use the spectral network? The reason is that if we use this dictionary directly, without any spectral network, the image of this naive non-abelianization map will not be the space of Versaro conformal blocks over C. There will be some unwanted insertions where there is a primary field with weight 1/16 at each branch point. But this map is not what we want. We don't want these extra insertions. We still want a map to the space of vacuum Versaro blocks. And actually, the main new idea in our work is to use spectral network to cancel those extra singularities at the branch points. And here, let me remind you quickly what is a spectral network. So for the purpose of this talk, we can simply understand it as a union of contours, which are those GIs, and they come with a label ij, which denotes the two sheets of C tilde. And we require that at each branch point, there will be 3 contours ending at it at an angle 2 pi over 3. And what I mean by using the spectral network is that we are inserting an operator, EW, which I will show on the next slide, into the Heisenberg correlators in this non-abelianization map. So if we want to have the trivial insertion on the Virasoro side, on the Heisenberg side, instead of just inserting 1, we should insert this EW. And if we want to have the one-point function, instead of just using the dictionary, we also need to remember inserting EW. And this also works for the other endpoint correlators. Okay, so now I want to give you the definition of this operator EW, which is essential. So it is given by the exponential of 1 over 2 pi I times the integral, where the integral contour is given by the spectral network. And although this integral is on the base, the 2 insertions, this psi plus, psi minus, are actually on the cover, depending on the label. And here, psi plus minus are the free fermions which appear in the fermionization of the Heisenberg fields. So those are the basic ingredients of our non-abelianization story. And we know that there are different types of spectral networks. For each spectral network, applying our non-abelianization map, we will arrive at a type of the Virasoro blocks. In particular, there is a type of spectral network known as the Fenchel-Nielsen type, which is adapted to the Pan's decomposition. If we use this particular spectral network and apply the non-abelianization map, we expect that the corresponding type of Virasoro blocks will be the ones that by AJT correspondence that are identified with the Nikolsov partition functions. And here is an example on the 5-punctured sphere. So here, those black curves are the spectral networks. And we can see that it's indeed adapted with the Pan's decomposition. And it will, we expect that it will give us the Nikolsov partition function corresponding to this comb diagram. We can already see that there are some similarities between the 2 plots. So that's all I want to say about our story. And now I just want to mention some generalizations. The first one is a natural one, which is to study the Wn conformal blocks at c equals n minus 1. And there, the conformal blocks are less studied, so it will be interesting to get some results. And the second one is to generalize the central charge to the cases where c is not equal to 1. And that's the end of my talk. Thank you very much for your attention.
Thank you. There is time for one question. Yes.
In my work with Okounkov 2003, we constructed the free fermion representation of these partition functions. So it uses vertex operators from GL infinity. So you can realize them on a single fermion, but it's not the most natural operator. Have you looked at those? Are they equivalent, or it's something else? The curve which you're using looks like a speckled curve, like a Zeiberg-Witten curve. So it should correspond to some asymptotic limit with conformal dimensions ascend to infinity. So it might be an asymptotic expansion, not the actual convergent.
Sorry, I'm not very familiar with this.
Okay, so let's thank the speaker again. Next speaker, here it is. Okay, so the next speaker is Sagar Husseini. Please go ahead.
Thank you for the opportunity and for organizing this nice conference. I would like to tell you about topological symmetry topological filters and how to obtain them from a string theory. So this is based on work done together with Iñaki Garcia Echeverria and also work in progress with Yuji Tachikawa and Ising. Okay, so what are these symmetry topological filters? Well, before I say that, let's recall that in modern physics, we would like to think of symmetries in terms of topological operators and their fusion rules as categorical structures, as we heard in the talks by Sakura and Matthew. So now consider a quantum filter which has a fixed local structure, so fixed spectrum of local operators and their correlation functions. Then this given QFT, it may admit different choices of global structures or symmetries. And we believe that this topological data of symmetries and the choices of symmetries, they can be encoded in a QFT in a topological filter in one dimension higher, which is called a Symmetry TFT. This is much like the idea of anomaly theory. So we have that the anomalies of a D-dimensional theory are described by a D+1 dimensional anomaly theory. But there's a crucial difference that here the Symmetry TFT is dynamical and it is a non-invertible theory. So its Hilbert space has dimension greater than 1, and so the theory on the boundary, it has a partition vector and a partition function, and there is this gap boundary on this side where if you assume that the elements of the Hilbert space in this theory are in one-to-one correspondence with the boundary conditions here, it is only when we fix the boundary condition and pick a space in the Hilbert space that we fix the boundary theory to have a partition function. And in doing so, by picking a boundary condition, we fix this theory on the boundary to have a fixed global structure. So it becomes an absolute theory and it's no longer defined relative to this symmetry TFT. Now, once we do that, we get this, once we fix the boundary condition, we get the theory on the boundary with the fixed global structure and its anomaly theory. Okay, now, how do we actually get this symmetry TFT from a string theory? Well, we can consider any construction you like, ADS-CFT or some brain construction, but let's focus on geometric engineering where we have just pure geometry. We put a string theory on some product manifold, CL times MD, and a CL here is the internal space. It has the form of a cone over some space L, some base L, and it is non-compact, so it extends to infinity on this side. And then in this way, we can engineer a quantum filter on MD living at this singular locus of this internal space. So this quantum filter we construct, it is a relative QFT that I mentioned. We need to figure out what global structures we have. How do we do this from a string theory? So it turns out that the information about the symmetry TFT, it comes from the topology of the boundary L. So if we, instead of reducing a string theory on CL, if we reduce it on L, we find a D+1 dimensional theory, which is exactly this symmetry TFT. So if we look at this picture and then we try to do dimensional reduction on L, we get this boundary at infinity gives us this boundary that we had before in the symmetry TFT picture, and then we said that the QFT lives here, and then on this side we have the boundary where the relative QFT lives, and then in this way we can recover the picture of the symmetry TFT from a string theory. So very good. Now, how do we actually calculate this symmetry TFT more precisely? So can we write an action for it? Let's focus on type 2B string theory or type 2 string theory. Here we know that the RR fields combine into a self-dual field which is valued in twisted differential K theory. And it is well known that it's hard to, so I want to get an action for the symmetry TFT by dimensional reduction of an action for string theory. But we know that it's hard to write an action for self-dual fields. At least in 10 dimensions, I don't think there is a well-known action written in terms of twisted differential K theory. So How do we deal with this? What we can do is, looking at these papers, we can construct some 11-dimensional actions. So we go from 10 dimension to 1 dimension higher and construct a Chern-Simon theory, which realizes this self-dual field as a boundary mode. And so we have this 11-dimensional Chern-Simon theory on a manifold with boundary, and the gauge degrees of freedom on the boundary, they give us the self-dual field. Now, now that we have a good description for this self-dual field, if we reduce this Chern-Simon theory, we expect to find the symmetry TFT. So in picture, again, we started from a string theory on y times L. I said that L is the boundary geometry, and then when we reduce, we get a d plus 1-dimensional theory on y. And this is where the symmetry TFT lives. Now, since we cannot write an action in 10D on y times L, we go extend this y to z. When we write an action, a Chern-Simon action on y on z times L, and then we integrate over L to find a theory on z. Then the gauge degrees of freedom of z give us the boundary theory on y. Now, in equation more precisely, we have that we want to work locally because otherwise we run into the problem of having boundaries of boundaries. So we write the Lagrangian density and for the Chern-Simon here, and then we integrate over L, and then looking at the gauge transformation of this, we find the derivative of the symmetry TFT. Okay, so now there are some remaining problems related to some well-known problems. So the configuration we considered was type 2 string theory, and in this generalized compositor where we have H2 set K theory, the NS field is taken to be a background field and not dynamical. How do we extend to the case when that is not the case? And also, how do we extend to the case of M theory? Can we write a 12-dimensional action which describes it in the same way? And also, at the beginning, I said that we want to think of symmetries as categories. So can we extract this categorical information in this construction? Because the symmetry TFT we actually get from the dimensional reduction of the action, it contains a BF theory, which tells us about the choices of higher form symmetries and also anomalies of higher form symmetries. So how do we see the categorical information there? There is some work in progress, but much needs to be worked out. And finally, we know brains, they can be thought of as categories. So can we find a way to extract some information about categorical symmetries from that? Okay, thank you for listening.
Yes, a question there?
Yeah, I'm confused by your question, how do we extend to M theory? Because first of all, it's easier to push forward in differential cohomology than in differential KO. And secondly, I thought that's what you did in your paper.
Yeah, so in M theory, there is a topological action. There is a G4C3, and extending that to 12 dimension, we want to think of G4 as a gauge transformation of a B5 field, which is a theory in 12 dimensions. And it's hard we cannot quite write B5 cubed because the dimensions don't quite work.
I thought you took the differential version of CGG in your paper and pushed forward in differential cohomology.
Yeah, in that paper, this is a different paper. So here we want to just look at the gauge transformations of a Chern-Simon in 1 degree higher, which is the...
I see, okay.
Yeah.
Any more urgent question? Okay, if not, let's thank the speaker again.
Backward. Perfect, great.
Okay, the next speaker is Edward Mazeng. Please, go ahead.
Well, thank you very much for the organizers for letting me speak a bit about some work I've been doing with Matthias Gabriel and Rajesh Gopakumar. So I want to start with going back to quite an old idea due to 't Hooft, which is basically the question as to how large N gauge theories are sort of secretly string theories. And sort of his insight was that we identified the large N expansion with some sort of topological expansion, a sum over 2D surfaces in the dual string theory. And the idea was that if you looked at the Feynman diagrams, you would basically kind of think of them, if you squint enough, as some sort of 2D surfaces on the right-hand side. So making this idea precise is quite difficult, and to make some progress on that, what we're going to be doing today is, if you want to erase all the sort of spatial dependence of the propagators of the theory, set the propagators to 1 if you want. So we're going to be looking at gauge theories that are just simply matrix integrals. So here is what I would call maybe the simplest possible gauge theory. So this is just the Gaussian matrix integral. This is an integral over n squared IID random variables. And what I want to convince you today is that somehow there's a whole string theory looking into it. So what would be the gauge invariant observables of this theory? They would be expectation values of products of traces. And we can compute them just by simple Wick contractions. So I'm showing you here, for example, a 4-point function of trace of m squared. And we would diagrammatically keep track of this from a Feynman diagram by having these 4 external vertices. They have two legs coming out because it's trace of m squared, and the various edges are just the Wick contractions that I'm showing here on the left. So I want to follow this Feynman diagram today and try to show you how this Feynman diagram, first of all, map it to some 2D surface explicitly, and then tell you how that 2D surface is embedded in some target space. So let me first of all just, of course, state the result. So this is really a result a la Tuft. This is an explicit all-to-all orders and 1 over n matching of the correlators of the Gaussian matrix model with endpoint functions of a dual closed string theory. And I'll tell you what that string theory is, and I'll tell you what these vertex operators are. So this is really along with the idea of Tuft, where the string coupling is just 1 over n. So I'll make 2 comments very briefly. First of all, I just want to emphasize that there's been, of course, an idea since the 90s as to how the Feynman diagrams of the theory were related to these 2D surfaces. And the picture there was essentially that the Feynman diagrams, or their dual really, were some sort of discretization of the surface. And to get a genuine string theory, you needed to take some sort of continuum limit where the mesh, sort of the discretization size, goes to 0. And on the matrix model side, that was what was known as the double scaling limit. So if you want, the whole point of today's talk is to try to understand how we're going to step back away from this double scaling limit. And the main reason why is because in most other examples of gauge string duality that we have, we don't resort to this double scaling limit. So what we want to understand is some sort of new picture as to how the Feynman diagrams are realizing these 2D surfaces. We're certainly not the first people to step away from this double scaling limit. So there was a lot of beautiful work in the early 2000s by Dijkgraaf and Waffe, who showed, in fact, that the type of matrix integrals we're talking about today could descend actually from some beautiful system of branes and topological string theory. The focus here today is trying to reconstruct, if you want, the world sheet theory and sort of fleshing that duality out by adding in an operator dictionary, so that every time you, say, put in trace of m to the k in this matrix integral, you know what vertex operator to plug into the sum over 2D surfaces of the string theory path integral. So what is it that kind of replaces the minimal string, if you want, away from the double scaling limit? It turns out we're lucky that there's 3 equivalent descriptions. So of course, I only have time to talk just about one of them, so we'll focus the one on the left here, this A model. But the fact that these 3 are equivalent is something that goes back to the 90s, some work by Ghoshal and Waffe, and Muki and Waffe in particular. The one that I'll be talking about today is the one that sort of naturally arises from this picture of the Feynman diagrams, and it's essentially a topologically A-model twisted Wessel-Witten model with target SL2R mod U1 at this very special level 1. And in particular, what I'm showing you here is some sort of kind of operator dictionary, if you want, that's telling you how to relate the vertex operators here to traces in this Gaussian matrix model. So in the remaining couple minutes, what I want to do is to try to motivate sort of why is it that we're falling on those particular string theories? Why are those the ones that are coming out from the Feynman diagrams? And we'll look in particular at the A model. So the A model, just as a quick recap, is a sum of holomorphic maps from some world sheet to the target space. So what I need to do to tell you is how the Feynman diagrams reconstruct the world sheet and how the Feynman diagrams know about this holomorphic map. Okay? So those are the remaining 2 slides. So we need a different picture than discretization, and what we're going to use is what's known as the Strabel parametrization of the moduli space of Riemann surfaces. And this goes back to the work of Stribel and was sort of famously used by Kontsevich in his proof of the Witten conjecture. And what it is an exact equivalence between metrized ribbon graphs. Ribbon graphs are just these matrix Feynman diagrams, and points on the moduli space. So, and the way that this works roughly, I won't really have time to tell you, but I'll try to distill this down to 4 lessons. So there is this graph, which the Stribel graph, and that's these yellow lines over here. And I've tried to superimpose this Stribel graph directly on the world sheet that you see. So we're looking at some 4-point function in the matrix model. This is going to be some 4-point function on the dual string theory. The Stribel graph is, how is it related to our Feynman diagrams? It turns out to be the dual to the Feynman diagrams. Now, if you want to specify exactly which 2D surface I'm talking about, sort of what are the coordinates on moduli space, those turn out to be certain lengths that I assign to every edge of the Feynman diagram. I assign some positive numbers. Those are like the coordinates on moduli space. So I need to assign some lengths to these yellow lines. And how do I do that? Well, this is a bit of an art, but sort of the choice that we take is to say that it's the number of Wick contractions that these yellow lines are crossing. Okay, so in particular, here these yellow lines cross the white lines of the original Feynman diagram once, so you would assign length 1 to all of them. So in particular, if you want the coordinates on moduli space are all integer, okay? So maybe the way to phrase this is that we're not really discretizing the world sheet, but in some sense, latticizing directly the moduli space here. Now, if you want if there's one thing to take away from today, it's to think of every single gauge theory Feynman diagram as one particular world sheet. That's kind of the underlying picture that we have. So in the remaining minute, I just want to emphasize, not only now have we kind of taken the Feynman diagram and told you what 2D surface we're talking about, but I now want to embed this 2D surface into the target space. So for us, the target space here is just going to be a sphere, which I've very suggestively drawn just as this line as a CP1, okay? And the world sheet, if you want, it's going to wrap this sphere multiple times, twice as many times as there are edges to the Feynman diagrams. So what you see these colored lines, this is just some covering of the Riemann sphere, 8 times because there's 4 edges to this Feynman diagram. And these are very particular types of maps. They're branched holomorphic coverings of the sphere branched over exactly 3 points. And if you want the whole way to specify this map, it reduces down to just specifying the branching profile over those 3 points. And it turns out that these diagrams actually know everything you need to know to specify that branching. So roughly, there's a sort of, it's a bit of a black magic if you want, but sort of the vertices, edges, and faces encode the branching profile of this map over those 3 points. And it turns out you can't take every Riemann surface and wrap the sphere in this particular way. Which ones are the ones that you can do? It's exactly those that were labeled by these integer points. This is a beautiful theorem due to Belli. So how is it that this is picking out this particular string theory that I suggested was the dual? Well, it was shown earlier in the symmetric orbifold case that this SL2R string theory at this very special level 1 localizes exactly to holomorphic covering maps of the sphere. So in that sense, it's a very satisfying story. So I'll stop with that, and if you want a more humanely paced version of this talk, you can scan this QR code, and I'll take some questions. Thank you.
Any question or comments? Yes, Andreas Kapp. Yes.
Thank you. That was a really nice talk.
Thank you.
Could you somehow, is there an intuition as to why the number of edges gives you the degree of the map or whatever?
Right, right. Well, roughly every edge of these, the way that you can sort of write down this map is every single edge, well, half of the edge wraps the target space sphere once. That's why the degree of the cover is twice as many times at the edge. And we're thinking of every single half edge as really an open string world sheet. That's the strip. So if you want, it's gluing all these open string world sheets to form the closed string world sheet, and every open string is wrapping the sphere exactly once. Does that answer your question? Yeah.
Okay. There's one more question.
Thanks for a nice talk. So usually in string theory, we have 2 sides. The side that you have the matrix model is also realized with branes. And in that context, the string worksheet itself gives you the corresponding diagrams of a 't Hooft automatically, right? So we don't have to kind of reconstruct it. It's there. In some sense, string field theory is the analog of writing those diagrams in the field theory language, so you're going kind of one step further. But if you directly did at the level of string itself, it's more direct, I would think.
Yes, so what I would say is that the Feynman diagram here itself, actually you can think of, so the Strabel construction really is implementing the sort of same gluing of open string strips as you do in string field theory. What we would try to do is to understand how this is dual to a closed string world sheet. So that is maybe the...
Yeah, but the open string part, I would think that the first step is to go to realize it in the open string setup.
Yes.
And then just say why open became closed in the string language itself.
Yeah, yeah, so
Yes,
this is
yes.
all about sort of that open-closed duality here. I agree, definitely. Thank you.
Okay, thank you. There's no time for more questions, I'm sorry. So let's thank the speaker again. So the last speaker before the break, here it is.
Okay. So forward, backward, and here you have the pointer.
Okay, thank you. Yes. Hi.
So now the next speaker is Vatsal, please go ahead.
Hi everyone. I'll talk about my work with Shiraz, Chopardon, and Nikhil. This work is on fermionic Chern-Simons theory, and part of it was published as a preprint last year, and part of it is still in process. My objective with today's talk will be to look at a fully non-perturbative finite temperature solution to a non-supersymmetric non-abelian gauge theory with vector fermions in curved space. Our interest in this theory is for its demonstrated Bose-Fermi duality, wherein the thermal free energy spectrum of a bosonic theory matches with that of the fermionic theory under an explicit map in the couplings of the two theories. These calculations were performed in the light cone gauge over the past 13 years, and for that reason, this hasn't been worked out in any other non-trivial manifold. Last year, we were able to reproduce these fermionic results in flat space using the quote-unquote temporal gauge, which I'll describe soon. The way we set it up was amenable to generalizations to general genus G Riemannian manifolds, and I'll show you how. The motivation of this entire enterprise is to establish the Bose-Fermi duality on general genus G Riemann manifolds, possibly at finite n. It has been conjectured that this should hold, but it would be nice to see a few examples. The theory that I'll work with has a gauge group of UN. The action is given by the well-known 3D Chern-Simons action, minimally coupled to vector matter, fermionic matter. And since I'm interested in the thermal theory, the time coordinate is compactified. The quote-unquote temporal gauge that we adopt is this partial 3A3 equal to 0, 3 being the temporal direction. I will not go into the details of the entire gauge fixing, but I would like your attention at the fact that our gauge fixing prescription is valid for all genus G, equation 4 particularly. So before we choose a particular genus and work out a particular example, let me impress upon you this expression 5 and 6, which is general for any manifold at finite n and at finite volume, which means that we have a prescription in principle to work out the fermionic matter Chern-Simons theory on any manifold. It is a complicated mess, but you must appreciate the fact that all of the terms here in this action are completely local. So there is still hope that we might be able to evaluate it in particular cases. So we set upon the simplest case, which is genus 0, S2, and we look at the action. It's still not that simple, but we can do a further simplification, which comes at large n. We are not able to solve it at finite n, which still remains a challenge. But at large n, what happens is that we are only, and after we perform the path integrals over the spatial gauge fields, the temporal gauge field A3 is space independent, which means that the path integral is only left over the fermions, and the path integral over the gauge field A3 turns into a regular integral over the holonomy eigenvalues, lambdas. So there's one caveat here. The covariant derivative d tilde that you see is a highly non-trivial object. Since we have to evaluate it on the surface of the sphere, it will also depend on the spin connections of S2. Now, to solve for this theory, we need to find the eigenvectors of this operator, and those eigenvectors have to be figured out in terms of spin-weighted monopole spherical harmonics. Once we do that, we can find out. It's a long exercise which I can't flash here, but at the end of the exercise, we'll have this finite temperature gap equation for the self-energy, sigma of t, and remarkably, the gap equation for the finite radius case, equation 12, looks quite similar to the gap equation we obtained for the flat space case, which is equation 14. One would say naively that you can obtain equation 12 from 14 by a simple replacement of an integral by a sum, but I would press that this replacement, the details of this replacement lies in the entire exercise of using spherical harmonics, monopole spherical harmonics, because we wouldn't know the limits otherwise of the summation for the replacement. We can solve this gap equation exactly. By exact, I mean at every order in the Tehude coupling, but only at large n. The solutions are given in terms of two functions, omega and phi. Only phi enters anything physical, for example, the mass gap equation, equation 19, or the thermal free energy. In the flat space case, we were able to evaluate the function phi explicitly as in equation 21. However, in the finite radius case, we weren't able to do that. We haven't obtained a closed form solution yet, but we can still numerically compare it with the large radius limit. Two things that we immediately observe here is that the thermal mass for the finite radius case is lower than the thermal mass for flat space. And the second thing is, if we start with a theory, if we turn on a bare mass which is greater, then the two solutions come close to each other, which seems like if we have a larger bare mass, the theory localizes on S2. It becomes closer to the flat space case. We don't have an analytical understanding of it yet. It's just preliminary work. I would reserve most of the discussion for posters and the reception, but I would present to you the key takeaway from here. In our entire calculation, the biggest thing that comes out, the biggest difference from the flat space calculation that comes out is now that the thermal effective action is not independent of the fluxes, the holonomy eigenvalues will not be quantized. If that won't happen, and if the Bose-Fermi duality has to hold, it has to work in a mathematically different way. And it would be interesting to understand how will that happen. Do I have time to go with the rest? Sure, thank you. So also in these calculations, as we saw, that the fluxes enter the thermal effective action, particularly they enter the fermionic determinant. And this has quite a few similarities with the calculations that we could see in the calculations of superconformal index, as in this paper and many others in the literature. We can also now attack a first principles computation of S matrices, which was so far only been approached in an ad hoc manner. But the final point about duality, we weren't able to compute the thermal free energy for bosons because of this difficult phi square A square coupling, since the A wedge A term doesn't go away in our gauge. However, one way to address this is to repeat the Blau and Thompson exercise for the bosonic case. Thank you. These are some selected references from my talk today. A comprehensive list can be found in the papers. Thank you.
Are there any questions? Okay, if not, let's thank the speaker again. So we reconvene at 4:25 in 23 minutes. This is to go back, and this instead is to. Okay, I think we can start. Please take your seat. Okay, we have the last block of gong shows, and the first speaker is Eduardo Garcia Valdecasas. Please.
Okay. Well, I thank the colleagues at ICTP and CISA for giving me the chance to talk about my work. I will be talking about a notion of a feature of some quantum field theories that can be thought of as the limiting case of higher p-form symmetries when, in the case of p equals to -1. And this feature shares some similarities with the usual symmetries, but not all of them. That's the reason why I'm putting here quotation marks, but I will remove them for the rest of the talk. And I will be talking about whether we can think of a spontaneous breaking of this kind of symmetries and what this means and what is some useful notions that it gives us. Okay, so this is based on this paper that appeared earlier in the year with Daniel Aloni, Matt Rees, and Moto Suzuki. I will start with an introduction, then I give a toy example in 2 dimensions, and then we'll graduate to 4 dimensions where I will very briefly talk about the Yuan-Yang-Mills QCD and the strong CP problem. So I told you that the case of p equals to -1 is a bit degenerate. So we will adopt the following definition for the purpose of this talk. I'll say that a theory has a -1 form U1 symmetry if there is a local operator, J0, which can be coupled to a background field which takes values in the circle. So I can write a coupling of this form. The property will be that the integral of star J0 is quantized, and we'll call this the -1 form symmetry charge. The example that I have in mind is a 4-dimensional non-abelian gauge theory in 4 dimensions, where the -1 form symmetry charge is the instanton number. Okay, so in which sense are these symmetries different from their higher p-form counterparts? Well, there is a conserved current, but the conservation equation doesn't really make a lot of sense, at least not in the usual sense, because the conservation equation is tautological. Every top form is closed. Still, the charges are quantized. Topological operators, something similar, they are space-time filling, so it's not very clear in which sense one can introduce them in correlation functions to, for instance, give selection rules, so there are no selection rules. And analogously, there are no charge operators, so there are no selection rules again. Okay, so these 3 properties are different, and there are some ways in which these symmetries are similar to the other ones. In particular, one can couple background gauge fields. So the background gauge field, you already saw it, is this field theta, which takes values on the circle, and one can think about the periodicity as a large gauge transformation for the -1 form symmetry. We can gauge the symmetry by summing over field configurations of theta, And so we understand that a compact scalar field can be thought of as a gauge field for a -1 form symmetry. These symmetries can have anomalies, and they have been studied in the past, and they give interesting constraints on the IR physics of families of QFTs. And finally, what I want to address today is whether we can think about the spontaneous breaking. You may think that this is a bit of a long shot. In particular, there are no charged operators that can take a Beth and signal that the symmetry was spontaneously broken, and there is no candidate for a Goldstone boson. Okay. So let me go to the toy model, but before, let me remind you about 4D Maxwell. So it has an electric one-form symmetry and a magnetic one-form symmetry. They are both spontaneously broken, and it is understood that the photon is the Goldstone of this spontaneous breaking. In 3D, there is a similar story, but in this case, the one-form electric symmetry is not spontaneously broken. Still, one can see that the zero-form magnetic symmetry, which in this case is a zero form, is spontaneously broken. And one can understand the photon and its dual, which is a compact scalar, as the Goldstones for this breaking. So then the question is what happens in 2D Maxwell. So in 2D Maxwell, we have an electric one-form symmetry, which is not spontaneously broken. And in this case, the magnetic symmetry is -1 form. So we can introduce this theta term that I wrote, which is the background field for this symmetry. The 2D photon has no propagating degrees of freedom. And then the question is in which sense we can think about 2D Maxwell as a theory describing an spontaneously broken magnetic symmetry, which is -1 form, and in which sense the 2D photon is the Goldstone of this breaking. So we want to characterize this breaking, but there are no charged operators. So we can try to, oh, sorry, I went a bit ahead of myself. So let me discuss a bit more the physics of 2D Maxwell theory. So we can regulate it by putting it in a circle. Then the theory reduces to the quantum mechanics of a particle in a circle with a magnetic field. The spectrum is well known. There are different branches indexed by a quantum number L. And in each branch, the energy depends on theta quadratically. And on top of this vacua, one can put the probe particles, and if one puts two electric probe particles, they will feel an attracting force, classically, so they are, which is linear, and so one says that the electric charges are classically confined in 2 dimensions. Very good. Now, let me try to argue that the symmetry is spontaneously broken. We cannot check any Beth for any charge operators because there are none, but we can argue by analogy. So if we had a zero-form symmetry and we wanted to argue that it is spontaneously broken, but we couldn't compute any Beth, one thing we could try to do is to gauge the symmetry and realize that it is in the Higgs phase once we gauge it. Then we would say that in the original theory, the symmetry was spontaneously broken. In such a case, the gauge boson will be massive, and there will be electric screening and magnetic confinement. So what we can do is gauge the -1 form symmetry in the previous theory in 2D Maxwell and check if these properties are realized. We gauge the symmetry by introducing this compact scalar field phi. It's easy to get convinced that this field is massive because of the spectrum that I plotted before. And it's some sort of Goldstone, would-be Goldstone field. There is electric screening, and one can also get convinced that there is magnetic screening because the magnetic operator, which is a vortex operator, is not gauge invariant. One needs to attach a Wilson line to make it gauge invariant, and I told you that the Wilson lines are confined in 2 dimensions. So we learned that there is magnetic confinement. So the conclusion is that if we gauge the magnetic -1 form symmetry, it is in the Higgs phase. So we say that in the original, we interpret this to mean that in the original 2D Maxwell theory, the symmetry was spontaneously broken. Okay, I think I'm running a bit out of time. Okay, so we want to find an order parameter. Again, there is no charge operator, but we notice that if the energy did not depend on theta, the gauge symmetry wouldn't have been in the Higgs phase. What we propose is that the spontaneous breaking of the -1 form symmetry can be diagnosed by an explicit dependence of the vacuum energy on a constant background electric field, on a constant background field theta. The leading dependence is the topological susceptibility, so we propose that the topological susceptibility is an order parameter for this spontaneous breaking. An interesting link is that the topological susceptibility can also be written in this form. And what this equation tells us is that if the topological susceptibility is non-zero, the two-point function on the right must have a quadratic pole at zero momentum. So this looks a lot like the usual Goldstone theorem, but it's not exactly the Goldstone theorem. Okay, so what we conclude is that This order parameter is related to the masslessness of the photon, which we interpret to be the Hodge dual of the Goldstone boson for this spontaneous breaking. Okay, and we think this story is general and it will be universal in any theory that has a spontaneously broken -1 form symmetry in the way I defined it. Will have an emergent description in the IR in terms of a topological theory, which includes a D-1 form gauge field. Okay. Two examples of these theories with such a property are SU and Young-Mills and QCD. Both theories have an -1 form U1 symmetry, whose background field is the theta term in 4 dimensions. They have a non-zero topological susceptibility, so the -1 form symmetry is spontaneously broken. And one can get convinced that the Goldstone field in this case is the Chen-Simons tree form. In fact, it's known that R large N, SU and Young-Mills, its infrared can be described using an effective theory in terms of this Chen-Simons tree form, which the theory takes this form, which is basically the same as the 2D Maxwell theory that I wrote before. Okay, so let me just conclude by making the link with the strong CP problem. So in our language, theta is physical if the -1 form symmetry is spontaneously broken. And this is a requisite for the strong CP problem to arise. The strong CP problem says that theta is very small and physical. So if we are able to prevent this from happening, we will be avoiding the strong CP problem. One can do this in 2 ways, by either gauging or breaking the -1 form symmetry. And indeed, if one looks at some of the solutions that appear to the strong CP problem in the literature, for instance, the action solution or the massless quark solution, one can understand them as having solved the problem by gauging the -1 form symmetry. And something that we also did is to look for new solutions, maybe using anomalies or explicit breaking in the UV, but so far we've been unsuccessful. Okay, and this is some outlook. Thanks.
Any question? Yes.
So if I understand correctly, intuitively speaking, instead of talking about like, I don't know, a -1 form field as the Goldstone boson, you actually introduce a dual field, which is like a D form field as the Goldstone boson, right?
Right, it's a D-1 form field, yes.
Yes,
exactly, so it's the Hodge dual.
Okay, I see, okay, thanks.
Okay, let's thank Edu again. And the next speaker is? Okay. The next speaker is Michael Schultz, please.
Thanks so much for the opportunity to speak, and thanks to the organizers for organizing a great event. So today I'm going to be speaking to you about recent work that appeared on the archive earlier this year with Andres Melmedier on the themes that are listed here in the title. And so we're going to start in kind of a strange place for this conference, which is by picking a real number x at random. And since we're picking it at random, it is with 100% certainty going to be irrational, since q has measure 0. But if somebody hands you this number x, how would you actually prove that it is irrational? So if the number is relatively simple, like the square root of 2, you could do it by contradiction, as we all know. But if your number is more interesting, then that's quickly not going to work. So one way that you can analyze irrationality is through this Dirichlet irrationality criterion, which utilizes 2 sequences of rational numbers, satisfying these conditions here, and essentially asking that the ratio converges to x sufficiently quickly to guarantee that x is irrational. So a more interesting class of numbers is that of values of the zeta function. So as opposed to values of the zeta function at positive even integers, the zeta values at odd numbers has resisted analysis. So in 1978, Roger Apéry really shocked the mathematics community by showing that zeta of 3 was irrational. People didn't know anything about it up to that point. And the way that Apéry did this was by using the Dirichlet irrationality criterion with these sequences of numbers that appear here, And in particular, these sequences satisfy the same linear recursion relation here. Now, these sequences were able to be constructed exactly. In particular, the ANs are all positive integers, and the BNs are more complicated numbers that are rational, but you can see hints of zeta of 3 appearing right there. And so while they're constructed exactly, one would still like to know, where did these numbers actually come from? So the short answer is that they come from algebraic geometry, though another way to answer this question is to say that they come from modular forms, as we'll see a little bit later. To see this, we can apply the Frobenius method, obtaining generating functions of these two sequences, in which case the linear recursion turns into a third-order linear differential operator, which is written here in terms of the logarithmic derivative. And then the sequence for the ANs gets annihilated by this operator L3, and this is a typo. It should say that gamma satisfies a non-homogeneous equation with the operator L3. So the genesis for the geometry that comes out is the fact that this operator is a Calabi-Yau operator. In fact, it's the Picard-Fuchs operator of something that we'll see in just a minute. But if we just had this operator ourselves, we could analyze it. We would see that it is self-adjoint. It's also maximally unipotent at t equals 0, and omega is the unique holomorphic solution at t equals 0 that satisfies the kind of integrality properties that you would expect from Calabi-Yaus. So the fact that it's maximally unipotent tells us that we have a canonical logarithmic basis of solutions near t equals 0, and the fact that this operator is self-adjoint means that these solutions satisfy a quadratic relation. So we would expect, because it's a third-order operator, that omega is the holomorphic period of a pencil of K3 surfaces. And this is indeed the case. So this was shown by Boykers and then later by Borkers and Peters using an integral representation for the series omega. And they showed that you can write precisely omega as the period integral of a K3 surface that's given by this affine equation here, or this equation in affine 3 space. So that's very nice, that's very cool. And one might ask, okay, for the other sequence Bn, is there a geometric interpretation of this object? So one way to analyze this question is by finding a fourth order operator that annihilates this series. So a way that you can do this is simply by taking the derivative of this third order operator, and then due to that non-homogeneous equation that we had before, gamma is going to satisfy this homogeneous equation, but this time at t is equal to infinity instead of at 0. And this operator looks pretty nice. It looks like the kind of operators that arise in mirror symmetry for pencils of Calabi-Yau threefolds. So one might also ask, because this is a maximally unipotent operator, is this also of geometric origin? And the answer is no, it's actually not. And the reason is because this operator is not self-adjoint. One way that you can see this is that the original three solutions for the previous operator are still solutions of D4 since we've basically just taken the derivative. But let's pretend like we didn't know that. And we just had this operator and we wanted to compute quantities that appear in mirror symmetry for Calabi-Yau threefolds, like the holomorphic prepotential, the Yukawa coupling, and instanton numbers. So this is due to results of Wensi Yang in 2021. And when he computed this, you compute the mirror map as usual. In this case, for the reasons that I was just saying, the mirror map is the same as the mirror map for the pencil of K3 surfaces. But the holomorphic prepotential that you would look at, for example, for mirror symmetry of Calabi-Yau threefolds, due to the quadratic relation among the first three solutions, is essentially just going to reduce down to this leading order term. That's really the only interesting thing here, and so I've normalized the coefficient to be 1. And so if we define this Yukawa coupling as being the third order derivative of this prepotential with respect to the mirror map, we can compute a Lambert-like expansion like we do in mirror symmetry for Calabi-Yau threefolds. Now I'm calling these virtual quantities because they really shouldn't be there. This is not a self-adjoint operator, so technically we can't do this, but let's just do it anyways and see what happens. So when Yang did this, he found very surprisingly that we get something that's non-trivial. In fact, we get instanton numbers that are integral, and in fact, they're 6 periodic. But even more surprisingly, this virtual Yukawa coupling is a modular form of weight 4 for the group gamma naught of 6+. And this is very surprising. This kind of stuff does not happen for Calabi-Yau threefold mirror symmetry. So Yang looked around for another example and analyzed the Dwork pencil of K3 surfaces, given here. And doing a similar story, found two periodic virtual instanton numbers that are given here. So Yang said, there's something happening here, but I don't know what. So in the article that I referenced earlier, what we found is that a common way to organize these examples was into modular pencils of K3 surfaces for the groups gamma naught of n plus for these values of n. And these appeared, in particular, in the work of Golishev in 2005 for mirror symmetry of rank 1 Fano threefolds, and later by Golishev and Zaghi in 2016 in their proof of the gamma conjecture for these rank 1 Fanos. So the case n equals 2 corresponds to the Dwork pencil that Yang found. So utilizing results from Golishev and Zaghi, we were able to show that these virtual Yukawa couplings were always weight 4 modular forms. In fact, they're always rational linear combinations of weight 4 Eisenstein series. I'm trying to get it to go over there. So this shows, in particular, the modularity, the weight 4, the fact that the prepotential is always an Eichler integral for these modular forms, and that these virtual instanton numbers are always going to be periodic integers after normalization. So this appears to show that maybe those virtual instanton numbers are just not so interesting. Yes, we get a modular form, but maybe they don't actually encode anything that would be worth checking out. But we argue that, in fact, you can get something interesting from these. So in Golishev's work, this operator that I'm calling the quantum operator D4 appears precisely as the Borel-Laplace transform of the A-side connection on small quantum cohomology of those rank 1 Fanos, in which these modular K3 pencils that we're looking at are mirrored to the anti-canonical K3s in those Fanos. So generalizing results of Steenstra for instanton expansions of the non-critical string on local threefolds, if we define this quantity capital Q via this equation here, relating it to the period integrals of the mirror K3, inverting the equation and then doing another Lambert series type expansion as one would in mirror symmetry, we get something like this, and we find some numbers that I'm calling n-twiddle, and I'm calling these the dual instanton numbers of the virtual instanton numbers that we had previously. And it's these instanton numbers that I argue actually carry some geometric content. So in all the examples that we analyze, we can find that these dual instanton numbers are in fact integral, and they have the candidacy to actually carry some real enumerative information. And so we found, in the case n equals 2, which again corresponds to the Dwork pencil, that after suitable normalization, when you compute these dual instanton numbers, that you find precisely the genus 0 Gromov-Witten invariance of local P3 as computed by Clem and Penhare-Pandey in 2007. So we conjecture that such a thing should persist for all of the examples here, and that these dual instanton numbers should be genus 0 Gromov-Witten invariance of the local Calabi-Yau fourfold. That's the total space of the canonical bundle of those rank 1 Fanos. And I'll end by saying that this sort of a result is consistent with Iritani's recent work on the mirror symmetric gamma conjecture. Thank you so much for your attention.
Is there any question? Yes. Wait.
Spot is actually the one that appears in 4 p.m. Black hole scattering. So it's exactly
this one here
that Boykers had.
Oh yeah, that's what you mentioned in your talk. I forgot to mention that. Yes.
Quite funny.
Yes.
And actually also the inhomogeneity plays a role.
Yes, right, exactly.
In the following up of the calculation.
Yes. Thank you for the comment.
Okay, one more question.
So if I understand, canonical bundle on P3, there being a relationship between Gromov-Witten invariance of that and of the K3 surface. There's some such relation which comes from quantum Lefschetz, and this is a different relation. What is the relationship between those relations?
It seems that it's this local relative relation. In talking to some other people, they've seemed to say that a way to think of this is in terms of relative invariance of the log Calabi-Yau pair in P3 corresponding with its anti-canonical divisor. So zeta of 3, as was mentioned just a minute ago, the connection is to that particular K3 surface, which seems to be quite interesting and arise in those ways. And then this sort of behavior seems to persist for these families of K3 surfaces that are connected to these modular forms. So the zeta of 3 family happens to be one of those.
Because in topological string, zeta of 3 mysteriously is a kind of a degree 0 contribution, which one deduces from indirectly, but maybe.
Yeah, it is interesting that it arises
Actually,
in that context
the
as well.
proof is that there's a hyperconvergency that Upper reused that he could use to prove that set of 3 is irrational. So as not, it's probably the gamma class.
Maybe we can you can talk more during the break. So no, there is no time. I'm sorry. Otherwise, the organizer will kill me. Thanks again. So next speaker, there should be a speaker. Yes. Yeah. So the next speaker is Irit Hukurvilla, please.
Thank you for organizing this conference and giving me the opportunity to speak. This work is based on an article that was posted recently and one that has yet to appear. So the main object of study here is the quantum K-ring. It is a Q deformation of the usual K-ring and defined using genus 0 K-theoretic Gromov-Witten invariants. Q here are Novikov variables indexed by effective curve classes in X. One way to describe it is by using 2-point invariants to deform the Poincare pairing, and then using 3-point invariants to deform the resulting structure constants, which defines us a quantum product. So in particular, the pairing of the quantum product of OY1 with an OY2 with OY3 is the number of genus 0 curves passing through Y1, Y2, and Y3. Simple example, projective space. The K-theory of projective space is determined by 1 minus O of minus 1 being nilpotent. Quantum K-theory, instead of being nilpotent, it becomes Q. In general, if you're familiar with quantum cohomology, the construction is similar, but it's generally harder to compute quantum K-rings. The targets we're interested today are flag varieties in type A. They parameterize flags of subspaces in a larger vector space. Their K-theory is described in the following way. Each subspace in the flag gives you a tautological bundle over the flag variety called SI. And these sort of obvious relations among the lambda y classes of these bundles that are on the bottom of the screen here are good enough to generate the K-ring. So what about the quantum K-ring? Well, in some cases this is known. It's known for full flags, it's known for Grassmannians, and it's known for instance varieties. But in general, we're not sure. But there is a conjecture made by Gu, Mihalcha, Sharp, Xu, Zhang, and Zhou. And it's determined by the following deformation of this Whitney sum formula. And there's kind of a heuristic from physics of why this should be true. It comes from the fact that the quantum K-ring is the OPE ring of a certain 3D GLSM. The Wilson line operators here correspond to doing kind of Schubert calculus in this quantum K-ring. So if you start with sigma times S1 and you apply a Fourier transform, that turns your S1 into a Z. So now your 3D problem is a 2D problem. And then this gives you a twisted superpotential. You get quantum K-theory from this after picking some Chern-Simons terms. And the superpotential looks like this for those interested. What we care about here is the critical locus of this superpotential. And that's given by the equations here for each I. These are called the Bethe-Ansatz equations for reasons I won't get into. If you interpret the xij as Chern roots of Si, or K-theoretic Chern roots, then some kind of symmetrization of these things gives you the Whitney relations. So the question we have is, how do we make this rigorous? What do these equations really mean? And the answer comes from abelianization. So classically, if you take a GIT quotient, A mod G, for G some reductive group, we can also consider the abelianization, which is the quotient A mod T by the maximal torus. The K-rings are related in the following way. There's a surjective map from the Weil invariance of the K-ring of the abelianization into the K-ring of A mod G. There's some more details here. We don't need them for now. In our case, our flags are GIT quotients in the most standard way you can think of. And the corresponding abelian quotients are towers of projective bundles. And essentially, the correspondence identifies O of -1 on these bundles with some Chern roots of the Si. So essentially, one might hope the same thing is true in quantum K-rings. And if you literally copy-paste everything in the conjecture, not quite. But one of the ways of handling this is to twist the quantum K-ring on the abelian side, which means you define your Gromov-Witten invariance using a different virtual structure sheaf. So the appropriate conjecture is that after doing this, you also have a surjective map. So this conjecture is true in the case of flag varieties, and when you calculate stuff on the abelian side, you get things that correspond to the Bethe-Ansatz equations, provided you interpret the xij as the appropriate tautological bundle. So the Weil group is Sn, so symmetrization of these do descend to relations back onto your flag. There's some work involved here, that's why I put a star, but it can be done. And so that ends up proving the Whitney conjectures, that they do in fact give you a presentation of the quantum K-ring of flags. Thank you again for organizing this conference.
Thank you. Any question?
This comes from the Yang-Baxter side. If you think of this, the compact limit of the Yang-Baxter story for T-star flags, the equations are the Bethe-Ansatz equations from there. So from that perspective, you can think of what I'm doing as explicitly calculating which deformations of the tautological bundles you get. I think Christian Korf told me something like this once, but I forgot what he said.
No. It's not. It's the spectral dual, so it's not the Q-tode. Q-tode is what you get if you start varying Keller parameters.
Q-tode is the full flag.
No, so if you take cotangent bundle to flag varieties, this is XXZ spin chain for SUN when n is the length of the flag. But if you take the limit, it's kind of I don't know what it is, so that's why I'm asking.
Yeah, I know I think there's some way to describe this also in the compact limit, but I don't know what it is.
Any more questions? Okay, if not, let's thank the speaker again.
Forward, backward, and here you the point here, not everywhere. Okay? Stay close.
Okay, the next speaker is Tommaso Maria Botta, please.
Great. Thank you very much for the opportunity. So yeah, today's talk, which is based on joint work with Ben Davison, is about two Lie algebras that naturally arise in connection with string theory and quantum field theory, namely the Maudek-Markov Lie algebra and the BPS Lie algebra. So since it's kind of late, and I will start with two tales from the 20th century. So let's fix a quiver Q without one loops, but that's just for now. So we can then define its. Okay. We can define its generalized Cartan matrix. So this is an example, for instance. And we all know that out of it we can produce a Lie algebra, a Kac-Moody Lie algebra, and we can define it over Q, and it has its standard triangular decomposition. And another thing we know is that whenever we have a quiver, it might be relevant starting quiver varieties, so as those defined in previous talks. So it's a symplectic reduction of the cotangent bundle of the space of representations of the frame quiver. And well, what Nakajima thought in the 90s is that if we consider the direct sum of the cohomologies of all the quiver varieties, then there's a canonical morphism of algebras from the universal enveloping algebra of the Kac-Moody Lie algebras to the endomorphism of this cohomology. And so this effectively means that we can produce representations of Kac-Moody Lie algebras out of geometry. So that's one cool story. It led off tons of new directions in geometric representation theory. And another interesting story that from last century is the one of Katz polynomials. So morally, Katz taught us that we might want to count isomorphism classes of representations of our quiver Q. And in particular, if we count them right, namely if we count isomorphism classes of absolute and decomposable representations, that we get some numbers that are really, really interesting and cool. And so from a representation theory perspective, one of the reasons why we want to study these numbers is the so-called Katz constant term conjecture, now a theorem by Tamas Hausel, and which means that if we pick some specific root space of our Kac-Moody Lie algebra, then the constant term of the Katz polynomial recovers its dimension. So, okay, but now we are in the 21st century, so we might ask ourselves new questions. So what if we want to recover the whole Katz polynomial, so not only its constant term, and what if we want to allow one loops in our quiver? So what if we want to consider something like this? So we want to allow loops or even multiple loops based at some vertex. Well, if so, then the resulting Lie algebra must be Z-graded. Well, that's because we want to recover the whole Katz polynomial. And in addition, we want to take care of three kind of vertices. So there are real vertices, so those without loops, those we are used to. Isotropic vertices, so those vertices which exactly want a loop, like the one in green here. And finally, hyperbolic vertices, namely those with at least one loop. So you see that there's a difference in the Cartan matrix. So the entries vary according to the type of the vertex. Well, so this is not the realm of Kac-Moody Lie algebras anymore, but rather the realm of generalized Kac-Moody Lie algebras, so also known as Brocher's Lie algebras. So of course I could write down the definition of these Lie algebras, but that would be kind of mean now in the afternoon, so I will just give you a feeling about them. So the idea is that they are still generated by some kind of generalized triples E, H, F, those we are used to, but we have to be careful because, for instance, if a vertex is isotropic, then these are the relations of these three base elements are not modeled on SL2, but rather on the three-dimensional Heisenberg Lie algebras, which means nothing but the fact that in this case H is central. And in addition, of course, we have cell relations, but cell relations now will apply only if the vertex I is real, or whenever the Cij is equal to 0. So in particular, for instance, if we have a vertex which is hyperbolic, then we don't have several relations there. Well, okay, so these are some cool algebraic facts, hopefully cool, but you might ask, so how do we construct them, and especially how do we construct them from geometry? And the answer here, well, there are two possible answers. And they go under the name of Malikonkov theory and cohomological algebras. So let's analyze them separately first. So Malikonkov theory is a gadget developed around 15 years ago that arises in connection with Gromov-Witten theory of quiver varieties. And in particular, it produces a Lie algebra and a Yangian. Oh, sorry. So this is the Malikonkov Lie algebra, and this is the associated Yangian, which is a quantum group, living and acting on quiver varieties. And essentially, both the Lie algebra and the Yangian are reconstructed from the braiding of its category of representations. So effectively, the geometric gadget that it's used to define these Lie algebra and algebra are the so-called stable envelopes, which are certain operators, Steinberg actually correspondences acting on quiver varieties on their cohomology that produce a triangular decomposition of the hermetics. And we also have a triangular decomposition of the associated Lie algebra, the Malikonkov Lie algebra, which is what we would expect from the theory of generalized Kac-Moody Lie algebras. And finally, so one of the reasons why this is relevant is that if we want to control the quantum multiplication on quiver varieties, we cannot just consider a Kac-Moody Lie algebra, but we need this whole larger object. And so this is, for instance, the formula for the quantum multiplication that, as you see, depends on certain invariant tensors in the universal enveloping algebra of this Lie algebra. So this is one story, and another story is the one about the story of cohomological algebras. So these also have geometric origin in the sense that essentially they categorify the T-theory for Jacobi algebras. But for us, let's see. So for us, essentially, there are some B algebras produced out of geometry that are defined as follows. So essentially, they are the Borel-Moore homology of the modular stack of representations of the zero locus of the moment map. So the multiplication and the action of quiver variety is defined geometrically by means of some Eke correspondences. And there's a generalized Kac-Moody Lie algebra, the so-called BPS Lie algebra, that essentially governs the algebraic structure underlying the cohomological algebras. And finally, last but not least, the Katz polynomials are recovered by the greater dimension of the root spaces of the BPS Lie algebra. So, okay, so we have two geometrically interesting Lie algebras that we might try to compare. And indeed, it's been, since the origin of this Lie algebra, it's always been thought that one has to do it, so they should be related somehow. And actually, the main result I want to present today exactly explains the relation. And actually, that's the stronger relation possible. So we have an isomorphism between the Malikonkov Lie algebra and the BPS Lie algebra up to fixing the base field where they are defined and modulo some center. And this intertwines the natural actions on cohomology of quiver varieties. So in particular, the Malikonkov Lie algebra is a generalized Kac-Moody Lie algebra, which is something that you cannot see directly. And there are two main corollaries of this story that have been also reproved by Schliffman and Vassero recently. And that is first of all, that there is an isomorphism between the cohomological algebra and the positive part of the Yangian, which also intertwines the action on quiver varieties. And finally, Konkov's conjecture that states that the greater dimension of the Malikonkov Lie algebra recovers, once again, the Katz polynomials. It's kind of surprising in many ways. So, well, in principle, I could spend a few words about the proof, but I think it's time to ask whether there are questions, and thank you for listening.
Yes, one question there. Any specific physics context that these apply to?
That's the question I fear the most.
Because the objects you're dealing seems to be very interesting for us. I just don't see the context.
Right, absolutely. So I mean, in a sense, as I said, this Maudsley algebra and the whole story associated with it, it's something that controls quantum cohomology of queer varieties, so moduli space of Higgs branches of 3D n=4 theories. And on the other hand, the BPS Lie algebra is something that should, as I said, it's something that comes from DT theory. And so because of this PBW type isomorphism, essentially the great dimension of the Koha should recover the Gopal-Kumar-Vafa invariants. But that's essentially what I'm feeling confident enough to say here in front of everyone. Then maybe we can discuss more later.
Okay, so let's thank the speaker again. Okay, we have one last speaker. Okay, the last speaker of the session is Justin Kulp. Please, go ahead.
Okay, thank you for having me here today, and thanks to all the previous speakers. I'm not going to talk about something nearly as fancy. I'm going to talk about stuff which is presumably entirely in Peskin and Schroeder if you look at it the right way. So most of the work I'm going to be talking about today is in a recent paper with Davide Gaiotto and Jingsheng Wu, but also there's relevant earlier works with Kasia Budzik, Brian Williams, and Matthew Yu. So here's the papers down at the bottom. So in particular, what I want to argue today is that quantum field theories have collections of higher multilinear k-area operations, colloquially called brackets, like in equation 1. And these brackets control deformations, operator product expansions, and anomalies of quantum field theories, and they satisfy various consistency relations, kind of generalizing Jacobi identity. And if you're familiar with words like factorization algebras, then there's factorization algebras, operads, and infinity algebras lurking underneath here, but I'm not going to address them directly, but if you're familiar with these words, then maybe you'll see something else. These structures are actually very familiar to high-energy physicists and mathematicians who've studied twisted supersymmetric quantum field theories, especially in the context of descent relations, or even string field theory, but I'm not exactly an expert on string field theory. And indeed, as that kind of implies, we can go very far in holomorphic or topological scenarios. So if people want to switch to their laptops or fire out a few tweets, this is the three main takeaways before you leave, is that quantum field theories have these higher brackets, and they're defined by something that I'll call the eta vector. These brackets are very computable, I really want to stress that, and they encode anomalies and operator product expansions. And then at the end, I'll flash very quickly a non-renormalization theorem in holomorphic topological scenarios. Okay, so let's start with the eta function. So given a quantum field theory T, it can be deformed, at least perturbatively, by turning on interactions, and I've schematically drawn that here in equation 2. And in this case, the couplings GI, they're kind of like coordinates on this theory space of like effective quantum field theories. And in this talk, I'm going to work to all orders in perturbation theory. So every function you see of GI should be understood to be a formal power series in these GI. Now, a generic quantum field theory famously, or a point, is not scale invariant. So if you do a scale transformation on the theory, then what that's going to do is we effectively trade that for a change of the couplings. And we encode this change of the couplings in terms of this change of the couplings generated by these scale transformations in the form of a beta function. So here's a beta function here in expression 3. And as promised, the coefficients are a formal power series. And sort of the first term, the linear term in the coefficient, or in the beta function, kind of tells you about classical violations of scale symmetry. And the higher order terms tell you about, in scare quotes, quantum mechanical violations of scale symmetry. So why did I tell you all that? Well, I told you all that because an often underappreciated point is that you can compute the analog of the beta function for any type of transformation. So for example, non-relativistic scale transformations are something very popular right now. And in this talk, what I want to do is I want to consider my quantum field theory T, but described in a BV-BRST formalism. So it's embedded in a larger theory, T-twiddle, and T-twiddle is some large ambient theory with ghosts, anti-ghosts, possibly anti-fields if you're going full BV. And it has some sort of odd nilpotent symmetry, QBRST. And the observables in T are recovered from T-twiddle, essentially by definition, by taking the QBRST cohomology. And then what I want to understand today is I want to deform T by deforming T-twiddle, but without breaking this BRST symmetry. Okay? And in this case, the BRST symmetry, just 100% analogous to the scale transformations, will be encoded instead in eta function instead of a beta function. And I've drawn it here in expression 5. And exactly analogous to the beta function, the linear terms of these coefficients will tell us if an interaction, calligraphic I, explicitly violates BRST symmetry. And higher order terms are going to tell us if it does so quantum mechanically. Now, because Q squared, or QBRST squared, is 0, then it follows that the eta function squares to 0. And this gives a whole collection of quadratic constraints on these coefficient functions. So this is the most general coefficient function here in expression 6. I haven't used the quadratic constraints to simplify it in any way. And what I'll do is I'll define the following multilinear operation on the space of interactions. So I've just defined it here in equation 7. It looks like I'm just defining a Lie algebra, but it eats arbitrarily many entries, or n many entries, and it uses as structure constants the coefficients of this eta function. In that case, a simple calculation shows that the BRST variation looks like this Mark-Cartan equation here in expression 8. And so the BRST variation is just this Mark-Cartan equation. But then if I'm saying Mark-Cartan equation, I must mean Mark-Cartan equation for something. And that something, as it turns out, is an L-infinity algebra. So indeed, the statement that eta squared is 0 is exactly equivalent to the statement that these coefficients and the brackets that I've defined define an L-infinity algebra on the space of interactions. And what I really want to stress is that these brackets are computable. So if you use Q on any interaction, it's going to take this form. It's going to be sort of a rotation in the space of interactions, plus possibly this total derivative, dj, which is invisible to the integrals because you integrate when you put in an interaction. And so, of course, it's always going to take this general form. And then if I work in some sharp cutoff regularization scheme, well, first let's just talk about, there's going to be, of course, a single bracket of just one single calligraphic I. And that's just going to be like the original Q acting on math cal I. And then the 2 bracket has just this very nice form. It's a very simple formula. And so it is truly computable. And for example, you can see if you just use all the definitions I provided, that if you take, for example, a 2D G gauge theory, and some matter theory with G global symmetry, for example, free fermions with a vector current or something like that, then you can open up Peskin and Schroeder and you can see how do you add ghosts, how do things vary, and you can study the interaction, the usual A wedge J interaction that, in scare quotes, like gauges the G global symmetry of the matter theory. And indeed, if you use this formula here I've written in expression 9, it's a straightforward example, actually. In fact, I would show it if we had more time. It's very straightforward to just see, you plug this in, and the 2 bracket I of this A wedge J interaction exactly recovers the well-known one loop anomaly for G gauge theory. And you could imagine that if I was working in 2K dimensions, that I would get, F wedge, F wedge, F wedge, F, etc. And this little pound sign out front just points out that, I ignored various combinatorial factors, which possibly might give 0 if I had chosen all my matter and representations correctly. All right. And then I can also talk a little bit about some generalizations. So I've kind of told you already about the eta function, which is sort of the analog of the beta function, but I can systematically compute corrections. I mean, there's sort of an analog of the anomalous dimensions. And so indeed, that's represented by this bold Q here. And this lets me systematically compute corrections to Q acting on local operators. So it's given by a similar simple form. And this simple form is very useful for computing perturbative corrections to BPS operators and twisted SQFTs. This is sort of generalizing how the Kanishi anomaly gives corrections to the chiral ring in supersymmetric quantum field theories. We can also consider position-dependent interactions. So in that case, there's momentum inflow at each vertex, and the space of interactions gets a little subscript pi, and this sort of reflects the momentum-colored operad structure, if those words mean anything to you. There's a very special case of this when holomorphic momentum can flow in at the vertices, and this recovers the case of lambda brackets, or n-Lie or homotopy conformal algebras. These lambda brackets already show up in standard VOAs. And finally, in our paper, we also study auxiliary, boundary, and defect systems. And indeed, for example, if you study some chiral VOA, all OPE coefficients of the VOA can basically be obtained from studying these brackets, and also the brackets of the system with some decoupled free fermions. So indeed, lots of the information, essentially all the information, is in these brackets. So in the remaining minute, I'm just going to flash some quick results, very quick, about the holomorphic topological theories. So by holomorphic topological theory, let me just be fast. I just mean a theory on CH times RT, where anti-holomorphic translations in the CH are Q-exact, as are all translations in the topological direction. And I'm generally interested in theories of this very broad form here in equation 14. And as kind of promised on the previous slide, in such theories we'll be interested in brackets which take the most general form like this, where holomorphic momentum is allowed to flow in at the vertices. It's not obvious, but the Feynman integrals that contribute will take this general form. Actually, this form is very straightforward. It just says, integrate over the position of all the vertices, holomorphic momenta is allowed to flow in, take a product of all the propagators, regularized. This little d is maybe the only thing you weren't expecting, but that's roughly because we're interested in the Q of things, and there's various descent relations that relate d to Q. It's okay. It's just a nice, straightforward formula. And I'm going to suppress the details, but it's actually not very difficult. Just simply by counting form degrees of the integrand and the things contributing to it, one can show that all non-vanishing Feynman diagrams take the form of what are called n-Leman graphs. And here I've drawn some pictures of 2 Leman graphs. And so these would be relevant, for example, if you had 1 holomorphic direction or 2 topological directions. And then I'm run out of time, so I'll just flash this extremely quickly, is that it turns out that the Feynman integrals associated with them satisfy various quadratic identities. These quadratic identities essentially enforce the associativity relations, or the fact that Q BRST squared is equal to 0 in a diagram by diagram way. In one of our papers, we show that, at least in the n equals 2 case, that you can bootstrap, it seems, all the Feynman integrals just from these identities, so you don't actually have to compute these things. And indeed, a purely graphical proof on these very restricted class of diagrams on the previous slide can be used to argue that all loop graphs in theories with greater than or equal to 2 topological directions must vanish. So with that, you can scan this code, and you can look at the paper, because that was probably a bit fast. Sorry for going over.
Any questions? Comments? Wait for the microphone.
So can you apply this, if you apply this to 2-dimensional Landau-Ginzburg models with a superpotential massive, do you see anything like is there any relation to the operatic structure that you see on the solitons?
I assume you're also talking about this web-based formulation of your paper. Yeah. I understand it's extremely closely related, but I don't have anything super concrete prepared.
Okay, the other question is, I think from factorization algebras, we expect local operators to have some kind of EN structure.
That's right, yeah.
And so do you think you can recover that from this?
Yeah, actually we have a whole section in the paper talking about the relationship between
Okay,
these.
cool.
Yep, section 6, check it out, people.
Yeah, thank you. So this quadratic relation, do you have a geometric interpretation of them? Because they look similar, like this Griffiths transversality conditions.
Sorry, what was the last part? They look similar to?
They look similar to this Griffiths transversality condition. So why are the quadratic? What is the geometric interpretation? What is the interpretation of this quadratic?
Okay. So the interpretation is described in the oldest of the papers, and it can sort of be related to the configuration space of the various graphs that appear, but it's a bit involved. I could go into, for example, how you might use equation 16, but to actually describe the configuration space might be.
They look so similar that I was wondering.
Yeah, it's probably related, but yes, it enforces it on the nose, order by order, basically, in perturbation theory. Yeah.
I have a question. Is there some physical interpretation of zeros of these eta functions?
Yeah, they're BRST invariant theories, basically.
Okay.
Okay, so if there are no more questions, let's thank the speaker again. Okay, so this is the end of the Gong Show. Let me remind you that at 6 p.m. there is the poster session and the reception. Am I right? Yes. Okay, so see you there. Bye.